Hello, wonderful people of the internet. Welcome back to another episode of Simuleos. Am I good? I think I'm good. Okay. Shadowmecia and anyone who might be lurking in chat, hey, thanks for being here. Oh, I can hear myself in the background. That's not good. Let me fix that. Sorry about that. That means the the intro there. Everyone could hear the background music twice, which is not. It's not good. Oh well, it is what it is. Anyway. Thank you guys so much for coming in. Let me go ahead and introduce what we're working on today. I'm going to CD into Projects Galilee over here. And now we're going to run into CD aux. And we should be able to run mpv all.mp4 loop. I misspelled loop. Let's try it again. There we go. Okay, so lots of things to talk about. Shadowmecia. Gifted sub yesterday from Screamer Chaotix. Yeah, so at the end of stream yesterday, we were talking about a bunch of different things. Let me just go ahead and full screen this guy, and let's kind of talk about it a little bit more. So, basically, in the middle of stream yesterday, we kind of found out that my GPU was really not powerful enough to run the simulations that we needed to run. For some reason, I feel like the video and audio is out of sync. Let me fix that really quick. I think this should do it. Maybe it was fine and I was just being a bit fussy about it. But yeah, so we realized that my GPU was just not really good enough to do the simulations that we need. And frankly, we're quite far away from anything we're doing on stream or on YouTube from basically generating enough income to be able to buy a new GPU to do more computation. So I reached out to the Julia Lab, in particular, one of my friends who is working on kernel abstractions, and we talked about it a bit. And he basically said that, I could use Julia Lab resources, or we could find a way to extend my MIT account and have access to the clusters that, we have at MIT. So for the GPUs in the future, probably I'm going to be using the GPUs that are available from MIT. And that's probably what we can do, at least for the near future. I mean, look, I'd love to have my own little cluster that we could do stuff on, but let's just focus on what we can focus on. Sir Komodos, Amorous, hey, thank you guys so much for coming in. Okay, also, I don't know why, but it is chilly. It is downright chilly. I'm in Barcelona. I lived in Boston for a year or whatever. And I was used to the cold. I got used to the cold. I like the cold. But for some reason, I was colder than I had ever been yesterday. Not during stream, but just before stream when I had to go to the to a clinic or something. It was a 30-minute walk. It was in pouring rain. It was absolutely miserably cold. It'd been a long time since I'd been that cold. I never got that cold in Boston, so I don't know what the deal is. But man, if I'm sniffly, like if my nose is all like today, that's why I could probably turn the heater on. But the problem is, even if I do turn the heater on, it doesn't actually heat up the basement. So I need to find a solution to that. But anyway, it's fine. I don't know why I'm going on the ramble session. Anyway, what you're seeing in front of you is an n-dimensional galaxy simulation, where n is, at this point, 2 and 3. We'll do the one-dimensional simulation soon. We'll do the four-dimensional simulation soon. We can do those today. But there's a lot of little things that I want to work on to make these simulations just better. If you weren't here for yesterday's stream, we started out with these visuals that you see right here. Here's a 2D simulation, and you just saw a 3D simulation before. Now, what we ended up doing is, after streaming for about 5 to 6 hours, we managed to generate the exact same images that you see before you, the exact same videos, which was actually very heartening. Is that a word instead of disheartening? It was actually very nice because at the end of the stream, we were actually able to run the simulations in parallel, both on the CPU and on the GPU. And based on our naive parallelism that we used, we found that the CPU and GPU basically gave similar results. Now, granted, I'm using a really old GPU and a really new CPU, relatively new CPU, so it's not exactly a fair comparison. But what I'm going to be doing today is kind of working with that parallelism, fixing up a lot of the little things that I didn't really like from yesterday's implementation, and then hopefully doing the full 4D simulation, and maybe a 1D simulation as well, so we can see the difference between each of the different simulations, 1, 2, 3, and 4, and kind of put them all into one video that we'll have playing in the upper left-hand corner for stream. Now, before getting into any of that, I do want to take some time to look at, okay, let's move this up here, to look at an algorithm archive PR, in particular the one for the Metropolis algorithm. Okay. in particular the one on the Metropolis algorithm, which is the one that we've been working on recently. I think I'm pretty sure that there's a video audio delay. Let me go ahead and fix that. 1 second. It's such a pain. Yeah, my GPU is really weak. So even moving like screens around will sometimes cause video and audio delay, which is not particularly good, but it is what it is. We are also going to make this that. Move over here and do the same thing over here. Okay, so let's look at the algorithm archive PR first, and then we'll hop on to other stuff. So CD into projects, algorithm archive. All right, over here, CD projects, algorithm archive. All right, let's go over here to github.com. Here we are, github.com, and let's take a look at the Metropolis chapter. Algorithm archive here. Wait, what was that? QCTRL, Python, what is that? Okay, anyway, not kernel abstractions. No, okay. Screwed up. There we go. Take a look at the PR here. Should be one for Metropolis there. Lots of updates since last time. Okay, so now what we're going to do is basically pull down the latest chapters, latest updates, and read through the first bit of the chapter, the Metropolis chapter. So yesterday we went through the probability density functions. Today we're going to look through the first bit of the Metropolis algorithm. Yeah, and go from there. Let's see how it goes. I'm checking something also. I'm checking my audio levels over here on the side. Yeah, so basically what happened was yesterday while I was streaming, I realized the background music was maybe a little bit loud, so I made it a little bit quieter, which should solve most of the issues we were having with the video and audio and all that kind of stuff. But, you know, I have been genuinely thinking about maybe just not having background music, but I don't know. I think it just makes the stream just a little bit nicer, specifically like when you're doing debugging and stuff like that and you don't really have anything to say, just to have a little bit of background music there. I don't know, like I go back and forth and I always end up settling on having background music, even though a lot of people say they don't. I don't know. I don't know. I really don't know the answer there. Anyway, it doesn't matter. Let's go ahead and grab the latest changes here and go from there. Grab this git pull over here and just paste. I think we're on git branch. I think we're on the right branch and everything. Yep. So let's go and pull the latest changes. Perfect. Okay. And again, guys, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know. And I'll totally address it as soon as I see it in chat. And yeah, like I said before, like I said yesterday or whatever, I don't know what the deal is, but for the past week or so, I've really felt like I can, start doing the longer streams again. I feel like my stream stamina is much higher than it used to be. Like doing the stream yesterday, I thought was genuinely fun. I think I really enjoyed like the entirety of the stream. Everything about it I thought went super well. So I don't know, like if you guys have thoughts on how the stream's going, about things that you might want to be improved, all that kind of stuff, feel free to let me know. And I don't know, I'm happy to talk about it. Let's go over here, make this bigger. Now let's go into the algorithm archive, localhost. Okay, so again, let's go ahead and talk about what this PR is. So this PR will be probably the first chapter that was not written by me that's going to be incorporated into the algorithm archive. So this encompasses two different chapters, one on probability density functions, like the binomial distribution kind of sort of type of thing. Not really, they don't really even mention binomial distribution, but like probability densities and stuff like this. And the other chapter is on the Metropolis algorithm. So yesterday we looked at the probability density chapter, and today we're going to look at Metropolis. Okay. So we're just going to read through it, see what makes sense, what doesn't. There might be a few updates that need to be made, but essentially we're going to go through to essentially this bit here. We're going to read through this section. And then tomorrow we'll come back and we'll read through the random walk and all that kind of stuff. So that would make it so once we finish this chapter, we've read through each section 2 or 3 times, and it should be mostly finished at that stage. Okay. So, the Monte Carlo integration method uses random numbers to approximate the area of pretty much any shape we choose. The Metropolis algorithm is a slightly more advanced Monte Carlo method, which uses random numbers to approximate a probability distribution, where D is a domain of P of X, i.e. all possible values of the X for which P of X is defined. Does that make sense? where D is a domain of P of X, i.e. all possible values of X for which P is defined. All possible values, I guess that makes sense. And f of x is some function that is proportional to p of x, such as a statistical frequency distribution, i.e. one that counts the number of occurrences of each x. The number of occurrences of each x. Sure. Okay, yeah, I see what they're going for. The integral in the denominator is a normalization factor, which ensures that the sum of all probabilities is unity, i.e. this. A one-dimensional example is the normal distribution or Gaussian distribution here. Sure. In practice, it's easy for us to know f of x, but the integral in the denominator can be quite difficult to calculate, even numerically. This is especially true when the coordinates x are multidimensional, and f of x is an expensive calculation, as we'll see in the examples below. Should this be in parentheses? I feel like that should just be comma, but whatever. I think either way is fine. Okay. So here we're going to do an example application. So one example of a complicated probability function arises when considering a physical system of n particles. These could be atoms, molecules, or even star systems. For such systems, we can usually describe the potential energy of the system as a function of each of the coordinates of all particles x. So we have E of x is the xyz locations here. Okay, where x of I, y of I, z of I are spatial coordinates of each particle I. So altogether, there are 3 n coordinates, making, yeah, okay, we need to modify that. Okay, let's go here, up to the top, and let's go to files changed, and we have to remember how to do an n dash. Yep, this. All right, perfect. And let's go through. Should be, where is it? There, this one. Okay, and what do I want to do? I want to, he had a dash in here somewhere. This guy, change this to an n dash. There we go. Start review. Okay, making e to the x a 3n dimensional system, which can be computationally intensive calculation on its own. But it doesn't end there. The physicist Ludwig Boltzmann discovered that when such a system is in equilibrium at some temperature T, you can describe the probability density of the system for any set of coordinates x using the following, where the numerator is called the Boltzmann factor and q is a normalization constant. We can see now that the probability density function is a difficult calculation, particularly because of q. Almost always, no analytical solution exists to the integral in q, and the numerical integration is unfeasible. To see that q is unfeasible to calculate, imagine there are just 10 particles, all of which exist in a 1D world, restricted to a line segment. Let's assume that these particles interact, meaning that the position of one particle affects that of another. This could be the case, for example, if all the particles were charged, so they would be repelling or attracting each other. Yeah, sure, this makes sense. This means that x is equal to E of x here of the system is a 10-dimensional function. It would not be possible to simplify it further due to the interactions. Thus, the Boltzmann factor E here is also a 10D function. And so, to calculate q, hey Karopeb, how are you? We would have to integrate the Boltzmann factor 10 times, one for each coordinate here. I don't like this and so. I'm going to be a bit picky. That's fine. I'm just going to remove that. Where is that? And so should be down here somewhere. Where is it? Okay, that was not what I expected. How do I, what? Are you kidding me? And so, okay. This guy, why is it on? Okay, that's fine. And put a period there. Start review. Keep reviewing, I guess. Okay. And so to calculate q, we would have to integrate 10 times, one for each coordinate. All these need punctuation. Okay, I'll add the punctuation in just a second to all the formulas. In most cases, there's no known analytical expression for the above integral, so it has to be done numerically. To do so, imagine that we divide the 1D line segment into only 50 different intervals, allowing each particle to take on 50 different positions. This is equivalent to dividing the length of a football field into intervals of about 2 meters, not a resolution you'd want to watch the game in. Even with such poor resolution, the number of different combinations of positions is 10 to the 50, a colossal number indeed. All right, let's keep going. That's another M dash or dash that needs to be changed to an N dash. Let me see, I changed that up here, there. I'm gonna grab this guy and Control C. Go down a bit. What do you mean no item selected? Can I copy that? All right, that'll do. Okay, well, let's go down. Where's that dash? Here it is. Change this to an N dash. Add review comment. I hate that I'm being so like picky, but I don't know. You just need a function which is proportional to it. Oh, why do they use so many dashes? There's so many dashes in this chapter. To see how large the number is, imagine a single computation of e to the x took only 1 nanosecond on a single processor, which is much faster than most energy calculations for physical systems in practice. With that speed, it would require 10 to the 41 seconds on a single processor to calculate Q, which means that even with all the processors in the world running in parallel, there could be billions or trillions of them. Calculating Q would still take longer than the edge of the universe by many orders of magnitude. I feel like we can just remove the dashes entirely in that sentence, and it would make perfect sense. Let's go here. I have to go this. Come on. And now I need to do this. And let's go ahead and remove the dash here and the other dash here. All right, add review comment. All right, let's keep going. What's really powerful about the Metropolis approach is that you don't need to know the probability function itself. You just need to know a function which is proportional to it. Okay, so here's the thing. There's so many dashes in this chapter, and I feel like that some dashes are warranted, but that one I feel is not warranted. I feel like a comma would do just fine. Does it? You just need to know that... I mean, look, it is a new sentence. Right, so what's really powerful, it's got its own object, it's got its own... So what's really powerful about the Metropolis approach is that you don't need to know the probability function itself. Instead, you just need to know need a function which is proportional to it. I'm going to split that into 2 different sentences. Here. Oh, come on. Instead... Sure. What do we have here? Which means, what this means for the Boltzmann distribution is that you only need to know the term f of x. The Metropolis algorithm can bypass the calculation of Q altogether. 1 second. Here, can bypass the calculation of Q altogether. And use f of x to generate a distribution of x, which follows a probability density p of x. Sure? Okay. In other words, it can sample values of x in such a way that the probability of sampling x will follow the actual distribution p of x. Thus, if Metropolis was used to sample from x, the number of occurrences of x would be proportional to p of x. Numerical normalization can be done by using the total number of samples instead of performing an integration. This fact dramatically reduces the number of calculations needed to approximate the probability function. Sure. Finally, the Metropolis algorithm can be modified or implemented in other algorithms. I'm going to say other methods instead of other algorithms. Just because algorithms being really redundant here. In other methods and forms the basis for many advanced sampling algorithms. All right, add review comment, keep going. The most popular is probably the Metropolis-Hastings algorithm, which is fundamentally the same. Some other algorithms that use this method are the Metropolis-adjusted Longevian algorithm and Hamiltonian Monte Carlo, to name a few. They're often used for physical systems that follow a Boltzmann distribution. Perfect. So now all I have to do is add punctuation to all of these guys. So let's do it. Okay, so we're going to look at every equation, just add punctuation to it. Here, so this guy needs punctuation. I think it's going to be what is it going to be, a comma? I think it's going to be comma. Add review comment. This guy, some all probabilities here. This guy's going to be a period. Here we go there. Add review comment. The fourth dimension is a vision. Whoa, let me go ahead and read this. The fourth dimension is a vision in our awareness that there is a object which we focus. What is fictive? With our eyes, but there is another ability to feel an object in our space. And I name it sonar. Wait, sonar. Oh, I think your thing got messed up with an emote. Was that science enough? I don't know if I fully understand what you're saying. Could you explain a little bit more? I don't really understand what you're saying at all, honestly. If I'm yeah. Okay. So here we have this guy. This is going to be a period. Let's go here, period. By the way, we're going to get to the 4D simulation soon. Just going to finish up this chapter review. Here, this should be a comma. Add review comment. Okay, here, this one's going to be a comma as well. Add review comment. This guy's going to be a period. What? No, that's not the one. There we go. Cancel. What is this? A period. Add review comment. Let's see. And I believe we're almost done. This guy's going to be a period. Add review comment. And is that it? No, here's one. This is going to be period. Add review comment. All right, keep going. We're almost done. Okay, so that's it for now. Okay, so comment. So I've been through. Looks good. Mostly done. Just have to look at the second half of Metropolis. Okay, let's go ahead and comment. Submit review. So we're almost done. So this chapter, again, is a chapter on the Metropolis algorithm. It incorporates probability density functions, the Metropolis algorithm, but the Metropolis algorithm is quite long, so I split the review up into three sections, sorry. One is the review of the probability density functions chapter, which we did yesterday. The second is the review of the first half of the Metropolis algorithm, which we did today. And then tomorrow we'll finish up with the second half of the Metropolis algorithm, and that will hopefully be the entire chapter done. And with one more look over at the whole thing, I think we're actually good to go. Just small nitpicks here and there. But yeah, this chapter is mostly done. It's just going to take maybe a few more days to finish up. Pretty happy with that. Okay, so now we can finally move on to the 4D galaxy simulation. So let's talk about what's actually happening here. I mentioned this at the start of stream, but this visualization that you're seeing here is, first of all, if you're just hopping in, this visualization is not 4D. It's 3D. And you'll see it flips over to a two-dimensional simulation, right? What we want to do is we want to basically do this very same visualization, but in 4D. One second. I am changing the song. I don't like this song. All right, perfect. 1 second. Okay, so what's happening here? Let me go ahead and pause at any given point in time. Essentially, every single frame of this simulation is something known as an n-body simulation. The idea is that you have n particles. Here it's something like 100 or 1,000 particles. I think it's 100 particles. And the idea is that at every single time step, this particle up here is feeling some sort of force of gravity by every other particle in the simulation, right? So this guy feels every other particle here and is moving accordingly. So if we watch its motion, you'll see that it's going to kind of fall back in to this cluster of other particles that we have at the center. And basically all the particles are doing the same thing, which is why we have this big cluster here. Now we can watch it for a while, but ultimately it should flip over to 3D in just a second here. Okay. So, essentially what we're doing is we're starting the simulation off in like some random uniform distribution of either a square or cube or something like that. And we're just letting all the particles come together and splash out and stuff like that. Now, in order to turn this into a galaxy simulation, there's actually a lot of other things we need to simulate. Like, for example, dark matter, which, quite frankly, I know basically nothing about. right now you could kind of imagine each particle being like a little green star in the black expanse of my monitor. And the idea is that, they're all kind of only really feeling each other's forces based on, just the force of gravity. But right now, all the stars have the same mass, and they all have the same motions and stuff like that. I mean, in principle, if we were going to do a galaxy simulation, we also need like a black hole at the center of the galaxy. We need some sort of initial velocity. We've got a lot of things that we have to do to make this a more physical simulation. My interests in this simulation lie not particularly in the physics, though. What I'm really interested in doing is taking this n-body simulation and speeding it up so that we can use that process of speeding it up in other simulations. We'll talk about how to speed it up and stuff later, but for now, I just want to say that these visualizations that you're seeing here were actually generated 2 days ago on stream. After basically during stream yesterday, we did everything we could to parallelize the system. That is to say, we took what we had, which was on a single core CPU, and then we modified it so it could run multi-core CPU and also multi-core GPU. Again, during the stream yesterday, I kind of ran out of GPU memory, which is something that we'll have to deal with when we get there. But for today, we have a bunch of little things that I want to do. The first thing is I want to take a second to revise the parallel methods that we put in yesterday. There were a bunch of little things that we did that I just wasn't really happy with, and I want to fix those. After that, we can start talking about a bunch of different things. Like, for example, how could we better visualize this? Because right now we're just plotting all the particles out in NuPlot, but in principle, there are better ways to do this. So I think what we're going to do is, 1, try to fix up the parallel methods. 2, do the same simulation here that you see for 2D and 3D, but also in 1D and 4D, so we have this nice progression for 1, 2, 3, and 4 dimensions. And then, once we get all that done, we're going to come back and try to speed up the n-body simulations, either with the visualization part of things, where we're going to try to directly output an image, or we can speed up the actual simulation by incorporating basically a parallel summation in the step where we're trying to figure out like how every single particle affects every other particle in the simulation. So there's a lot to do, which is why I wanted to jump into this as soon as possible. I'm going to be streaming for the next basically 5 hours and 30 minutes. If I start to sound or feel a little bit down or tired, I might put like a little Swoleos workout in the middle just to kind of get my energy levels back up. Maybe I'll do something else if I'm also getting tired of the simulation. I'm happy to chat about literally anything to do with academia, maybe physics, computer science, even biology and chemistry. Fair game. I'm happy to talk about them. So yeah, feel free to ask any comments or ask any questions you have, comments, questions, concerns, anything like that. I'm happy to talk about basically anything. And let's just, I guess, go ahead and jump into it. If you haven't been to the channel before, this is your first time ever here, this is Leos Labs. The idea is that we are trying to do research in a really open and engaging way that really, encourages other people to take part in the research process. That's the whole goal. That's what we're trying to do. And we're hoping that, through these simulations, people can come, they can chat, and we can just enjoy the process of doing research together, because it is quite fun. And I think it's worth doing, with others, Anyway, there's a lot more to it than that, but this is kind of where we're at. Do we even have a definition for dark matter yet? Like, it interacts with our universe, but does ours interact back or change dark matter? I gotta be honest, I'm gonna let you know the maximum I know about dark matter right now, and you're gonna see exactly how little I actually know. If you want to, look it up and give me like articles or something to look at as well. Let me open up ZeroPP. Move this over here, that over there, perfect. Okay. Right, so when it comes to dark matter, what is dark matter? Ethan, if gravity travels in waves, couldn't overlapping waves form constructive interference and create chaotic spots of gravity that's hard to predict, like dark matter? Maybe, right, that could be true. I actually don't know. Like, when we say, I actually hadn't really thought of it that far. Let's talk about two different things. So one, I'll talk about what I currently know about dark matter. Dark matter. And two, we'll talk about the gravity as a wave, because both of them are interesting in different scenarios. Give me a second. It is cold. I don't know why I'm like sniffling. It's cold. I'm hoping that like during stream I'll warm up. The problem is, like, if I turn on the heater, I know like halfway through stream I'm actually gonna start feeling like really hot. And so like I'm kind of in that weird stage where it's like, man, I'm either I'd be cold or I'd be too hot. I don't really know what's going to happen. So basically, if I'm still sniffling in the next hour or so, like I'm still quite cold, I'll turn on the heater or something. Okay, so what do I know about dark matter? Here is literally the most I know about dark matter. Oh, I don't know why that whole thing turned green. 1 second. If you take a three-dimensional galaxy, a 3D galaxy, 1 second, and you let it evolve for a certain amount of time, it will eventually form a two-dimensional spiral galaxy. Right? So let me just go ahead and draw like a quick sketch of the spiral galaxy. I guess we'll do yellow for stars. You'll have, I guess we'll do dark blue in the center for the black hole, and then we'll do yellow out here. So what you'll have is a whole bunch of stars that are all kind of rotating in some overall direction like this. So they're all kind of rotating around like this. And you could imagine these kind of spiral star clusters, which are kind of going like off here or something like this. Like if you've ever seen the Milky Way, you kind of know what I'm talking about. It's basically like, it's not quite a disk. It's basically a bunch of stars rotating with these little like spirals coming off. The important thing to note here is that if you just run an n-body simulation, you only run it with stars without taking into account the dark matter, only stars. The rotation at the center in this region here will be faster than the rotation out here. And this just has to do with the fact that the stars are closer, so the forces acting on them are much higher, and therefore they're just going to rotate a lot faster, right? There's other things to do with the moment of inertia and stuff like this, but what you find actually in nature, like when you look at galaxies that are actually in the real world, you notice that the rate of rotation in this area is not too dissimilar than the rate of rotation in this area. And the only way to really get that simulation to work out, to make it so that the rotation in the center is slow enough that it kind of matches the rotation at the rest of the galaxy, is to add a huge mass at the center, therefore increasing essentially the moment of inertia. And by doing this, you can then create a spiral galaxy that looks more or less physical. And that is the only, like, that's what I know dark matter is. It's essentially this giant mass that you have to add to the simulation in order to get it to make physical sense. Like that's all I know about dark matter. It's just used in simulations, in theoretical methods, to get the math to work out. I should know more, and obviously if you guys have more information about it, feel free to post it. The problem with dark matter and all this kind of stuff, specifically when we start talking about astrophysics and cosmology and all this kind of stuff, is it just gets really dense really quickly. And you know me, I love jargon, but I like jargon when it's like placed correctly. Like it's like, here's a review article or something like that. And maybe we do spend some time reading review articles, learning more about cosmology, all this kind of stuff. But if you guys have like a more intuitive grasp on what it is, feel free to let me know. You should add that the speeds are measured by redshift, right? Yes, so I don't know how they're actually measured physically. I only know how they're measured numerically. This is the first time I've heard that they're measured by redshifts, but I guess that makes sense, right? Because, you would expect, I guess, a faster, how does this work? So we have light, which is going to be, you've got red and blue, and here's the color, right? The spectrum of light. And then you have the wavelength, so everything below this and everything above this. So this is slow, and this is fast. So if you have a particle that's emitting white light and it's moving particularly fast, then we would perceive it as red-shifted or blue-shifted. Maybe I just don't even understand how that works. It's been a long time since I did the basic physics classes, Okay. There was another topic here that we talked about, which is gravity as a wave. And I just want to say, in the same way that a photon is a wave, I don't know exactly how interfering gravitons, in the same way I don't really know how interfering photons would create different patterns, would create different patterns in the fabric of space-time or whatever. I don't exactly know the relation. What I'm trying to say is I don't know the relation between gravitons, gravitational waves, and dark matter. I don't know if there's a relation. There probably is. I mean, there's a reason we spent so much money trying to measure gravitational waves, right? So there must be some reason why we did that, and I don't fully understand it. If you guys have more information, feel free to let me know as well. Is blue shifted if it's moving towards you? I guess that makes sense. Okay, so why when you look at a pool? Okay, so when you look at a pool, right, there's a line at the bottom of the pool that goes like this, right? And when you look at it, one side is red and the other side is blue, right? When you look through the water due to refraction. And I feel like that has something to do, I always forget, but it has something to do with this as well. Think of it as Doppler effect, but with light, just like how a car, yeah, right, I recognize that. How a car sounds higher pitched when it's moving towards you and lower pitched when it's moving away. Yeah, that's probably fair. Anyway, let's go ahead and close this here. And let's go ahead and delete some of this stuff up here as well. We'll leave the questions, but I'll delete this stuff here. Okay. Right, so guys, feel free to talk more about the physics here if you want. Like I said, there was a time, maybe 5 years ago during the PhD, that I knew a lot more about physics. I genuinely was better at physics than I am now. Right now, I've like kind of forgotten everything to do with physics, and usually I get a little PTSD when I start going down the physics hole, you know, because like for the longest time in my research career, and I mention this a lot on stream, I don't hide it from anybody, but I have always been more interested in the computation than the physics, but I do computational physics, which means a lot of the papers that I've been putting out are well, physics papers, not computation papers. And so I tend to feel like, I don't know, I tend to fear that as we go more and more towards physics, we're going to move further and further away from stuff that I consider to be interesting, quote unquote, right? So that's kind of where we're at. See you, Crop App. Have a wonderful afternoon or whatever time it happens to be your time. Hopefully we'll see you around later. And yeah, thanks for stopping by. Okay, so let's do, 1 second. I have to do one more thing. I think the video and audio is still kind of out of sync. Let me see if I can fix it. Here. Okay. And then let me also check one more thing. I feel like my audio is a bit quiet. I don't think I can do anything about it. Yeah, okay. I don't think I can fix that. I think it's just gonna be what it is. Okay, that's fine. Also, I somehow like F11. I pressed F11 a bunch of times when I did that. Okay, so let's go back over here. And let's go ahead and hop into it. So yesterday, right before I went to bed, I thought of a bunch of different things that I kind of wanted to work on today. Let's see. So what do we have here? So first of all, if we want to go any further with the parallelization, so let's do here, talk about parallelization, right? So as you guys know, we're doing parallelization with a library called kernel abstractions, which allows for us to do basically parallel CPU and GPU at the same time. It comes with a bunch of caveats in that like the error messages are next to impossible to read and all this kind of stuff, but for the most part it works and it's quite nice. So yesterday, we ran into a few issues. The first of which was we eventually need to do a parallel sum. Or reduction or whatever. I always call it parallel summation. A lot of other people call it parallel reduction, but look, it's kind of the same problem, depending on how you want to call it. This, I'm not sure exactly how kernel abstractions works, if it has an appropriate parallel sum or not, so we have to dig into that. I don't know if we have to write our own method or we can use a method that already exists, whatever. So that's number one. We might not do this in order. This is just a bunch of things to look at. The other thing is I wanted to see if we could use, oh, yes, function pointers. In CUDA kernels. That's my question. The reason I want a function pointer is I was hoping to make it so we could swap out like the force of gravity and stuff like that. The reason this would be nice is because, you know, in 4D, for example, we might have a 1 over r cubed potential or 1 over r cubed force law instead of 1 over r squared force law. Just stuff to keep in mind. Okay, and then we want to do 3. And this one is, I think, a little bit easier. Oh, right, optional arguments in a CUDA. So optional arguments in a kernel abstractions launch configuration wait event. So these are the things I want to look at. I'm actually going to take a look at them in just a second. I'm going to take a 2-minute break before hopping into this. So let me do that really quick, and then we'll be back and we'll work on probably 3, 2, and then 1. And then hopefully we can get all the parallelization questions out of the way in the next hour or two. And then we can do our 1D and 4D simulations. So that's hopefully where we'll be. Give me a second. I'll be right back. Yeah, so I just turned on the heater. It was apparently 15 Celsius in my apartment. So I decided to at least bump it up to be like, I bumped it up to 20. We'll see how it actually gets. Give me a second. Let's go over here. There. Okay, perfect. Also, what is 15 Celsius in Fahrenheit? 15 C in F. 60 Fahrenheit. So it's not super cold. It's like right at that room temperature. Like, you know, it's kind of just a little bit colder than I wanted it to be. Also, like, I don't think we're allowed to. Yeah, I think in Boston we weren't allowed to have our heater below 60. Like, it wasn't allowed to be below 60 because if it's below 60 inside, it's probably way below freezing outside, and so the pipes could potentially freeze and stuff like that. That might be why I'm so chilly right now, because it means that in my apartment in Boston, it never really went below 17 Celsius or something, so it's actually colder than it was in Boston. Well, that's good to know. Okay, let's go here. Control C, and we're just going to, I don't know, CD here, clear. Over here, we're going to stop building the algorithm archive, CD, clear, and let's go. So we're going to have to create a bunch of little minimum working examples, which is just going to be testing how kernel abstractions works and all this kind of stuff. So CD into projects, Galilee. Over here, CD into projects, Galilee. And so we're going to tackle the first thing, which is, I guess we'll do optional arguments and kernel abstractions wait events right now. So let's go ahead and create a minimum working example for that. Ooh, man, my desktop is lagging a bit, isn't it? Oh, no. Oh, well, we'll see how this goes. I think there are regulations in France saying that schools can't teach with a temperature, when the temperature inside is below 16 Celsius. Really? I feel like 16 Celsius is pretty... Oh, I am at 16 Celsius, yeah. I mean, I don't know, at least in Alabama... you know, heaters were kind of unnecessary, right? Like, they were kind of a waste of time because you're never going to get into a situation where you actually need a heater. Like, it will get below freezing sometimes, but it's fine. Like, put on a coat, you'll be okay. Like, the truth is, though, you always need an air conditioner. Like, life without an air conditioner is just abysmal. But life without a heater is fine, you know? But I think in the Northeast, a lot of people don't have air conditioners, which is, it boggles my mind, if I'm being honest. Like, how you could possibly live without one. But anyway, also from Okinawa as well. Like, you kind of need an air conditioner. Anyway, I'm rambling now. So we're going to CD into projects Galilee. Over here, CD projects Galilee. Okay, so I'm going to talk about the parallel implementation that we did yesterday, and I'm going to pinpoint a lot of things that I genuinely hate about the parallel implementation that we did. So we're going to CD into source, ls here, and then we're going to go into vi, I guess forces.jl is where I actually want to do. Actually, let's start with simulate. Okay, so the way this works right now, okay, so right now we don't really have very many like IO methods or anything like that. Right now what we're doing is at every time step, from 1 to number of iterations, where your iterations are the number of time steps you're running for, you're basically going to write to file at the start of the time step, then you're going to find all the accelerations, that's what this guy is doing, and then you integrate by using your integrator, right? So for our finding accelerations, we're going to be using the n-body algorithm, which is just, you know, it's just a very simple, you're looking at all the other particles type of thing. And our integrator here is still Verlet. We can add other integrators like Runge-Kutta or whatever, but we'll deal with that later. The first thing I want to do now is actually CD into, I see what happened. CD into projects, Simuleos, and then GPU. Over here is CD project, Simuleos, and then GPU. And what I want to do is check out some very basic kernel abstractions tests and stuff like that. So I think I should have like a test.jl. Let me go into vi test.jl here. So what I want to do is test to see if we can pass in optional arguments to kernel abstractions kernels. Again, the reason I want to do this is because I want to configure the equation that we're solving kind of outside of the kernel runtime, right? So that's what we're trying to do. I don't know how possible this is, so we're just going to give it a go. So I think what I'm going to do is move or cp test.jl into test2.jl. I know it's super wonderful naming conventions, but I don't really care. vi test2.jl. We're going to do kernel function ftest kernel. Seems fine. I don't actually know what I'm going to do here, except maybe I'm going to say, we read in an optional argument, a is going to be equal to 1, and all we're going to do is say output of TID is going to be equal to a, or something like this. So we're just going to do, in fact, let's just say input. So we only have one thing that we're reading in, just to minimize the test. So it's like only one thing that we're looking at. And we have kernel here. And this guy in here is going to now read in an optional argument, which is going to be a equals 1. Okay, so we have ftest. Everything should work just fine. So let's run Julia, and let's go ahead and include test2.jl. Okay, so then what I'm going to do is I'm just going to run the ftest kernel on an input just to see what happens. So we're going to say zeros of 10, sure, sorry, input is going to be equal to that. Let me make this huge so people can see what we're doing. Huge here. Okay, and then we're just going to read that into the kernel. So we should be able to do ftest exclamation mark of a, and this should in principle, input, and this should change all the input. Wait, what's going on? Oh, I'm dumb. There we go. Write this. Over here, we're going to control D, Julia, include, and do this one more time. Create the input again, which is just going to be zeros, and then we're just going to basically set them all equal to 1 and make sure it works. So now we're going to do input is going to be equal to 10 zeros, and now we're going to do f test of input. And if we look at the input vector, it should have changed, but it didn't. Maybe because we didn't wait on it. Let's look at input again. Okay, why are we not changing? A is equal to 1. We read the input in. It's the size of input 1. Size of input 1 is 10. Okay, so what's your deal, dog? Why are you not running? Let me change this just to be 1 instead of A. Okay, so now we're going to do include one more time. Now we're going to try ftest here of the input. Okay, now let's take a look at the input again. Okay, so now they're all 1s. So now if I change this to an A, and I set A equals 10 or something, and then we re-include it, and then we take a look at the ftest, and we take a look at the input. Okay, so now it's working. I don't know why it wasn't working before, but fine, whatever, it's working now. So what I want to do now is I want to do the wait function. Where were we? It was wait here. Okay. Then I want to change this to maybe 12, and then we're going to include it again. We're going to wait on ftest. We're going to look at the input. This should be all 12s. Perfect. And now what I want to do is read into ftest an optional argument, which is going to be a is equal to 15. That worked. Okay. So let me try the num cores. Equals 12. Okay. All this seems to work just fine. So I don't know what was going on yesterday. So let's take a look at input. Oh, interesting. Interesting. Oh, that's probably because we're not running the kernel here configured correctly. All right, let's reconfigure the kernel then. So it takes in an ND range. I see, that could be part of the problem. So let's do this, put it in the optional arguments here, a equals a, see what this does. So we're gonna run include one more time. And now we're gonna do wait here, so that one fails. No method matching kernel abstractions, blah, blah, blah. Okay, so this makes sense to some extent. Let me try changing this here. I need a comma at least. So now we're going to include again, and now we're going to do wait here. Got unsupported keyword A. No method matching kernel abstractions, kernel. Okay, so something is happening such that we don't allow for optional arguments appropriately. Now, what I'm going to do is a couple things. One, I'm going to look at the kernel abstractions code base just to see if anyone else has an issue with this. And then two, what I'm going to do is try to find a way around this. Now, one obvious way around this is just to make it so, we just don't have optional arguments on this kernel in here. But yeah, look, the problem here is that, yeah, maybe that's fine. Maybe we just don't have optional arguments in the kernel. So if I specifically say a is equal to, if I specifically do just a, read a in here, and then we just have a in as an argument here, and we just don't have the optional argument, that's probably fine. Here, and then we just do this. So the optional argument is on the configuration level instead of the actual kernel level, then this should work. So if I look at input, we should have 17s. Yeah, and if I change this again, so we do wait on, I don't know, let's do 23, and then we do the input again. Okay, so let's just have the configuration, let's just have it so the actual kernel running does not have an optional argument in it. It's only the, it is only the configuration that has that optional argument. Okay, cool. So we can modify that fairly easily. The other thing I want to do is see about inlining functions here. So I want to see if I can read in function pointers and stuff like that. I think that's number 2. Yeah, function pointers. Okay. So the other issue here is that I kind of wanted to just use the gravity function. That's what I wanted to do. Just use this gravity function that I've already created. But I wasn't able to do that because the gravity function that I created for some reason wouldn't inline properly into the kernel abstractions kernel. So that's kind of something we need to fix, you know? So that's what we're going to work on next. Again, just go into our test, see if we can just create a function, inline it, and see how that works. So I'm going to go in here and we're going to create a new function, which we're going to call, what do I call it? +1? Sure. Reads in some value. Now, I don't think we can return anything, but let's just see how this goes. So I think one issue could be, let's just do +1 of a, and this is just going to return a +1. That's all it's going to do. And here, so what we want is input TID is going to be equal to, +1 of input TID. Okay. I'm fairly confident this is going to break, but I'm just trying it just to make sure. Include test2. +1 after end of expression. Wait, what? Extra token +1 at the end of expression. Extra syntax, extra token +1. Where is this coming from? Line 6. Function. I misspelled function. Include. Okay, so this seemed to work. So let's go ahead and run the last wait event here. And now let me take a look at input. Is it working? Oh, it seems to work. Perfect. Good. So this seems to work just fine. So next thing I want to do is read in F. And this is actually going to be F here. And we're going to create a new function that's just +2. Maybe +2, a +2. And in here, we're going to make it so the optional argument is +1, +1. Okay. And in principle, this should do it. Except we want to make it so it's now F is equal to +1. And we want to make it so this guy is now an F. Okay, let's write that. Let's go ahead and include one more time. And now we have that included, so let's see what we can do. So we've got that included, and we should just be able to run, let's see, we should be able to run the wait event one more time. 1 second, wait here. And this is going to be F is going to be equal to +1. Okay, let's take a look at the input. Perfect. Now we're going to modify it so it's +2. And we're going to look at the input. Okay, so everything seems to be working just fine. Perfect. Okay, so now we just have to incorporate that into our code and see what happens. Raise this down a little bit, something like that maybe. Okay, good. Yeah, okay, that's fine. Okay, good. So it looks like we can do what we want to do, which is perfect. Now all we have to do is just kind of put it into the Galilee code and see if we can write the code in a more extensible way. So how are we going to do this? So right now this kernel function here must just read force law in directly. Force law. Okay, dd here. And then what we want is to basically replace all of this stuff in here with just force law. So that's what we want to do. We have to think about exactly how we're going to do that, but it should be okay. So we have gravity in here. And so that's going to become our force law. So where's n body? N body is, where are we? Gravity here. Here's n body. So we're going to replace that with force law, because that's a kernel. And then we want to find acceleration. Where's n body being called? Oh, it should be called in sim type. It's called in sim type. Oh, I see. So here we're going to read in the force law directly after temp acceleration. Good. Okay. So now we should be able to read it in. So this should all work just fine. Let's go ahead and check it out. Julia -- project. Using revise, misspelled revise. Let's try it again. There we go. Perfect. And then we're just going to do using CUDA Galilee. And then we're just going to run it really quick just to make sure we get decent results. And yeah, go from there. I hope everyone's having a wonderful day. Feel free to talk about what's going on. And yeah, again, we'll be here for another, I don't know, maybe 5 hours doing stuff. So if you want to take a break, come back later, that's also fine. If you have any questions about, anything, whether it be the stuff that we're doing immediately here or other stuff like maybe academia stuff, like, the publication economy or anything like that, feel free to ask. I mean, I know I tend to do rants and stuff, but I don't know. That's kind of part of the fun of streaming, doing a whole bunch of like rambles about this and that. Yeah, just let me know what you guys think, and I'll address it as soon as I see it in chat. I hope everyone's having a great day. I hope if you happen to be from the US, which I doubt you are because it's quite early, but I hope you had a good holiday yesterday. I know it's Black Friday, so maybe a lot of people are going out and buying, I don't know, whatever. I hope that's going well, all that kind of stuff. Apart from the fact that I'm tired, I'm good. Good. Happy to hear that. Man, I cannot tell if it's getting warm or not. I'm still kind of sniffling a little bit. I'll check the thermostat when I go back upstairs in like an hour or two on the next break. But man, I am cold. Can you guys hear that when I'm doing this? Okay, you can't. I'm like doing this with my hands because I'm like kind of hot or kind of cold, and I'm like trying to warm myself up. I don't know, like I'm so cheap. I don't want to use the heater, but at the same time, so let's run Galilee.run. cuArray should all run just fine. So this should give us a some sort of. I'm running a 5-dimensional simulation. All right, I don't want to run a 5-dimensional simulation, but I'm apparently running a 5-dimensional simulation. So we're just going to let it do its thing. Okay. I don't know why I decided to run a 5-dimensional simulation. That's so stupid. Yeah, that's so stupid. All right, let me run it again, but with 2 dimensions. Let's go ahead and remove this guy. 3 dimensions is also fine. Let's do 3D. All right, we'll run that and we'll check the results. CD back into aux, and now we should be able to run the last GNU plot command, and this should be 256 particles, and we just should see all the particles just coming in and kind of doing the thing that you see in the upper left-hand corner, just with a few more particles involved. It's also going to be a different color, but who cares? All right, give it a second. This is one of the big problems and why I definitely want to work on visualization a bit, because doing these visuals just takes a while for GNU plot, and it wouldn't take that long if it is like some other plotter, Okay, so let's go and do Mirage here. Okay, so here we have I plotted them in 2D when I need to plot them in 3D. Try it again. I'm in waiting mode, so I basically can't do anything though. Wait, you're in waiting mode because of what? Like, do you have something big going on? I mean, you don't have to answer if you don't want to, but, or if you're waiting on a PR, that's that's totally on me. Sorry about that. Okay, give it a second, let it finish running. There we go. Now let's take a look at Mirage. Okay, so these are 3D cloud. And give it just 1 second. Okay, good. They're all coming in. They're all exploding. Oh, I like that visual. It's quite nice. Maybe I should just redo the visuals we have in the corner. This one looks so much nicer. Doesn't it? They kind of look the same. Yeah, they look the same. I like the visuals, though. They're quite nice. Yeah, okay. So let's go ahead and close that. Let's clear here. So everything's working. Just for the record, everything's working right now. It's not on you. One cause is the x64 assembly PR. Yeah, so the x60, I didn't even know what to do about that one because I don't know how to, I don't know how to like build anything in x64 assembly. So I'm actually even not sure, like, I don't even know how to approach it, you know? But on the other hand, I'm glad that, you know, it's being worked on and that it seems like it's basically done. I mean, I don't know how much more is left on it, you know? Let's go into VI source, forces.jl. Okay, so the first thing I want to do is basically replace all of this section in here with the gravity function in here. So I want to just replace all of this with this. This should be fine, but we'll see how this goes. So right now, how is this going to go? So when we look at this, in principle, we should be able to read in the two different positions. We get the R2 here. So can we just read in? Here's my stupid, super naive question. Can we just read in the following? Can I just take this guy, literally right here, and just pop it up into this guy in here, and then just use this? I'm going to comment this guy out down here, because we might still need that. Here we go there, and let's see what we can do. 8. There we go. You can do assembly in Julia. No. So the assembly is for the algorithm archive, where we have multiple different languages. You can look at LLVM in Julia, but you can't do assembly directly, I don't think. Basically, it's waiting for Peanut Butter Warrior to see if it compiles correctly on Windows. Right, I remember that conversation. Okay, so what I want to do now is modify it so I guess we just have positions. Size of position. All this is positions, right? No, we have temp acceleration. We have temp acceleration. So we need to read in the temporary acceleration? No. What do we need to read in? Where is temp acceleration defined? It is defined. Oh, it's read in. It is read in as all zeros. Right. Perfect. So this particular function then needs to read in a set of positions and a set of accelerations, I believe. So this guy can just be, in fact, I can create a separate, this guy can be positions. And so we're going to read in positions. Wait a minute, what's going on here? Positions, we only have one position vector? I guess that's fine. Oh, we have to read in the entire positions vector. Oh, and then that means we also have to read in a TID. It means we also have to read in the TID. Okay, let's just see what happens. So we're going to try reading this in. We just need to read in positions, TID, and K. And let's see if this works. Positions, TID, K, and then I think we also need temp acceleration. Okay, so in principle, this should just run. And let's see what happens. So we're going to do gravity in here. I'm just going to comment all of this out instead of deleting it outright. Let's go here and where? Here, I believe. Okay, and then we're just going to run the force law. And it's just, right now we're going to read in positions, temp acceleration, TID, just TID is all I need because K is actually defined in here. Yeah, so I don't need K. Okay. What's R2 used for? R2 is here. Okay, so R2 is used for a temporary calculation. In principle, that should run. So let's go over here and try it again. And see what happens. Worst case scenario breaks and we have to fix it. I don't like this implementation so much. There's some things I don't like about it. But it seems to run okay. So this at least allows it to be a little bit more extensible so we could, plop in some different force laws later if we need to. We need to figure out how like args ... stuff works and all that, how we can splat arguments, all this. But okay, let's just go ahead and check here. So we're going to run GNU plot and just make sure that it actually outputs the correct results. So this should just create the same visualization we just generated. It should all just kind of come together and all this kind of stuff. So we'll see. It's basically the 3D visual that you're seeing right now in the upper left. Echo. Are you hearing an echo? I don't know where that would be coming from. Is anybody else hearing an echo? Let me see. Maybe the stream is. Yeah, I don't know where an echo would be coming from. Is anybody else on stream hearing an echo? The only thing I could think of was maybe my audio was somehow playing somewhere else or something. But I'm looking at the audio inputs. It doesn't look like anything. Here, I can just show this over here. Greetings and no echo. Hey, Warrior Giggles, how are you? So 2 people say there isn't an echo. Hector, if there is an echo, I don't know what to do about that. I don't know how to fix that. I'm so sorry. But if you have any advice, I'd be happy to look into it. So we should see all the particles come together. Give it a second. And perfect. Okay. No echo. Okay. So most people are saying no echo. So it seems fine, probably, but we'll see. I can look at the audio afterwards as well, and see if anything's happening. I guess, okay. So the other thing is, maybe there's like background music that kind of sounded like an echo or something. I have some rather light background music, I think, going on right now, but depending on the song, it kind of is louder or quieter. I need to find a way to better normalize the background music, actually. Okay, this visualization looks pretty good, I think. So for 3D, I think it's fine. Good. Okay. I think we got that working. So let's go into forces.jl. Let's go ahead and delete this in here for now. I don't like the fact that we have to unroll this, but it's probably fine. And then let's go here and delete this guy. Here. Okay, now what about the temp acceleration in here? I don't think we need that anymore. So this really made the code a lot simpler. Okay, now there's a lot of little things that we need to do, but slowly getting there. Slowly but surely getting there. Let's go ahead and right quit, and let's go ahead and add that change. It's not a big change, but it's something I want to add in. Oh, there was something else I wanted to add in. So we have kernel n body. So now we should be able to change the force law if we want. So let me just check to make sure this is actually working. We're actually going to create a new function, which is just going to be called repulsive. Not like repulsive as in like ugly, repulsive as in like the opposite of gravity. So gravity attracts everything, repulsive like pushes everything away. So we're just going to generate that function, and we're going to switch the simulation out to make sure that this function pointer is actually working as intended. Let's paste that here, dd there, and let's go. TMPOR, thank you so much for following, really appreciate it. So here we're basically going to add in a positive value. Let's go here, Galilei.run, and what I want to do is read in an optional argument here, which is going to be force law is going to be equal to gravity. Just make sure that runs. Gravity not defined. Gravity. Oh, Galilei.gravity. So probably Galilei.gravity. Come on. Okay, that should run. Give it a second. Good. So now we're going to try the same with, oh, I called gravity twice. Oops. I need to change it to repulsive. Repel, maybe? What is it called? Like, it's not, what is the repulsive one called? Chicken Boy, thank you also for following. What is it called when you repel things? It's the Coulomb law? For like charges? Whatever, we're going to say repulsive, and that's just what I'm going to call it. And you guys are just going to have to deal with it. All right, give it a second, and we should get a phenomenally different visual, which is the particles fly away. That's what we're looking for. So let's go here, run GNU plot. What programming language is this? This programming language is called Julia. So it's relatively fast. Roughly the same speed as C, like within a factor of 2 of C. It's predominantly used for high-performance computing. It boasts of being as easy to write as Python, but as quick as C. That's kind of its goal. It may or may not hit that depending on who you ask. But again, it's mainly meant for numerical calculations and stuff. Okay, so if this worked, these should run away from each other. They should just run away. It didn't work. Oops. Well, okay. All right. Let's try it again. I'm going to run it again. Let's go using revise, because there might have been an issue with, there might have been some other issue that I didn't notice. So now we're going to do, where are we here? Oh, I forgot to remove the old data file. That might have been it. So that was probably what broke. Okay, so now we're going to do using CUDA Galilei. We got to figure out how to deal with the data file stuff. I need to create a specific IO function for this. Yeah, so let's do that next. Let's deal with the IO after this is done. So now we're going to try running it again. So we should just be able to run Galilei.run with the repulsive interaction. And this time, because we erased the old data file, we should just see the particles run away from each other. That's what we're looking for. Hopefully, it works. Please. Sometimes it's like one of those things where I feel like I'm begging with the compiler to work correctly, but it doesn't. It broke. Crap. How did it break at this stage, though? This is dynamic function invocation. So let me try this again without this being added in. There. That also broke. Really? But you were just working. Literally just working. Ah, crap. That means that revise is not working as I thought it would. Crap. Okay, so what do we do in this case? So unsupported dynamic function invocation call. Is there something wrong with this? Maybe there's like an at inline issue. I mean, I know what the problem is. I know exactly what the line is that's broken. Let's go here. This is a problem. So I'm using a package called revise. So supposedly what revise allows me to do is change the source code of a package that I'm working on, which I'm currently working on, and then have the compilation kind of work dynamically so that, you know, I don't have to continually like open Julia up and down again. So I don't have to go through the precompile steps. Like I only go through like the little bit at the end, you know? But revise doesn't really work for GPU kernels. So what I might have just done is just break all the code. Which is fine. Let me try changing this, so instead of saying force law, it just directly says gravity. Let's go here, comment that out. Let's go here, and now we're gonna run this guy. So this one runs. It runs, no, it doesn't run. It broke. It broke as well. Everything's broken, which is fine. Crap. But if I just directly, let's comment everything out. Okay, so let's Control D, Julia, run using CUDA Galilee again, and just run this code. Nothing should break. It's not going to produce any results at all, but nothing should break. And then I'm going to try the first line with gravity and the second line with force law, see what's actually broken. I'm pretty sure this is going to run. It should not break. If it does break, then we're going to be in trouble. It's fine. I can always go back to the last commit, but you know, like that's you know, that's quitter's talk, you know? All right, let me get some water. Okay, so that ran. So the next thing I'm going to try is just calling gravity directly here. Okay, Control D, Julia, using CUDA Galilee, and then we're going to try it one more time, just calling gravity directly. And then we have to figure out how to read in function pointers. No, we have the function pointers already being read in. I just tested that over here. I just tested that. So why is it breaking? All right, let's try running this. Maybe it has to do with the function itself being too complicated to... Maybe it has to do with the function itself being too complicated to, like, inline, maybe? I mean, that could be it. My guess then is that this function is too complicated to inline. How do I fix that? It could be... So here's what I'm going to do. I'm actually going to go to this +1 guy. And let's try creating a new function in here. And the new function that we're going to read in is function... Okay, how are we going to do this? So what I did here is created a very simple, like, I read in a function, I called the function here in the kernel, and then I ran +1 and +2. Now what we're running into over here is that the function here is just maybe slightly too complicated. So let me try making the function a little less complicated and see if this runs, for example. Because the problem could be in the function arguments, not in the function itself. So we're going to do Control D, Julia, CUDA, Galilee, and go from there. Your function is recursive. It shouldn't be recursive. Yeah, I don't think it's recursive. It's not like I mean, there could have been a typo. I'm not seeing the typo right now. But oh, I see. So maybe yeah. So a dynamic function call could mean that you're calling a recursive function. That's what you would expect with C or C++. Okay, give this a second to run. Literally, the only thing we're doing here, it looked like it was calling itself. Okay, so that one actually runs. Okay, so let me see if the next set of lines runs here. Control D, Julia, using CUDA. I mean, maybe, let me see. I'm not seeing. It looked that it was calling itself. Yeah, let me see. Okay, so now we're gonna run this again. I don't expect recursive functions to parallelize well. No, recursive functions don't parallelize well. You don't want to run recursive functions on the GPU. It's just that this isn't recursive. So that's why I think it should be fine, you know? So it used to be like a long time ago, you couldn't even run recursive stuff on the GPU. Like nowadays they let you, but it's kind of like strongly discouraged. And the recursive depth is like way lower than it normally is. So like, for example, if you want to do an AST solve or something like that on the GPU, you definitely don't want to use a recursive version. You want to use a stack-based method, you know? Okay. So it doesn't like this guy, and it doesn't like this guy because I'm not sure. It doesn't like this guy because maybe it doesn't like accessing something with a TID. So let's do @print. Oh, I don't know if this is actually going to work or not, but let's try. So @print positions of TID 1 or something, and then we're going to give it a new line. Let's go over here. Sorry, I'm going to have to open and close Julia again. Here we go. I'm not sure if it's the accessing pattern that's not like working. So let's check that out. Yeah, and obviously the error message is just completely unhelpful here. It won't even give me a line number that's broken. It will just give me a general error to look at. This is one of the big problems with kernel abstractions. The error messages are just genuinely inscrutable. Like inscrutable, is that the word I'm looking for? Basically just useless is what they are. Okay, so we are able to print the TID, which is fine. We are printing too much. Let's see if I can Control C out of here, Control D. Okay, could be the for loop then. So let's go ahead and try that. Paste. Okay, Julia _ project. I don't understand. Is it the call to size of positions that it doesn't like? Let's go here to CUDA. Yeah, I'll go back in just a second. Let me just run this. Give it a second. Here. So what were you talking about? Sorry, I didn't read this. So the ftest function here, we'll just call the function f. So we have kernel here. It's reading f in as a function pointer. Here as a function pointer. Then it's just saying input of TID is f of input of TID. So it's literally just, you know, we either use +1 or +2. That's all it was. It was a very simple function. So there isn't really, I don't think there's too much more to really be gained here. We can look at it more in a second, but I'm just showing it on screen. Okay, so that ran. So let me see, what else could there be? Let me try modifying this so it's just R2 plus equals 1. Otherwise, there's something wrong with this calculation here, which is fine. Okay, so let's go here, Control D, Julia _ project using CUDA, and let's just kind of keep working on it one step at a time. See where we can go. Yeah, again, if you guys have anything in particular, you know, you want to look at, just again, let me know, and I'll take a look at it as well. So I think today's going to be a lot of debugging, just kind of messing around with the code, trying to get it to work, all this kind of stuff. So yeah, we'll just see. We'll see how it goes. If you guys have any questions, comments, concerns, ideas, anything like that, just feel free to let me know. I'm going to take a look at the error message in a bit more detail in just a second. Okay, so that also works just fine. We know we can access positions TID and K. We just tried that. So what's the problem? This line is broken. Why is that line broken? Is positions of TID and K minus positions J, K. Oh, we don't have J. Okay, that's it. Oh, well, that was a waste of, what, 10, 20 minutes? That's fine. Again, I don't think this is the best way to write this. I think there's probably better ways to write it, but this should at least run. Please. Come on, just run, please. I think the next thing I want to do, the compiler did complain about J, but it was in the middle of an error message and I just didn't look at it. That was my fault. I'll show the error message in just a second, once this is finished running. Okay, so that run, so the error message, okay. The error message is not visible, but the error message was like said invalid dynamic function invocation call. That was the error message. It didn't say J was missing. It said that this function was wrong. So that was the issue. It wasn't, I mean, I think I probably could have dug into the error message a bit, but it was like a 200 line error message. Like, again, that's one of the big problems with kernel abstractions. It's just kind of a bit hard to, it's just a bit hard to use, for that kind of stuff. So we're going to read in J here as well. Write this, go over here, Control D, Julia _ project. The error message was awful, like genuinely awful. Let's try it one more time using CUDA Galilee, check to make sure the results are what we expect, and then we're going to try the repulsive interaction and see if that worked as well. So let me get some water. And let's just give it a go. So let's do Galilee.run. I also think I want to run this one more time with an @time in front of it. And what I want to do is I want to @time, maybe for like 4,000 particles, I want to @time the CPU version in this current version with the function pointer and without the function pointer and see if there's a difference, really. Crap. What happened? Down here, we must have screwed up. We have JK, TIDK. So this line is now broken. What is this line broken for? That was a problem with C++ as well. The error messages were awful, at least before the redesign of the GCC compiler. I gotta say, the new GCC compiler error messages are actually quite nice. Like, it went from me being like, I don't really understand what any of this is, to me being like, oh, actually, the error messages here are top notch. Like, probably some of the best error messages I've ever seen. Okay, so this is broken. I'm not entirely sure why it's broken. I'm gonna take a look at the error message, see if it gives me anything. It says JL get field is broken. Okay, let's just, I don't know, let's just, so it was working when these were commented out, so let's just comment them out again. And let's just run it a few more times, see if we can figure out exactly what line is broken. I could just do a bunch of print lines, but we know it's one of these two lines. It's saying get field is broken. Yeah, so that must be like this guy is broken or something. But we have J and K, we have TID and K, because we're reading K. Oh, that's why. I got it. This should be size of positions. There. And then here we go to size of positions as well up here. Perfect. We figured it out. Okay, let's comment these guys back in. Again, I'm not saying this is good code. It's actually really not good code, but that's okay. So we're going to do using CUDA Galilee, and then we're going to run it one more time. And what I'm expecting is just to basically recreate that 3D simulation you see in the upper left-hand corner. Yeah, and that has taken a lot of work by programmers and programmers who produce good error messages. That wasn't the case in the old version. Right, so, I mean, the developer of kernel abstractions is like one of my best friends. I've spoken to him a lot about the error messages. And look, it is a complicated issue. It's not something that you can just fix. The big problem with error messages in specifically kernel abstractions is that, you know, first of all, you're running on heterogeneous architecture, right? You don't know if you're running on the CPU or GPU. But specifically, if you're running on the GPU, you're going to run into a whole bunch of issues where, like, you might be in the middle of kernel execution and you're just not at the right scope where you can actually output to your error log or something like this. Like, there's just a bunch of things that could break. And the Julia compilation infrastructure is like, you know, it kind of mixes, the Julia compilation infrastructure mixes like runtime and all this kind of stuff. So there's also a bunch of other errors that could pop up. Basically, it's a complicated problem. And like, the more he delved into it, the less I understood about how hard the problem was. Like, it was one of those things that the more he spoke about it, the more I realized that I just genuinely don't even understand why the problem is a problem to begin with. It's just, like, it was so deep that I wouldn't be able to understand it, no matter how deep he would go, type of thing, is what I'm trying to say. But that said, you know, that's why he's working on that, and I'm working on ND Galaxy simulations, because ND Galaxy simulations are way easier than error messages. So, It's one of those things, when you talk to a lot of physicists, they take the software for granted. They take a lot of things for granted. They're like, how hard could it be? Like, that's a software engineer's job, or that's I don't know, like, you just see people, they often will be like, oh, that's the job for this person. And they act like this person is like an underling of some sort. Like, they act like it's actually a very easy problem to solve and all this kind of stuff. So they should all come in. All right, perfect. Nice visualization there. I like that. But that's really not the case. Like, almost all of the jobs that you see, physicists saying are trivial are like, they're usually not trivial at all. They're usually very, very complicated. I don't know. I'm kind of rambling here. I end up rambling a lot, but anyway, that visualization looks good. So let's try to change the force into a repulsive force. So we're going to say force law is going to be equal to probably Galilei.repulsive. Let's try running that. And they should see the opposite effect. We should just see all the particles flying out. I need to remove this guy. See it one more time. And then we should be able to run it in GNU plot and see what happens. So we're going to run GNU plot. And again, we should just see all the particles fly away. That's it. That's all we should see. And hopefully works okay. Give it a second to do its plotting. And then what I want to do is some quick just timings, not benchmarks, just timings of what it is now with the dynamic force law or whatever, and what it was before we had the dynamic force law. So let's go ahead and take a look at Mirage. Okay, so again, if this worked, this is now a repulsive force. Like basically, you could imagine them all as charged particles of the same charge, so they're all forcing each other away, and it didn't work. Yeah, this is definitely not what I was expecting. Okay. Right. So what's the issue then? Let's go here to source forces. Good news. Good news. We can read in. Let me go ahead and see what I can do here. So I can do code lowered for the force.repulsive, maybe at edit. We have positions, temp, acceleration, TIDJ. They're basically the same function. The only difference is that one of them has a negative sign on this line at the very bottom here, and the other has no negative sign there. But that's the difference between a repulsive and an attractive interaction. Okay. I have no idea what to fix. I don't even know how to approach this. So we're reading in force law there. And here we say force law is equal to gravity by default. I think I see the problem. So now we're going to go into, where is it? Simulation. Here. And then what we want to do is wait, array type, and then I also want to read in, I think I can do it this way. Force law is going to be equal to, I think I can just read in as force law. Okay, let's try this. Go over here, Control D, Julia, double dash project, using Galilei and everything like that. Perfect, and we're gonna run it one more time. Have you seen the last video by Veritasium? I found it interesting because that was typically the kind of thing I should have known but didn't understand correctly. Are you talking about the, wait, actually, no, I don't know which one you're talking about. The last one I saw from Veritasium, I actually found incredibly confusing. Like, literally, like, the most confusing video I think he could have put up for this topic. And it was on the circuits and stuff like that. I just thought it was super confusing. I was like, dude, like, you could have described this in 2 minutes, and you ended up taking 20 minutes, and you made everyone confused. But that could just be, like, me not, like, with that in mind, everyone kind of interprets things differently. And so if it worked for you, I'm actually super happy to hear that, on the energy transported by the EM field. Yeah, I think we're talking about the same one. And like that one was super, like, I had no idea what he was talking about, like, all the time until I took a second. I was like, okay, like, you literally could have just said this and that, and it would have been way easier. But I gotta be honest, like, I genuinely can't follow Veritasium videos at all. Like, I mean, I've mentioned this before. Like, I'm very, very bad at following video content. Like, I 100% cannot understand anything if you give it to me in a video form. Twitch streams are different because they're conversational, you ask questions, all this kind of stuff. But like, if you give it to me in a YouTube video, I'm not gonna be able to understand it. It's just not gonna work for me. So Veritasium is like an extra layer of just, still going in. It's just an extra layer of me just not, I'm just not gonna be able to follow it, I didn't get that video, gave up halfway through the video. Yeah, I don't know. But on the other hand, like I also acknowledge that I just don't have the attention span for video content. So for me, it's very clear that people teaching people. It's very clear that video is not a form of education for me. It's the same as lectures are not a form of education for me. Like it's just not a form in which I can consume educational content. And with that in mind, I recognize that Veritasium is probably one of the best educators on YouTube. I think his videos are the cleanest, the highest produced. I think in general, even though that one I didn't fully understand, most of the scripts are very well written. So for people who are in the game of learning stuff on YouTube, Veritasium is probably like number one, followed by 3 Blue 1 Brown. I probably put 3 Blue 1 Brown second only because I know his content is a bit more niche in that it's more like specifically for mathematicians. Okay, basically he demonstrated that the electrical energy is transported by EM field generated by electrons and not by the electrons themselves. Right, yeah, I mean, yeah, I don't know. He kind of said that. I don't know if he demonstrated it. Okay, so we have the force law here is reading in as gravity. So then we're also reading the force law in, so we're doing function.run. So the force law down here is going to be force law is equal to force law. Great. Let's go here. Oh, that's not what I meant to do. So let's go into source and forces. Sorry. Forces.jl. And we should just be reading find acceleration. They should have force law of gravity right there. And then the kernel should be force law here. Let me try just directly. Oh, I'm an idiot. I can't believe I did that. I'm so stupid. Okay, let's go here. Control D, Julia. Remove this guy. Using this guy and try running it one more time. Let's see. Basically demonstrated that, okay. I felt that specific Veritasium video was kind of misleading in how it explained the circuit and circuit representation in the beginning ending of the video. Yeah, I think so as well. Anyway, let's go ahead and run this. There's also Mathologer, who is amazing because he touches rather difficult problems. Yeah, so like that's the truth, right? Like there's so many good educators on YouTube nowadays. Like, you know, there's Mathologer, there's 3 Blue 1 Brown, Veritasium, there's Smarter Every Day, and those are like the old folks. And then you've got like new people coming in. You've got like, dang, that didn't work. You've got, you know, like Reducible, who's quite good. You've got, I don't know, you just have a whole bunch of people who are making really good educational content now. Flammable Maths is another one that people really like. I also really like their content. There's a lot of people out there making really good content nowadays. And I don't know, I just feel like, you know, if you're looking for education on, if you're looking for educational content, like I just feel like you're going to be able to find it. Let me try changing this so it's just repulsive instead of force law. Just to make sure the function is actually working. Write this, go over here, Control C, Control D, Julia, using, and try it one more time. It's pretty similar to the gravitational energy is transported by gravitational waves, aka movement of gravitational fields. Right, it's just, I don't know, like the thing that got me about the latest video was like, you know, like, I don't know. I can't really talk about it too much more because if I'm honest, like, I know my biases here, and like I'm pretty sure the video was actually quite good for a lot of people. Like I'm sure a lot of people learned a lot from that video. I just wasn't that person, but also I can't learn anything from video content. I'm not someone who can learn from videos and lectures. So, you know, it's kind of, what am I supposed to do about that? There was a failure here because of a dynamic function invocation call to repulsive, which says to me that I failed somewhere in here. Positions, temp acceleration, TID, and J. So we have positions, TID, K, positions, J, K, that works. I'm not exactly sure what I did wrong. Let me try commenting all of this out and seeing if it just works this way. Okay, we're gonna do Control D, Julia -- project, and then we're gonna try using CUDA and Galilee and try running it one more time. Reducible is their name. I'm kind of 50-50 on Reducible's content. So the problem is like when I make content, sometimes I talk about algorithms on my YouTube videos. A lot of times I talk about algorithms on my YouTube videos. This has kind of been my shtick for the past few years, kind of. So reducible is basically 3 blue, 1 brown. Reducible. It's basically 3 blue, 1 brown. Let's go to YouTube. But on algorithms, right? And the thing that gets me is that, like, I gotta be honest, in the same way that I don't particularly follow 3 blue, 1 browns content, I don't particularly follow reducibles content. And so it's kind of like, it's in that same vibe of stuff on YouTube that makes it feel like you're learning, or rather, okay, for me, it makes me feel like I'm learning without actually learning something. And it's the same thing that's true for, like, 3 blue and brown, where it sometimes feels like I'm learning something without actually learning it, right? And the same is true for Veritasium. It feels like I'm learning something without actually learning something. This happens a lot with these types of people that I don't particularly watch. Like, they're good. They're like, I know they're good, but it's just I can't follow their logic, right? And so what happens with Reducible, and also what happens with a lot of the other educational content creators who make very long or somewhat longer educational videos, I just can't follow it. I just don't understand what's happening. Like, it makes it feel like I should follow, and then I'm like, I don't understand what you're saying. All of a sudden, it's just all gobbledygook. And like, I know if they would have just given me a paper, I would have been able to understand it. Or if they would have just given me, a textbook, I would have been able to understand it. But the fact that it's in video form, it just kind of makes it hard to follow for me. And so because of that, it ends up turning into this thing where, like, a lot of times Reducible, he'll make a video and I'm like, I just don't understand why you didn't, like, why this video is 20 minutes. Why didn't you just do it in 2 minutes? It would have been so much more understandable. And then, like, he does super well. People are like, I really like this content. So the thing that the reason I'm kind of like 50-50 on Reducible's content isn't that he's making bad content. The content is genuinely good, in the same way that 3 blue and brown's content is genuinely good. It's just that channel made me think of something that I hadn't thought of before, in that when I had been making YouTube content, I had always made it for people like me who can't really follow the longer videos, so you make shorter videos, so that, you basically give the intuition, and you assume that there's stuff that people already know coming into things and all this kind of stuff, and these are the videos that I prefer, because they're like less than 5 minutes, and I have the attention span to follow the entire video. But it made me realize that that's just not what people want. People actually do want the longer videos that I don't like. The longer videos that I don't appreciate as much is what I should say. Because again, they're good content. It's just they're good content for other people. And so with that in mind, it's kind of like, I don't know, the reason I'm kind of 50-50 on Reducible isn't that he makes bad content. Again, the content's great. It's that, like, it just made me realize what YouTube was. And it's kind of frustrating in a way. Let's see. It's pretty similar to gravitational energy. Let's see, you got a point there. The new YouTuber is Reducible. How do we report Leos? Whatever, you can just report me, it's fine. Confiscate his papers until he likes watching videos. That's never going to happen. Like, the amount of joy I get from reading papers, let's call it 50, right? Like, on a scale from 1 to 10, let's say the amount of joy I get from reading a paper is about 5 out of 10, right? The amount of joy I get from watching YouTube videos is like 0.1 out of 10. Like, it's so much lower. Like, it's so much less. It's kind of impossible to get anywhere near the entertainment value out of any video form. Now, again, Twitch streams I actually do kind of enjoy. I don't know why, but the interactive nature of Twitch streams make them quite enjoyable for me. Specifically, like, Kitboga I really like, Pokuri Mio I really like. A lot of the Lana, I'll like lurk in her stream all the time. I don't usually chat in her stream because she's so interactive. When she sees me in chat, she like shouts out my channel, and I kind of don't like that, so I end up just lurking in her channel. And there's a few other people that I end up lurking in, but I very much enjoy because of how interactive they are. But just something about YouTube, just kind of, I don't understand YouTube as a platform, I guess is the truth. And I think the watching Reducible's content, watching 3 blue and brown's content made me realize I understand even less of YouTube than I thought I did. Again, I'm still going to use it, and I'm going to do my darndest to make sure that this upcoming year we make YouTube content that people actually like. We make Twitch content that people actually like. And let's go. You watch Pokemio? Pokemio N? I don't know who that is. The one that I was talking about was Pokurimio. Sorry. Let's just go here. Pokurimio is the one that I usually watch on Twitch. Wait, did that actually... Oh, that didn't post for some reason. I don't know why. But Pokurimio. Here. Yeah, so that's the one I usually watch. She's quite good. I really enjoy her content. She's just an art streamer. That's all it is. let's see, what do we have here? Oh, I must have pressed page up. That's what happened. Let's go down. There we go. Yeah, I guess maybe because I lived in Japan for so long, it's not so hard. Poku de mio, it's actually pretty easy. But also, I'm very used to Japanese stuff because my wife is Japanese, and I have to speak Japanese every now and again to her family. So you can only learn by practicing. They can help understand stuff, but you didn't understand even though you learned it. He has to do it in 20 minutes because else there will be 14,000 comments giving arguments as to why he's wrong. So he has to address as many as possible. That's probably true. That's one. Japanese stare. I mean, I don't know what else to say there. But what I was going to say is that, I don't know, like this is my core problem with YouTube is that I just don't understand it. And so like whenever I start talking about people who make content, I end up accidentally being super negative about it, like you just saw. Like I end up being like, yeah, like they make good content, but, and there's always a big but, and I'm always like, like I just don't understand this or that, because whenever you make videos, you're always constantly compared to other people who make videos. The number one comment I get on my videos is 3 blue 1 brown did this better. I get that comment all the time. In fact, for a while, I banned the word 3 blue 1 brown from my chat, from my comment section, because it was constantly people talking about 3 blue 1 brown. It's like, I'm not 3 blue 1 brown. I'm a different person. I make different content for different people. And part of that is because, I got a shout out from 3 blue 1 brown, and I work with him a lot. And I'm very grateful for his community being so open and active. And I'm doing a 4D gravity simulation as a collaboration with him. Like, obviously, he's been very open and honest and forthcoming and everything. And look, I get that. But it's just, when I end up talking about people's content, and people ask my opinion on that content, my opinion is usually quite persnickety. I'm usually like, I don't know, I don't really like this, or I don't really like that, That's kind of what always happens. I like big butt, you other brothers can't deny. Okay, that's not the direction I was going in. Okay, so let me go back down here. Let me try running the same function here with the force law, but then change the force law to gravity. So we're going to do force law. Here we go here. Let me go ahead and write. And let's do Control D, Julia double dash project using CUDA and Galilee, and run it again, except this time force the force law to be gravity, and see if that works. I don't know. Anyway, the truth is I need to stop talking about YouTube on Twitch. I really do. I mean, the more I talk about the YouTube, the more I just kind of, I don't know how to put it. I just get down, because it's, like, for example, the last video I put out was on the approximate counting algorithm. I admit, there's some things about that I probably should have done differently. But it was my most hated video on YouTube. People genuinely hated that video. And I was like, okay, look, it's called the approximate counting algorithm. I'm showing you how it works. I think it's pretty clear how it works. I don't know. Like, I was like, I don't understand what the issue is, Okay, so this is still breaking, which is not great. So let me try fixing this again, so that it's just calling gravity directly, and see if that works, because we know that worked last time. Here, dt there, gravity, and let's go ahead and comment that out. Okay, so we're gonna go over here, we're gonna do Control D, Julia double dash project using CUDA Galilee. Anyway, so after the last video, I just kind of realized that, screw it. I'm only going to put content on YouTube that's like fundamentally new, that people haven't seen before, so they can't just sit here and argue about it. It's like, hey, here's a 4D galaxy simulation. I guarantee you haven't seen this before. I guarantee it's new because we actually published a paper on something like this. Like, this is what I'm going to do with the YouTube channel. Like, just be like, hey, here's something you haven't seen before. I can guarantee you haven't seen it before. And if you dare question me about it, you can't, because I've got all of this stuff, to talk about with it. Okay, I don't know why this is breaking now. I genuinely don't know, because it was just working like 2 minutes ago, and now it's completely broken. How? How is it breaking? Oh, I'm such a complete moron. That's why it's breaking. I'm so stupid. Every single time, I'm like, this should work this time. Okay, we're going to do Control C, Control D. We're going to run Julia double dash project using CUDA Galilee. We're going to run it one more time. We're going to get it working. This is going to work. This is a Leos Labs guarantee. It's going to work. I'm not even going to look at the error message because it's going to work. I don't have to look at any error messages. We can keep going for the rest of the stream without ever looking at an error. That's how it's going to be. Oh man, I don't know. But look, here's the thing: if you enjoy educational content online, as much as we've been trying to make educational content a thing on Twitch, it hasn't been incredibly successful. Like the people who are making educational content, you've got like Kitboga, who's making some good content. You've got a lot of the like some PhD streamers who are also like doing their PhD and stuff and talking about what they're doing. And that's also quite nice. But like, it's just we don't have a bunch of educators on Twitch, but there are a bunch of educators on YouTube. And because of how difficult it is to get like, I don't know, get people involved in Twitch, like to have people find new people on Twitch, like it's basically impossible to find new streamers on Twitch at all. I don't know, like I feel like you have to go to YouTube for educational content. Like I feel like that's just what you have to do, because like there isn't a good place for you to go here. I mean, there's the software and game development channel, which is pretty nice, or category that's pretty nice. Science and tech is mostly nice, but then you have a lot of people on the top of science and tech that are just like, I don't know, it's like 24/7 earthquake monitoring and stuff like this, which is not, it's not like what you're looking for when you're thinking about educational content. Okay, so what did I just do? I ran the gravity simulation with a different force law. This force law is repulsive, so we should see, if this is working correctly, we should see all of the particles fly out of the simulation. Okay, are you ready? 3, 2, 1. It's broken. Nothing is happening. There's nothing going on. Dang it. Well, I tried. Okay, let's go here. Let me try running with gravity. See if at least gravity is working. It's probably not. Let me remove all the force laws. Try running it here. And see if at least a gravity simulation is running. Oh, boy. Okay, so now we're going to run GNU plot. I can't believe that. It didn't even work after all of that. Okay. All right, we're going to give that a second to run. And take a look at the visual. This confirms YouTube is a distraction. Well, I don't know. Is YouTube a distraction? I feel like, to be fair, I've been rambling about YouTube, but we have been actually doing stuff, Like, okay, give it a second. We should see gravity. Okay, so gravity is working. The repulsive interactions are not. So these are all kind of coming in. Perfect. So this simulation is working. Wonderful. Okay, let's go over here. Let's remove this. Now, oh, I see. Now the next thing I want to do is force law is going to be equal to Galilee.gravity. Okay, now let's see if this one runs. Here we're specifically running in the Galilee version of the gravity. So now we're going to run GNU plot one more time and see if this is what we expect it to be. I hope it is, because otherwise I have no idea what the problem is. Also, for the record, the notation is kind of messed up here. Gravity should have an exclamation mark at the end. And probably I should have like a submodule for forces or something. Mirage here. Okay, so gravity should work. We should see all the particles coming into the center. Yes, okay, so that's working just fine. So it's only the repulsive function that's not working. Here, there, repulsive. Let me try it one more time. Which is an easy fix. Well, it's not an easy fix, but we know that something's broken and we kind of know what's broken, so we can go from there. I'm actually going to be right back, guys. I'm sorry about that. Let me run this. I'll be right back. Did you just decomment the function? Maybe. Let me go ahead and check. 1 second. Okay, so this probably didn't work. Let's take a look. Give it a second. Yeah, so that one didn't work. Let me just go ahead and Control D here. Go into, where were we? Here, and let's see what we got. Ah, thank you. All right, take a look at there. Take a look now. Julie Double Dash project. Oh boy. For the record, guys, it's now 17 Celsius in my apartment, which means it's gone up by 2 degrees Celsius. I'm not sure if that's because it's later in the day or if the heater's working. It's still way colder down here in the basement than it is upstairs, so I reckon it's probably 14 down here in the basement. Which, it's fine. It's not a huge deal. It's just that, I'm still kind of sniffling a little bit. I'm sorry about that. I know no one really cares about the temperature of my apartment, but it's just a little bit colder than it should be. But also, I'm so cheap. It's kind of maybe I want it cold, you know? Okay, let's give this a go. And hopefully it's going to run. And then hopefully we get the simulation we want. And then I'm going to commit it. And then let's take a look. Good morning from the States. How are you, Screamer Chaotix? I hope you're having a wonderful day. Yeah, so good morning. I hope you had a great Thanksgiving yesterday as well. All right, let's take a look here. We're going to run GNU plot. And now, if this worked, we should see a bunch of particles flying out of the simulation. That's what we're looking for, just a bunch of particles running away. I don't know if it's going to work or not, but let's see what it is. Let me check over here really quick. There. Okay, 1 second. Perfect. Okay. There and there. Sorry, I was looking at my side screen for a second. Okay. This here is what I'm looking for. Let's take a look at Mirage. Okay. I'm going to do a prediction here. Let me move this over here. Okay, I'm gonna make a prediction here. Let's go. Let's make the prediction. All right. All right. I'm gonna start the prediction. This simulation will be repulsive. That's my prediction. And we're gonna give everyone a few seconds to think about it. So we've been working on this for the past 2 hours. This simulation will be repulsive. Okay, channel points. Yes. No. All right, let's go ahead. We are going to give everyone, I don't know, a minute. Start prediction. Confirm prediction. Sure. Got it. Okay, so we have a prediction going on in chat saying this simulation will be repulsive. So what we're expecting to see here when we look at the simulation is all of the particles in the box flying out, right? Now, we spent the past hour basically trying to make it so we go from the gravity, which is all the particles kind of coming into the center, to the repulsive interaction, everything kind of coming out. I think we fixed everything. The function pointers are working. Hopefully, this will work. Everyone has about 30 more seconds to vote on this prediction. We'll see how it goes. There's what is this 2.1K? What is the channel prediction doing here? It is 3,000 channel points versus 90 or 100 on one side. We'll see how it is. Okay. I hope this is going to work out. We've got another, 10 seconds? 9, 8, 7, 6, 5, 4, 3, 2, 1, and... All right, let's go. No! The answer is no, it's broken. Crap. Oh, this is the worst. After all that work. I'm sorry. I wanted to use the new prediction feature. I'm like, okay. The answer's no. Complete prediction. I'm so sorry. All right, let's see if we can fix it. I feel so bad. There were 3,000 channel points on one side for it succeeding, and 10 on the other side. All right, so let's do this one more time. No. Oh no. This is so unfortunate. I think the simulation actually worked. It's just I was plotting the wrong data. I'm so sorry. Oh man, that's super unfortunate. Oh man. All right, let's take a look at this one. Okay, well, it's still... Oh, no, it worked. Well, hey, it works now. Okay, okay, well... Cool. That means we have the function pointers working, which is amazing. Great. Good job. Congratulations to everyone who lost channel points because I'm a complete idiot. But look, you should have taken that into account before you voted, right? Like, everyone knows I'm stupid. I'm really sorry. Okay, it is working though. I want to turn that into a video. So here's what I'm going to do. I'm going to save only a couple frames here, and I'm not sure at what stage we should stop saving frames. Probably at, I don't know, like this point in here. Well, actually, what do we want here? Control C, Mirage here. At what stage do we want to... Okay, so maybe about 100 frames in is probably good. Yeah, let's do 150 frames. 150 frames exactly. Perfect. PCMan FM. So we're going to go down to 150 frames and just remove all the other ones. 150 frames is down here. So this one, shift, and shift. Okay, how do I do this? I don't know how to use GUI, so forgive me here. I think I just do shift and then down. Perfect. So we're just going to delete all these guys. All of these guys. No, not those guys. These guys here. Delete. Yes. Perfect. And now we're going to convert that to a video. So we're going to do Mogrify. Probably just this one will work. So we're going to convert all of them to be black and white so we have a video to throw up there in the upper left-hand corner. And then we're going to run /create video. Yes. And then let's do MPV test.mp4. There we go. We have a repulsive interaction. I'm so sorry. Like, I feel really bad. Zarko84 and also Gradient Ick. Thank you so much for following. Really appreciate it. Okay. Should I stop doing predictions? Because so far, both of the predictions I've done 2 predictions. One was, we're going to finish this in an hour. We didn't finish it in an hour. The other prediction was, this is going to work, and it didn't work. Should I just stop doing them? Or should, like, everyone just start betting on no? Because, like, no matter what we do, like, it's just going to be no. All right. So we've got that working. Let me go ahead and move test.mp4 into repulsive3d.mp4. There we go. Okay. Now, what are we going to do next? We have that working. I'm going to go ahead and commit what we... Got to get my channel points back. I'm so sorry. I feel so bad about it. I just lost 1K points. No big deal at my scale. Oh, see, now you're just like... I need to do something with channel points, I figure. You know, like, I feel like we should use them more frequently, and I don't know how to use them. I think the predictions are kind of fun. You know, like, they're not like... I don't know. I think they're kind of fun because that was actually really funny. Like, I really did. Like, I really thought it was going to work. We spent 2 hours on it. All right, let's do git status. Let's go back a directory, cd to sources, git add dot, git commit dash m, allowing more generic function interface. All right. Git push origin development. Okay, so here's what I want to do. I actually want to run the simulation again, but this time I'm going to run it with a few more particles, and I'm just going to get a few data points. I just want to see how long it takes to run. So we're going to go over here, Control D, and we're going to run this branch versus the other branch. I think it's going to be kind of negligible, but I want to see if there's any overhead to the functions, like the function compilation and stuff. In fact, maybe we... Here's what I'm going to do. I'm actually going to run this with a full CUDA profiler is what I'm going to do. So let's go ahead and do that. NVProf, isn't it NVProf? No, it's NVV. Oh no, what is the command? It's NVProf launch, nsys launch. There we are. Julia. I think I have to grab a particular Julia version. This should be the same Julia version over here, right? Yes, okay, Control D. So we're gonna go here, Control D. Let's just launch Julia -- project. And let's just take a look at what's happening. 4D, we're gonna do 4D in literally next. We're gonna do some profiling of the 3D results right now. And then we're gonna do 1D simulations and then 4D simulations. So probably either this hour or maybe the next hour, we're gonna actually do the 4D simulations. Okay, so what do I wanna do? I'm gonna do using CUDA Galilee. We're gonna run it once, and then we're gonna run it again to profile. And we're just going to see what happens. I just want to take a look at it, make sure it looks good is essentially what I'm looking at here. Just to make sure we don't have like a whole bunch of unnecessary launches and all this kind of stuff. This is mainly just systems performance is what we're looking at here. So Galilee.run, we're going to run it with the gravitational force. Gravity. Okay. Give it a second. There's a little bit of profiling overhead here. And then I'm going to run it with, I guess, 4,000. Yeah, we'll do 4,000 points. Because that was as many as I could run with before my GPU started sputtering yesterday. Yeah, speaking of which, if you see any video audio desync, it's because my GPU is like really working itself to the bone right now. And I can fix it pretty easily now that I know how to fix it. Okay, so now we're gonna do CUDA.appProfile. Here we are, and we're gonna run it with, let's do 4,000 points. Let's go. Okay, so CUDA's tracing, blah, blah, blah. Give it a second. Let's see what happens. And basically, I just want to look at the profiling results, make sure that just make sure that we have like contiguous blocks of, computation. I'm looking at the visualization up here, and I'm noticing that it's going at like, it's a 60 FPS visualization, but it's definitely chugging a bit. Oh well, we'll see what happens. It's just playing back a video. Like this is how, like, it's a GTX 970, so you know, God bless its soul. It's an old device, you know. Processing events. Let's see what happens. Capturing symbol files. And now we should have what is it? It's Nsight Sys, I think is what I need to open up next. It's just every time I have to do profiling in CUDA, I just kind of forget how to do it. So we're going to Control D. Report 1. So Nsight Sys report 1.qdrap. This should open it up, and we should be able to just take a look. Okay. If I'm honest, I don't really even know what I'm looking at here. So we've got the CUDA API here. Let me just go ahead and show an events view. Ooh, lots of allocates. Holy cow, why do we have so many allocates? This is not pretty. This is not pretty at all. Yeah, this is quite ugly. Why do we have so many allocates here? CUDA memcopy H to oh, you know what these are? These are for writing to file. All right, let me try running this again. Remove report 1.qdrap. And let me try it one more time, but this time we're going to remove the output to file. VI simulate. Oh, I could just run it the same. All right, Nsight. Nsys launch. Launch. Julia -- profile project. Sorry. Okay. Now we're going to do using CUDA and Galilee. And we're just going to run it one more time, but this time we're not going to output to file. What is it? It's file output. VI simulate. Okay. Yep, that didn't work. All right, let's go VI source simulate. And it is file output. So we're going to do this guy. And we're going to do file output equals none. That should work. Error. No method matching run. No method matching run int64. File output. Output method. There we go. That should run. Okay, and then we'll profile this. And so since we don't have the constant back and forth between CPU and GPU, it should be a better profiling result. And then we should be able to take a look at it and just check to make sure that we have consistent computation going on. That's it. That's all we're looking for. Give it a second to do all the pre-compilation steps, and we're going to run basically the same CUDA at profile function. Okay, so now we're going to run CUDA at profile here, and we're going to do output method equals none. Okay, let's give it a go. So this time we should basically be popping back and forth between the generation of the acceleration of all the particles and the generation of the acceleration and the actual Verlet output. So we want to do another output one more time, running only a single time step. And that should be what we need. So we're going to run this with about 1,000 time steps. And then we're going to run it again with just one time step. So we'll have two different reports that we can look at. Good. It looks like we're getting somewhere. To be honest, like I think I don't know. I think we'll keep doing the predictions here. Should we do a prediction about like what the output's going to look like? We could do that, but maybe I'm just being a bit too, like, yeah, one. Maybe we shouldn't. I mean, who cares? It'll be fine. Yeah, let's just take a look at the output because I think a lot of people don't even know what they're looking for here. So so no one would even know what to predict. All right, give this a second. So we have two different reports, report 1 and report 2, Control D. And now let's just run nsite sys, and we're going to run report. Let's do report 2 first, .qdrep, which is just a single time step. CUDA device, let's do the CUDA API here. And it looks like if we show an events viewer, we still have a lot of the CUDA memcopies H to device, which is weird to me that we have so many. Let me zoom in here. Why is this so bad? What is going on? CUDA, why are we copying so much to the device? So what are we copying to the device? So we start the simulation off, and we are copying what to the device? We are copying, this is the initialization. This is all the initialization bit. Okay, that's fine. So this guy, what is this guy then? I'm hoping, this is CUDA memory allocate. This is also CUDA memory allocate. Do we have any actual computation, or am I just really bad? CUDA memory here. Oh, here it is. There's the actual computation right there. Not this, but what is this? Event record. Okay, so that's this is it. Julia, GPU, nbody, context 1. That's it. This is the actual call to the, oh, that's unfortunate. Where were we? Oh, come on. Where's nbody? This is it, right here. Okay, the reason this is so bad, why do we have so many of these? It's only one time step, right? So if it's only one time step, why do we have so many of these guys? So we have 1, 2, 3, 4, 5, 6. We have device to device asynchronous. Do we? I didn't realize we had that now. Oh, and the other thing I get it now. Every time we run a time step, because we're allocating the temporary array. Okay, I get it now. So I think I understand what's happening. So this guy, and this guy, these are all generating the particles' positions, velocities, and accelerations. So that's fine. These guys are going to be, I think, no, this guy down here must be the generation of the temporary acceleration array. These guys, I'm not entirely sure what these guys are, if I'm honest. Yeah, I don't know why we have these D to D. The only thing I can think of for that is because we're calling nbody, which is then also calling a gravity simulator. Oh, maybe it's a switch between the Verlet and the nbody. So we have the nbody kernel, and then we have the Verlet kernel separately. So that could be what these are, which is not great, but it's fine. So we have the nbody, which we expected to take a while, but where's the Verlet calculation? Here it is, Verlet kernel here. So this takes 29 microseconds, whereas this guy takes 12 microseconds. Can we rank these events view, bottom up view, flat view? This guy, duration is 34. Oh, this is the order. What I want to do is rank them by duration. Right, duration here. Okay, this is what I was expecting. Milliseconds, nanoseconds. So this is going to be 11 milliseconds. It's going to take hardware to device, that's expected. D to D, that's also expected. CUDA memory allocate, again expected. D to D, I still don't know if I understand what these are being called for. We'll look at that later. CUDA memory allocate, Verlet integration. Oh, you're telling me Verlet integration takes longer by almost 2 times, than the n-body calculation. Now that's surprising. I was expecting the Verlet integration to take way less time. So what's going on with Verlet integration that's taken so long? Huh. Okay, well that's good to know. Yeah, that's really good to know. All right, let me do report 1.qdrip, which should be this one, and we're going to put this in the events view. I'm going to do the same thing as I just did. So this guy is going to be the n-body calculation at this scale. Yeah, it takes the most amount of time, which is good. That's what we expected to see. We have all these stupid CUDA memory allocates. But then we should have, where is it? The n-body calculation. Where is the n-body calculation? The reason we have all these allocates is because every single time step, we are allocating a new array to put into the GPU. So that's actually, oh, that explains the memory issues. Yeah, okay. That explains the memory issues as well. Okay, let's go ahead and fix that right now because it's just going to be worse as we go further. I'm not entirely sure the best way to do this, but I'll explain the issue here. So if I go into forces.jl, what I'm doing is I'm defining a temporary acceleration to be read into the kernel here. What I should do is I should create it out here and just read it into the find accelerations and then like reset it to 0 or something. Yeah, that's what I should do. So we are going to define the temp accelerations somewhere else and read it into the find accelerations here. So this is also going to read in the temp accelerations. Accelerations. And this also gives us a way to run this without reading in the array type as well. So we can just read in the temp accelerations from this stage, and that should solve some of our issues. Cool, okay. So let's go ahead and do this, right and quit. And then we're going to do one more profiling and see one more profile and see if that removes all of the CUDA H to D computations. We're going to vi simulate.jl, and here when we generate this, we're also going to generate the following. So it's going to be temp acceleration is going to be equal to array type of zeros of, and I suppose we should set them to 0 as well. Yeah, we should have like a set to 0 function or something, kernel. I think we can just do, yeah, I think we can just do that with broadcasting. I think it should be fine. Then the broadcasting operations become the biggest operations, but that's fine, that's fine. We'll just, it's better to do a broadcasting operation every step than it is to do a like CUDA H to D, hardware to device. So zeros of size of pset2 or pset dot par, accelerations. And that should do it, I believe. Okay, and then in here for the find accelerations, we're going to read in temp accelerations. Okay, and then here, when we're starting things out, we're just going to broadcast. So we're going to say temp accelerations of colon is going to be dot equals 0. And we're going to actually put that below after this guy. The find accelerations in here, this didn't work before, and I don't remember why. But I think it should be fine now. So let's just D2D there. Okay. And I think we're good to go. So let's go ahead and write and quit. And we're going to do one more profile, this time with the new, whatever we have. Okay. So let's do that. So we're going to run nsys launch Julia -- project. And we're going to do the same thing that we did before. Yeah, okay. I think I figured this out. So the reason we were running out of GPU memory was because the Julia garbage collector sucks. And so basically, as we were allocating this array every single time step, the Julia garbage collector couldn't keep up, and it was just using all of the GPU memory because it just okay, yeah. No one has any idea what I'm talking about using CUDA Galilee. I'll try to explain it while this is running. So we did a run not too long ago, like a super long time ago, about basically FFTs in Julia, doing an FFT of a GPU array. Let me run this, make sure it runs. I don't know why we're doing it for 1,000 times. Oh no, you're kidding me. Temp acceleration is not defined. Let's fix it. I'll run it and then we'll do some story time. Simulate here, temp accelerations. There, temp accelerations, plural. Okay, let me also go into VI forces and make sure we're doing this correctly. Temp accelerations, perfect. All right, we're gonna try this again. Okay, and while this is running, I'll tell the story time about the FFTs. Give it a second. This should also speed up our code a bit, which will be nice to see. So let's see if that happens or not. Here, we're just going to run it for a single time step. We don't have to run it for 1,000. All right, give that a second. And then while we're doing the big run, we will we'll talk about the FFTs and all this kind of stuff. Oh, man. So also, guys, I've been streaming for about 2 hours and 30 minutes now. Oh, I got to check something really quick. I'm so sorry. I got a message on Slack. One second. Wait. So I just got word about the resources at MIT. So let me just go back here and go back here. Okay, good. So I just got word about the resources at MIT. So if you guys noticed, my GPU was kind of chugging a bit. That is to say, like, it's slow. Like, when I run the code, sometimes my computer just kind of crashes a bit. I think I know why that was the case, and I think we just fixed it. But at the same time, I do need bigger GPUs for bigger simulations. So what do we do in that case? I have recently asked some of my old collaborators at MIT if I could use some of the resources that I used to use while I was there. They said yes, under certain conditions, and they basically told me some of the conditions just then. So that's essentially what just happened. So CUDA at profile, let's do 1,000 time steps first. Good. And then we're going to do it again with 1 time step. And hopefully, ooh, hello there. Okay. I'm lagging. I'm lagging a bit. I don't know what happened, but apparently, okay, I'm going to let it go, but my video and audio desync is going to be pretty bad after this is done. I'm at 6.56 FPS right now. Oh, I'm lagging a lot. Okay, I definitely need the other computing resource. But it's done now. I should be back up to 30 FPS. Let me fix my video because there might be some desync there. There and here. Okay, and now let's run the other one with just a single time step. Oh man, that was pretty rough. All right, we're gonna do 1 time step now. Why? I don't understand why it was using more processing power. Because I should have fixed that. Anyway, we'll take a look at the profiling results and see what's going on. Yeah, we'll see. I thought I fixed it. I don't see any video audio delay. I should be okay. So Control D. So now let's take a look at these two guys. So nsys, nsite sys, and then we're going to do report3.qdrap. So this is the 4000 run. So we're going to take a look here at show an events viewer, and let's take a look at the duration. And we have coup event create. Oh, that's fine. Nbody is the biggest one. Then we have all these memory allocates. I'm still not certain where these memory allocates are coming from. I know some of them, but I don't understand all of them. Yeah, why are we allocating any memory at all? Is this for the broadcasting operation? Weird. Yeah, okay, I don't know where these allocates are coming from. We're gonna have to fix that. Because frankly, this is pretty rough. All right, let's take a look at report, file, open. Where are we? Histograms. No, I want to go into back one more directory, into Galilee. Where are we? This is going to take a lot of annoying. Like we're gonna have to look at this in a bit more detail. I guess it's going to be under source and show you report 4.qdrep. Then we go here, show an events viewer, and let's take a look at the duration here. These three are expected. Relay kernel, again, it's weird that that's up top. Where are all the allocates coming from? Let me take a look at the difference between report 3.qdrep, which is going to be, let's see. I mean, we could look at start time instead and report 1.qdrep. So let's take a look at show an events viewer, duration here, duration there. So again, the memory allocates here are the biggest time sink, and we see that they are, let's see, 3.5 milliseconds versus 728 microseconds. And over here we see 758 microseconds and 1.6 milliseconds. So it looks like they're about the same. Oh, the n-body calculation is way smaller for some reason in report 3. I don't understand that one. Also, I don't understand where these allocates are coming from. We're allocating something every time step, but what are we allocating? That is a big problem. Okay, so we can just go ahead and do the 4D and 3D stuff, the 1D and 4D stuff. But then I want to dig into the performance here a little bit. I'm not happy with all those allocates every time step, so I want to cut that down as much as we can. And I just need to figure out where they're coming from. So we're just going to have to take a look at the source code, look at the profiling results, and just kind of work our way through it and figure out where everything's coming from. So we're going to do that in a bit. I realize that maybe a lot of people here are probably here for 4D simulations, not GPU engineering, but also like GPU engineering is a part of the 4D simulation. So just, deal with it. Okay, so let's do 1D first because that one's going to be pretty easy. And then we're going to do 4D after that, where we actually have to project down to 3D. It's not going to be too hard. It's just something we have to do. So for that, what I'm going to do is I'm going to create a separate I/O function, which we already have. But it's just, I'm going to basically write something more formally. So let's go over here, quit. Okay. So yeah, let's just go ahead and do it. So let's go into VI. Over here, let's do VI simulate, source simulate.jl, and over here we're going to go into VI.io.jl. Okay, so we have write to file, which is fine, and then in here what we're going to do is, let's see, we have write to file, which is totally fine. I guess in the write to file method, we need to have a specific projection down to 4D is what we need. So let's do that then. And so what we're going to do is the following. We're going to say if size of A2 is greater than, equal to 4, we're going to do end, and we're going to do a projection. How do I want to do this then? I guess we're reading an A, so I guess we're going to say A is going to be equal to projection. We can do this in a number of different ways. We could just continually project from 5D down to 4D to 3D, but let's just deal with 3D, 3 to 4, I guess is what we're going to say. It's a horrible name, but that's okay. Let's just do project of A. Let's do project to 3D. A, and then in here we're going to say, I guess else, if size of A 2 is greater than 4, print line, we currently do not support. Raise, we currently do not support arrays greater than 4D. I suppose actually what we should do here is we should say 4D for projection. Let's go there, there. Let's say we do not support arrays greater than 4D for projection. Oop. There we go. And this guy, we're going to say if, and then we also need an ampersand, and project. And then here we're going to read an optional argument, which is going to be dd here, and it's going to be project equals false. Okay, so basically, if we're running a 4D simulation and we want to project it down, then we're going to basically project to 3D. So let's go ahead and create the function to project to 3D. Function project to 3D is going to read an A, end here. Now here's the thing, when it comes to projecting down to 3D, there's a bunch of different ways to do it, but essentially we just multiply every single set, like every single four-dimensional element into a 3D form. So here's what we're going to do. We're going to go in here and we're going to say no color scheme. Do you think they are distracting? Yeah, I personally think they're distracting. I know a lot of people personally love color syntax highlighting. That's great for them, but it's just not something I find useful, so I don't use it. I think, maybe someone, hit the nail on the head yesterday when we were talking about how this particular stream is like attention deficit disorder on steroids or something, and someone said that, and maybe that's it. Like maybe like colors are just too distracting for me. Like it could be the same thing. Like maybe that's why I can't follow video content, because it's also just too distracting for me, and that's why I like text, because it's like super easy to read. I don't know, maybe that's true. Even if it is true, it's not like I'm going to fix it or anything, I just think it's easier to go through long code. To some extent you're right, but it really does depend on the code. Like in my opinion, like yeah, you're right. But also, like, there's a lot of things, like, if I see a colored object, my eyes don't look at the colored thing. Like, it just skips over the colored thing, no matter what the color is, So having everything black and white means that everything is equally as useful to me. So, like, I don't know, I just don't like adding color syntax highlighting to the code, because it just makes it so I start missing things, but yeah, I would love to do it without color scheme, but I like pretty colors. Yeah, honestly, it's totally up to you. Like, I'm not sitting here, like, everyone complains about my lack of syntax highlighting. Not everyone, but a lot of people complain about my lack of syntax highlighting when I code. Totally fine. I mean, like, they're completely valid in their in their own programming style, right? Like, totally fine. I mean, heck, I use VI. I mean, there's a reason we have a Simul VI emote here. Wait, where is it? It should be here. Simul VI. I mean, we have this emote. Like, I use VI, not Vim. I mean, it is what it is, Anyway, let's go here. So project to 3D. I think to do this, we have a W dimension, but we also need to read in some parameter that I usually call LW, but I'm just going to call L here. So project to 3D-A, and then we're going to also read in L. And then here we're going to read in an arbitrary L. So the idea here is that, like, when you project from 4D to 3D, it's kind of like you're casting a shadow onto a 3D object. So you kind of have this light source that you can move in and out. I don't remember what we typically do for LW, but I think it's like 1. Let me go and check some old code that I have here. Let's go over here and take a look at the old 4D code that I had in Python. Quit here. Right quit, sure. Back into CD into 4D. Probably an archive, and then 4D. Where is it? Molecular dynamics, maybe? No? Where did I put the 4D code? Backup directory, ls here. Let's see. Affine transformations, affinity propagation, Barnes Hut, BEC challenges, color quantization. Where did I put the 4D code? Did I lose it over time? No way. It must be here somewhere. Parametric, tree traversals, relay, viral video visualizations, histograms, heart, genetic algorithms, fractals. We've done so much stuff. Research, it's not going to be there. Schoenhage-Strassen. Oh man, the Schoenhage-Strassen algorithm. Man, I wish we could have finished the Schoenhage-Strassen algorithm. Temp, affine transformation, must be an archive, right? But archive only has ants, Bastrop, CUDA, function integrate, Igloo, linear algebra. Maybe it's linear algebra. Conjugate gradient, Gaussian elimination, Gaussian visualization. Huh, what's going on with the Gaussian visualization? Gaussian visualization, L is here. Ah, okay. Okay, what do we have here? FS integrate here, LS here. I cannot find my old 4D code. I was hoping to find like one that gives me a good projection down to 3D. Because, so I'm just gonna go open up my old video because I know it's probably there. I mean, the matrix there that we're gonna use is there. So let's go to your channel, videos, and now we're gonna go to most popular, ray tracing stuff. Could have been under ray tracing, maybe. Oh gosh, freaking ads. Nope. There we go. So I'm looking for this equation in here. So it's 1 over LW minus W. So that's the matrix that we're multiplying by. So what was LW? LW is the position of the light source. So yeah, let me take, maybe it's in the ray tracing stuff. I'd be surprised if it was there. I don't think it would be there actually, because this was done a super long time ago, before I cared about ray tracing at all. Ray tracing, I'll take a look at ray tracing. No, this is all Julia stuff. This is way back with Python. In fact, maybe I can just do tree into tree.text. And then I can vi tree.text. I can look for 40. No, that didn't help at all. Let's look for Python. Let's see, color quantization.py, power iteration, anderson.py, daemon.py, determinant, eigentest maybe? Create data, fourth dimension. Okay, so it's gonna be under visualization. Okay, I see. CD into visualization, and let's CD into fourth dimension. L is here, and let's go into VI fourth dimension .py. Okay, so I should have created an array in here. We have the project function in here. Okay, let's see what this is. So we have the projection. Oh gosh, temp W is going to be one value. So what's value? Value is being read in. So let's take a look at project here. Projection matrix there. Sure. It's literally just temp W, and temp W is 1 over val points. That's fine. So we should look for a project function. Project is a cube, and it literally just read in 1. So let's just see what happens if I read in 1. It doesn't really matter too much. I mean, this is literally just a projection, so like, you know, it's going to look different no matter what we do. So we're going to say L is equal to 1, or we just read it in. Let's read it in as an optional argument. Okay, so in here, we're also going to read it in as an optional argument for the project here. And it's just going to be L equals L. And then here, it's going to be L equals 1. Sure. Okay, so for the projection, I think we'd create a projection matrix, which is going to be equal to, it should just be something like, I think I'm going to do the same thing I did before. Temp W is going to be equal to 1 over, and it should be LW minus W, so it should be L minus the W position. We'll define what that W position is later. So we have A that we're reading in. A is an individual point, but it's also a matrix of points. So probably what I want to do is have this work on like an individual level. A is going to be equal to that. No. Let's just go through each element in A. So we're going to say output is going to be equal to zeros of size of A of 1 and then 3. So we're going to project it onto a 3D array. We're going to go here. We're going to do for I is equal to 1 to size of A 1. There we create the temp W, and here. Okay, so then in here what we're going to do is W here is going to be A of I and should be 4. Yep, so that's going to be the fourth dimensional stuff. So that'll be the fourth column. So that'll be our W component. I think it's LW minus W. Yep, perfect. So now all we have to do is create the array. So we're going to say projection array is going to be equal to, and it should just be something like, if I've done this correctly, it should be temp W And it should just be all zeros, I believe. Yeah, it's 0, 0, 0. I think I can do this, 0, 0, 0, this, and then we're going to do 0, temp W, and then 0, 0, and then we're going to have to do 0, 0, temp W, 0. Okay, let me go ahead and just kind of put these on separate lines so it's a bit easier to see that it's a matrix. There we go. And paste this down here. Okay, so that should be the projection array. So we're going to say output of I, 1 second, colon, is going to be dot equals to, and it should be A of I colon, 1 second, colon, and I believe we have to multiply the projection array on this side. Projection array times this guy. I think that's right. We can test it really quick, project to 3D. So let's go ahead and grab this, run it really quick, and make sure the project to 3D function actually works as intended. And then we'll run a 4D simulation, project down to 3D, and see what happens. So we have project equals false. So let's go into vi simulate.jl. And in here, we're going to make the default argument. I hate all these default arguments. We're going to have to fix this at some point. So we're going to do project equals true by default. And then in here, we're going to do write to file, and it's going to be project equals project. Same with this guy in here. Although to be fair, projecting the accelerations is kind of weird. Okay, so let's do write and quit. So we have those guys being written to file. In principle, we should be able to load this in Julia, and we should be able to do a simple projection down to 3D. So let's do quit here, and then we should be able to get a video with 1D, 2D, 3D, and 4D visuals just to throw in the upper left-hand corner. Unfortunately, the 4D is going to be kind of weird looking. I mean, it'll look the same as 3D, I think. It's going to look identical. Maybe not. Well, let's just see what happens. I have no idea. So we have simulate.jl. Let's go ahead and run Julia, _project. Let's try first to make sure we can project down to 3D just fine. And then we can go from there. Hey, Shidipto, how are you? Lou Jack, thanks for following. Really appreciate it. Okay. Oh, yeah. So as far as the chapter is concerned, I went through the first half of the Metropolis algorithm earlier today, and I'll be going through the second half tomorrow. And then after that, I think... it's going to take one more look over, but then I think the text is good. I think Amaris has some other comments on the code and maybe some notational thing, but I think the text would be fine. And then it's just notational questions here and there. And I think that's all it is. So yeah, I'm pretty happy with it. I think it's really coming along. So thanks for that. Okay, so we got this running. Let's do using CUDA Galilee. And then we're going to do Galilee.project to 3D, and we're just going to make sure it works on an array and see what we get. So, it didn't work. Something's broken. Let's fix that thing that's broken. Missing something. This is going to be on io.jl line 5 here. And that is because... Oh, these should be these guys. Try it again. See what we got. No, thanks to you for writing the chapter. I really appreciate it. Okay, let's see what else broke. Missing comma in argument list. What's going on now? Oh, I'm no longer able to define arrays that way. A is equal to 1, 2, 3, 4, 5, 6. That worked. What is it? Alt enter? No, that didn't work. How do I do this? That's all fine. So what's wrong here? Project array is going to be 1, 2, 3, 4, 1, 2, 3, 4. What's your dealio? All right, let's take a look here. So the error here is syntax else if. Oh, okay. Well, that's just me not knowing Julia's syntax. I always forget if there's a space there or not. All right, try it again here. This should precompile. We'll try to convert a 4-dimensional value down to 3D to see what happens there. Oh, come on. Just work. What is going on? Missing comma in argument list is in IO line 19. Thank you. You're right. Oh, this is just me doing like an awful job with like literally anything with Julia syntax. Like it's like I'm just missing everything. If only I had some sort of way to like, I don't know, color my text so that it would tell me like when I do weird, stupid syntactical errors like that. That would be nice. I mean, obviously I'm joking. So A is going to be equal to, how does this work? So the first dimension is going to be, so it should be, let's do 1, 2, 3, 4, 5, 6, 7, 8. There. Okay, so now what I want to try to do is Galilee dot project 3D, and we're going to try to read an A, and hopefully it works. And we're going to call it B, and B is nothing, because I didn't output anything. Let's go here, and let's do output, return output. All right, that's fine. Control D, Julia, double dash. This one, and let's try it again. What the heck? Leo's ready for a real IDE? No, I was just messing around. Obviously, I'm not such a pro programmer that I need an actual IDE, you know? Hey, happy little rat, how are you? I hope you're having a great day. Okay, so we're gonna create A, which is gonna equal to this. We're gonna do B, is gonna be equal to that. Good, it looks like it projected down to 3D. I don't know if this is the correct projection, but, you know, it did something. So that's something. So in principle, if I run a 4D simulation, it'll project it down to 3D and we'll have something. By the way, about the projection, I think you'll find that the 3D projection of 4D will have more overlap and appear to move more slowly, just like the 2D projection of 3D on your top left appears to overlap more and move slower. As we lose information of position and speed in the other direction. I think you're right about that. So let's just see what it looks like. Again, we might need to read in a different L here, L parameter. I'm not really sure how we want to do that. Let me check to make sure I'm reading it in appropriately. So from the run, we're going to have to read it in here as well. I hate these. I hate this so much. This is just an awful thing. So then we read in L equals 1 here. We write to file. We're going to have to read it in here as well. L equals L. Wait, what's going on here? L equals L. Output method write to file. IO, write to file, reads in L equals 1. Wait, I feel like I'm missing something. I feel like I just did this. Didn't I just do this? I feel like I just modified this file. What is going on? Okay, that's fine. I mean, it doesn't really matter, but I just... Okay, so in here we're going to do project equals true. Let me just go ahead and move these down to the next line. And L equals L, perfect. Then we're also going to do project equals true. Equals true, and then we're also going to do L equals L. I think that'll do. You know, differences between decent and expert programmer is just doing more mistakes and faster. That's kind of true. Okay, let me... this is bothering me. Okay, fine, I'll do this and that. Okay, project equals true, L equals 1 by default. Probably project equals project is what this should see. And this should also be project equals project. Okay, write and quit. Let's go into io.jl. Project equals false by default. Otherwise, we do, if project is true, we run this, L equals L. Sure, okay, that seems fine. Good, okay, this should in principle work. I mean, looking at the 4D code here, it looks like by default I was using L equals 1, but let me double check. So let me do project here. So we're running project here. It looks like we're using L equals 1 for define tesseract. Project PT is 1, PT value. So when we're doing single rotation, and value is defined as what? Oh, we're reading it for single rotation. Let's see what we're doing. So single rotation. Have you seen visualize fourth dimension? What is it? Fourth dimension. Okay, here we are. And then we have place duplicates. It's fine. Create tesseract connectomy. Oh man, back in the day when I cared about names. This is all commented out. Current cube. So we're reading the value in. So let's see if I can just find value. Value is all being read in there. Double rotation. Value is equal to 1 times 4. Oh, what is all this then? Value is equal to 5 minus 4 times I minus resolution, divide by resolution. What is this? Why did I do this? You were young at the time? Yeah, this was a long time ago that I wrote this. What is this? Resolution 1 minus resolution 2. So let me just do stereographic projections. And let me see, I misspelled projections, but I should be able to find it. Let me see if I can find this definition that I was using before. Hey, VCubingX, how are you? If you guys don't know, VCubingX is a, they make YouTube content. Let's just go here, VCubingX. Definitely check out their channel if you haven't already. They do a lot of like really cool math visualizations and stuff like that. Oh, I didn't realize I have not been keeping up, unfortunately. I didn't see this one that came out a month ago, but I'm happy to see you put it out. It looks good. So anyway, definitely check it out if you haven't already. It's a really good channel. It makes really, really good content. Stereographic projection here, I'm just looking for the array definition. Oh, you're kidding me. Just give me the array definition, man. All right, let's take a look at Wikipedia maybe. I should be able to find it somewhere. Let's go up. Here we go. There, paste this here. And let's see if I can just find like a simple, like the same array projection that I was using before. I was hoping I could just very easily, maybe I would just use stereographic 4D to 3D. Let's see what I have. Stereographic 4D. Sure, let's take a look here. G. This man made a feature, flammable math. Wait, this man made a feature. Teach me sine pi. Wait, what's going on? Made a feature, flammable math. I just traveled for 27 hours, so I'm dead. Oh man, look, I know how those travel days work. Like, yeah, like I definitely know how those travel days work. Anytime I travel from like Okinawa back to the US, it'd be like 30 hours of travel, and it was insane. Like absolutely insane. Oh, I didn't realize you did a video with flammable maths. It's super cool. Let's take a look here. Probably look at the PDF. I was really hoping to see like a very simple. We might have to just mess around with the tesseract a bit. Let me see what I did for the double rotation stuff. So for the double rotate, I was reading in a particular value. You went from Berkeley to India? Oh yeah, I hear that India in particular, depending on where you go, has different transportation like patterns. So like some places you can go and it's totally fine. Other places you go and you still have to take like a 6-hour bus when you get there to get home. Like a lot of my friends who were from India, whenever they traveled home, they'd be like, they'd complain not about the flight, but about like the bus trip that they have to take from the flight to get home, you know, which is the same. Like when I went to Okinawa, I'd always complain about the last leg of the trip. I'd always be like, the trip from Tokyo to Okinawa was always my least favorite because like you're so excited to get home, you know, and then, you know, it still takes an extra 3 or 4 hours to get there, you know. They should build a Berkeley within India. I think they're trying. I mean, there's a lot of really good institutions in India that people are working with. So the value here, what are we defining as a value? In range 8 is the value 5 minus 4 times I times resolution 1 divided by resolution 2 minus resolution 1 times 0.5. What does this mean? What is the difference between resolution 1 and resolution 2? Oh boy, this is a thing, isn't it? This is a thing. So the current cube is equal to the final cube. Oh my gosh. How did I do this? Like, man, looking at Python code is like super difficult for me now. So we have the value defined here, but it looks like just values equal 1. And then what we did is, oh, this is a different visualization. Oh, I see. I see. This is the visualization probably with the projection changing with time. That's probably what that one is. And then if we look at another value here, so let's go up a bit. Value there. Values there is equal to 1. We project there. We have the values is equal to this guy. That's not what I'm looking for. Single rotation ZW. These guys I'll read in the projection value. Double rotation, projection Z. Again, maybe not. Maybe I'm wrong. For J in range 0 to 8. What's 0 to 8 for? Gotta be honest, I don't remember what this code was doing. I'm completely lost here. We can just do like, I just need to figure out like what the projection means here. So if we go back to my stupid video in here, the idea is that the light source is like 1 unit away minus W. So how big is W going to be? W is going to be a range from like -2 to 2. So if W is a range from -2 to 2, we probably want the light source like, I don't know, 1 range above. So maybe we actually want L to be 3. Let's just see what happens. I'm going to mess around a bit. And we can try, like, let's try 2 different projections and see what they look like and just get the one that looks the prettiest. Let's do that. Like, I mean, I think that's what we're going to have to do in the end anyway. So I think we can just run a 4D simulation right now and just see how it goes. So let's do Galilei.run, and we'll do 256 particles. Why not? Dims equals 4. And actually what I have to do first is remove the other data files. And let's try it one more time. So Galilei.run. Here we are. Let's do a 4-dimensional simulation. Output method is going to be equal to file, so it should just be default. And then we go from there. What do we have here? They should build Berkeley. Why don't you use syntax highlighting? I just don't like syntax highlighting. I think it makes it harder to read code. It's surprising. Like the past few days, I have gotten like no comments about syntax highlighting, and today we've gotten like 3 or 4 about syntax highlighting. I guess it just depends on the day. But yeah, I think syntax highlighting makes it harder to read code, so I don't use it. That's why. Yesterday, people were saying that there's a bit of ADD-ness in the stream, so maybe it's because it's just too distracting for me. But for me in particular, like when I see color, like my eyes naturally just go away from the color, like no matter what the color is. Like, so white text means that like everything is equally important, right? Every single character is equally important. But like if it's red or gray or blue or green or all that kind of stuff, my eyes will just ignore anything that's colored. And so because of that, I just don't, I end up just missing a lot of stuff. It's just hard for me to like see what's actually happening, And like, sure, some people argue that the code looks really bad if it's not syntax highlighted. But my argument to that is, if you can only read code when it's syntax highlighted, probably the code wasn't formatted properly to begin with, Anyway, that's just a weird, like, kind of, I don't necessarily believe that argument, but like, it is an argument. Okay, so let's see what happens here. I'm going to take a look at it, see if it's actually being projected properly. And then we're going to try it again with a different L and see what happens there. But yeah, we do actually even have an emote in chat for those who don't know. Simul VI. That's just like, an emote for VI. I'll give it a go too. To be fair, you probably shouldn't give it a go. Like the same thing as you probably shouldn't use VI. Use what you feel use what you feel you're comfortable with. Let's go VI back into positions. Oh wait, no, I'm actually in the right direction. No, wait, what? VI. Oh, it's in check.dat is what I called it. This is 4-dimensional. That did not work. Whatever I did. Let's go to simulate.jl. Write to file here. Should be project is equal to project. Project should naturally be true. So let's go into vio.jl. So we have L is equal to this. So if project is equal to false but otherwise is read in, and project. So if size of A2 is equal to 4, is size of A2 not equal to 4? Let me just print line size of A2. Size of A2, sorry, A2, there, that should work, right? Let's go over here. Let's start running it again, but this time for, just single time steps, fine. Okay, that makes sense because I didn't, right? Okay, Julia using revise this time, and we're gonna try it one more time. For the record, guys, I've been streaming for about 3 hours now. So if you notice that I'm kind of a little bit tired or something like that, that might be why. I'm going to keep going for another 3 hours today. I'll be streaming until 8 o'clock p.m. So feel free to, obviously take a break whenever you want. Ask any questions, comments, concerns, anything like that. Go ahead, put that in chat, and I will respond to it the moment I see it. Again, for now, what we're going to do is we're going to get the 1D and 4D simulations, and then after that, I'm probably just going to do CUDA profiling a bit. It's kind of bugging me that we are running into issues with that. So also, for some reason, this is not being projected appropriately, and I don't exactly understand why. So what I'm going to do is I'm going to print line size of A2 here, and then I'm going to yank, and paste it down here as well. 1 second. Paste it down here. So this is after the definition of A, and this should have changed. So let's try running it again. We should get 4343 is what we should get. CUDA profiling, I'm actually pretty excited for it. So 4343, so it is actually being written out correctly. Am I just dumb? Let's go into check.dat, go down to the bottom here. Oh, it is 3D at the end. What's going on with the first time step? Let's go ahead and remove this guy, and let's try running it one more time. And let's take a look at check.dat. Oh, it's 3D. What happened? I don't understand what happened. Why did we have 4D? Whatever, it doesn't matter. So let's go back into io.jl, remove those print line statements. And remove these two down here. Write this again. I'm going to remove these data files, and we're going to run for 1,000 time steps. So we should be able to change this to 1,000. Oh, that's 100. Remove the data files again, and we're going to modify this so it is 1,000. And then in principle, we should have a projection from 4D to 3D, and we can just give this guy a plot. Okay, so let's go ahead and run into cd aux, and let's try running with GNU plot. Now let's see what it looks like. When you get this crap to run, I might make a stab at converting it to GLSL compute. Yeah, so we're gonna, I mean, look, you could probably do that, but I'm not sure if that's gonna be the best idea. Like, right now, the end body will work, but we've got a lot of work to do to like get the auxiliary stuff. There's just a lot of little stuff to get to work. But if you want to try it, feel free. Like, I'm not gonna say no, because it'd probably make a pretty cool visualization if I'm honest. But we've got a lot to do, like another month or two. Okay, so here's our 4D grid. Okay, this is actually kind of different. Like it's not clear how it's different, but you can kind of tell what's going on here. So let me make it a bit bigger. And maybe we want to make the axes a bit bigger as well. So let's go back to the very start here. A few frames back. Yeah, let me just go back 1 second. Okay, so first of all, I think the grid needs to be bigger. So let's do this again with a bigger grid. But what you can see here is we have a bunch of particles kind of zooming into the center. And then you'll see some that zoom super far, like that go out quite quickly. So let me try to make this like double the grid size or something. Let's go to vi plot.jl, plot.gp. And yeah, let's just do yank3 yank, paste it up here, comment these guys out, and let's make it, I don't know, 4 to 4. All right, let's see what that one looks like. So we're gonna run GNU plot. Let's see what we get. I did my own CPU side. It's fast enough, but need to test my Vulkan compute support in a week or two. Yeah, that's totally fair. I mean, if you want to do it, go ahead. We have gotten the parallel CPU and parallel GPU implementations working. It's just that I just kind of want to do some profiling because there's some allocation that's happening that I really don't like. Let's take a look at this in Mirage. Okay, so this is a bit bigger. I kind of want to run it with more particles and see what happens. So here it is at a bigger, oh, we need to zoom even further out. I see. Okay, that's fine. We'll zoom even further out. Okay, so we're going to zoom to like 1010 or something. Or something, I don't know. Maybe 8.8. Let's just go up in powers of 2. All right. So now we're going to do GNU plot and see what happens. Okay. Give it a second to do its thing and see what we got. All right, and also let me get some water. Okay, and then this will be essentially a 4D galaxy. I mean, projected down to 3D, but it'll be a 4D galaxy. And again, when we say galaxy, like we're missing a lot of stuff, like dark matter, all this kind of stuff. We're missing stuff. Okay, so let's see what happens if we zoom in. How far out do we have to go? Should we just drop? I mean, this is, it's not really helpful in any way. It's like, it's not really... Okay, I think we want the stereographic projection to like zoom in a bit. Oh no, zoom out a bit is what we want. So let's try running this again, remove this guy, and we're gonna set L equals 3. And we're gonna run it one more time, and we're gonna take a look at that plot. Why do you run everything on the GPU and not the CPU? The GPU is way faster. To be fair, in this particular case, the GPU is not that much faster compared to parallel CPU. But yeah, we can talk about the difference between GPU and CPU in just a second. Let me just try plotting this really quick. Yeah, then I'll talk about the difference between the GPU and CPU actually, because there's a lot of good reasons why you want to run it on the GPU instead of CPU. And a lot of it's not really clear to a lot of people why you might want to do that. So let me run this, get the plot out, and then in like 5-10 minutes, I'll answer that question if that's okay. It is actually a really good point of discussion that we should bring up. Okay, let's do Mirage. Okay, so now we're zoomed too far out, which is fine. Yeah, we're definitely zoomed too far out. All right, let's zoom in again to plot.gp. Let's try 2.2 again. Actually, no. Let's try 4.4 again. GNU plot. Let's see what we got. And hopefully this will be like an interesting enough visualization. So what I did is I moved. You can think of projection from 3D to 2D as like taking a light source and shining it on an object, and then looking at the shadow on the 2D screen on the other side. So we're kind of doing the same thing from 4D to 3D. And so what I did is I moved the light source back a bit. And what that will do is it'll cast like a more defined shadow. So, I mean, this is fine, but yeah, we definitely want to be closer. So let's take a look at what it looks closer. Let's go vi plot.gp. So let's try 2.2 again. Comment these guys out. Actually, D3D, why not? All right, let's try it one more time, GNU plot, and go from there. Dark matter might not be real after all. Some of the original observations that it's based on has been disputed. Apparently, problem with how they measured things. Fixed measurements fit the regular physics. There might be something else going on, though. Yeah, so for me, the dark matter is basically just useful as a tool to get the simulation to look more physical, in a sense. So right now, you kind of need it for the n-body simulation just to make it look better. Why are they so close to each other? I mean, look, this is kind of fine. Oh, it's just ugly. You're not really going to be able to... maybe. Okay, we're going to have to do a better visualization than this, because quite frankly, this is just a bad visual. Let me try moving the light source a little bit closer. So we're going to go ahead and remove this data here. Let's try with L equals 2 and see what that one looks like. The projection are close, not the actual particles. Right, that's what's happening. So we're going to go here, run GNU plot again, and see if we can just zoom in a little bit. So now we should be a little bit closer, and we should see things a little bit better. There will still be particles that fly super far off the simulation, which is fine, and we'll deal with that in a second. Then after this, I'll talk about why we run things on the GPU instead of CPU. Talk about that workflow, because it's actually, it's an important topic, I think. So let's run Mirage again. Okay, so this is a better cluster to begin with. Give it a second to load all the images, and sure. I mean, look, fine. I don't know what I was expecting. Again, I was expecting to look almost identical to the 3D results, and it kind of does. The only difference is that you see, like, particles are shooting out way faster, and the reason for that is exclusively because of the projection. So, like, you know how, like, when you look at a shadow, let's do this guy. So, like, here's the person, and then if you look at, okay, his hands are weird. And then his arm is weird now. Okay, there he is. This is a person. Yeah, there he is. His shadow will be like, some large figure over here, Okay, now it's a really long shadow. Sorry. And at the extents here, like his head over here kind of looks a bit bigger than his legs over here. I did a very bad job of it, but like when you look at a shadow, like the very far part of the shadow spans a very long distance as opposed to the places close by. And so what you're seeing here with this visualization is that like the particles that are all kind of at the center of the shadow, let's just go all the way back to the start of the simulation, are all kind of moving like as you might expect, a little bit slowly, kind of towards the center. But the ones that go far out go out really quickly. They shoot out and stuff like that. So that's kind of what's happening, big brain shadow. Yeah, I'm sorry, I did a really bad job of it. But this is literally because of how we're casting it down to 3D. It's not entirely physical what we're looking at right here. It's just that, they just shoot out very far, We'll be looking at better visualizations later. The surface receiving the shadow is the cause of the distortion. Yeah, you could say that. Yeah. You could say that as well. I think. Yeah, sure. Like, for example, if you were to take the 2D, like you take this visualization here. Let me go ahead and mute myself. You take this visualization here, right? Here. So let's go ahead and make this full screen. And you kind of plot this. So you see that if you watch this thing, it kind of accelerates as it goes further out, and then it comes back in. You see? And so it does it again, accelerates as it goes further out, and then it comes back in. That's kind of what we're looking at here. That's why it looks like it's going super fast as it's shooting out. So that's what we're looking at, I think. Okay, Okay, let me go ahead and convert this to video as well, just so we have it. And then we'll also do the 1D example. And then, yeah, and then we're just gonna, you know, yeah, we'll just go from there. So we'll have 1D, 2D, 3D, and 4D, and we'll put it all into one big video, and we'll just watch all of them. And then we'll talk about GPUs, which is super important. Who asked that question? It was Just Robbins, Rabes. I'm sorry, I hope you're still in chat. We will talk about that in literally like 5 minutes, if you give me just a second. Mogrify all the images, and then we're gonna convert that to a video. And then we're going to move that over to the 4D visualization, and we can look at the differences between all of them. Again, we're not expecting to see much at this stage. It's not really pretty yet, in some sense. In principle, we could do higher dimensions as well, 5 and so on and so forth. But like, you're seeing already when we get to 4D that it's kind of like weird to plot, you know? All right, so let's do /create video. Yes. And now we're going to move that over to 4D. And then after that, test into 4D.mp4. And now let's do the 1D stuff. There we go. Let's go over here. Let's do it in 1 dimension. I'm going to have to... also, we are running with more particles. It's probably fine. It doesn't matter too much. I could redo the 2D and 3D visualizations. Maybe I should. So we all run with the same number of particles. Let's just do the 1D visualization. Who cares? Let's go into VI plot. Actually, let me move CP 2D into plot 1D dot M GP VI plot 1D. Oh, come on. What did I do? Plot 1. I'm an idiot. I typed in VP instead of CP. There we go. Now let's do VI plot 1D.gp. Okay, so we should just have an... Oh, how are we going to do this? So it's a 1D thing. What happens if we just plot it? Is this going to work? And what happens if we just plot it? Okay, I have no idea. So let's do GNU plot 1D.gp. Maybe the plot 2D and plot 1D functions are literally the same. I have no idea. Let's just see what happens. This one's going to be weird looking. I need to find a better way to visualize it. Maybe the best way to visualize it is literally along a line. So let's do Mirage. Okay, so we have this guy. What are we looking at here? Oh, I see. All right, let me try this again. Okay, I understand the problem here. Set X range is going to be from 0 to, how many am I running with? 256. There we go. Set Y range -2, 2. We were not even looking at the particles. They were like all the way off the map. All right, we'll run it one more time. But it worked. We should probably also plot it with lines, is what we should plot it with. It's not a good visual, but yeah, we'll look at it. Let's see what it looks like. So let's do Mirage. Okay, so here we have all these particles. Oh, maybe this is cool. Oh, actually, that's not bad. I mean, that actually kind of looks neat. I don't know where the striations are coming from. But you should see them. So you see the clump in the center. You see all the particles kind of accelerating outside. And you should see them all kind of want to start clumping together. That's quite nice, actually. I kind of like that. I kind of like that a lot more than I thought I was going to. I actually really like that. All right, let's go and close that. Let's do Mogrify. And then we're going to convert that to video, and we're just going to put all of them into one big video. And yeah, that's what we'll do. And then we'll just watch all of them in just a second, and then we'll talk about GPUs, and then we'll do some GPU engineering. Looking forward to it. I liked that a lot more than I thought I was going to. That actually looked kind of neat. So let's do create video. Here we are, yep. And then we need to, I think straight lines are the orbit planes. Could be. Yeah, I think you're probably right about that. So let's go ahead and move test.mp4 into 1d.mp4. Let's go into vi concat.text, and we're going to do yank paste, change this to 1d. Yank paste, change this to 4d. Let me do write and quit. Let me do history grep concat. Oh, good, I have it. So I should just be able to run this guy. Yep. Where is it? There? No, come on. Oh, it's not, okay. Where is it? Hello? Wait, where's my, oh, there it is. Okay, perfect. That's what I was looking for. Control C. All right, we're gonna play it one more time. Here. Okay, and let's move this up to the corner. Okay, my computer's lagging a bit. All right, we're gonna watch this, and then we'll talk about GPUs. Okay, so let's go and full screen this guy. Move it back. Shidipto, hey, Siddharth, how are you? Could you plot ND and project to N minus 1D side by side, except for 4D, just show the 3D projection? We could try that. Yeah, do side by side. These are fundamentally different things, but yeah, we could project down dimensions. Yeah, we could create a general project down by one dimension. Wait, maybe I'm not understanding. So you're saying you could plot ND and project to N minus 1D side by side. Right, so we show 1D and 2D, 2D and 3D, 3D and 4D, right? All right, let's go ahead and watch this. So here's a 1D simulation. We see all the particles coming together. And what's really nice about this is you'll start to see them all start to clump in the center, which is what you'd expect. In just a second. Here, so you do kind of see that. And you also see this weird like orbit plane that's kind of moving up and down. I think this is actually what you would expect, but actually I'm not entirely sure. I think it kind of makes sense, right? So you have these kind of groups that are kind of far away, and they're kind of moving back and forth, oscillating in and out, and then eventually they all find themselves in the center. You do see some of these particles kind of like go quite high up. I'm not exactly sure why they're shooting off like that. It could just be a problem with the force laws. But yeah, overall, I kind of like this a lot more than I thought I was going to. So here's the 2D simulation. They all kind of come together. What I really like about the 2D simulation is you see, one second, here, one second. Come on, please. Okay, there. So you see the particles out here, which are kind of on the side. They actually shoot really far out. So you see this, and then you see, boom, they shoot really far out to create like a kind of mini square in a way. So you see that they kind of shoot out and everything. So anyway, so for 3D, you would also plot a shadow of the XY plane. For 2D, a shadow on 1D. Right. Yeah, that's fair. Yeah, we could probably do that visualization. It's probably not too bad. Yeah, let's think about that in a second. I do want to talk about GPU engineering in just a second. Let me get some water. So here's the 2D results. And then after this, we'll see the 3D results. Maybe we let these simulations go on for too long. But oh well, I don't really care that much. Okay, so the 3D results should be next. They all kind of come together. They don't fly out as much. I don't exactly know why. Or maybe they do go as far out, but because we're on a cube, we can see more of the plot, maybe? I'm not really sure. Anyway, so you just see they're all kind of coming into the center, just like the other plots. Right now, we don't have any angular momentum or anything to kind of like, rotate them into a plane or any of that kind of stuff. So when we see the 4D results, it'll look almost identical to this one, with the exception that the particles seem to fly out more. And that's because of the same thing that I was talking about before. It has to do with the projection. In 4D, it actually looks more like what you're seeing here. It's just that the projection will look kind of funky. So here's the 4D one. So here you see those particles are just shooting super far out. They're going to come back. And that's kind of the main difference between the 3D and 4D visualization right now. They look almost identical. It's not super clear what the differences are. By the way, Sid Darth Vader, thank you so much for following. Really appreciate it. But we're going to be working on it a bit more. I mean, the ultimate question with the 4D visualizations is, can you create like 4-dimensional double rotating galaxies? Like that's stuff that I kind of want to know about. And we kind of know what that's going to look like. It's going to look something like a cylinder in 3D. So this is kind of the stuff that I'm interested in looking at for the like physics, quote unquote, of 4D. Okay, we're back to 1D. Okay, I'm going to put this on all desktops, and now let's move over here, and let's do a brief side question. Journal, new page before. Okay, also the 1D thing, shouldn't they all be moving along a line instead of perpendicular to it? Shouldn't they all be moving along a line instead of perpendicular to it? Yeah, so they are all along a line. Yes, that's exactly what's happening. So for the record, with this guy, I visualized it. You could imagine all these particles are actually squished along a single line. That's actually what's happening. It's just that I thought I kind of like showing like all particle positions, but yeah, they are all technically on one line. They're not, and then I just kind of spread it out along a 2D plot. Questions, is that actually a valid way to plot it? I mean, it is, but maybe it's a bit misleading. I don't know. Okay. So let's talk about GPUs. Okay, so there's actually a long history here that I'm going to talk about. I think a lot of people here in chat already know exactly what I'm going to say here. So I'm not going to go too much into depth here. But the main question was, why are you using a GPU for doing the computation instead of just using your CPU? And the answer is that the GPU has been highly optimized to do these massively parallel operations. So way back in the day, with high-performance computers, HPCs, also called supercomputers, people used, a huge number of CPUs kind of stacked together into a giant, distributed group of CPUs all together. And that's what they did to do their computation. So what they would do is they would take simulations, like fluid simulations or something like that, and they would take little patches of the fluid, and they'd kind of, put this patch on this CPU, and this patch on this CPU, and this patch on this CPU, right? And so to some extent, early adopters of HPC technologies, early people who were used to using supercomputers, were very used to creating algorithms that worked in parallel. They worked distributed across multiple nodes. The GPU is kind of like taking that distribution across all these different nodes and putting onto a single device. So now instead of having, thousands of different compute nodes, you've got 1,000 different threads on a single device on your computer. This makes communication between the threads way faster. And ultimately, we see now in the high-performance computing space, a lot of people are moving towards using predominantly GPUs for their computation. This is called GPU, General Purpose GPU Engineering. It's just what a lot of people are doing. So the main reason you use a GPU is because if you can write something in a way that's easily parallelizable, easily spread across all the different cores on your GPU, it becomes really fast, right? Now, there's a bunch of limitations here in terms of memory, like you only have so much RAM available. Also, like in terms of transfer time between the CPU and GPU, that's also something that takes a lot of time. And so if you're asking why we're using GPUs, another reason as to why I personally prefer doing GPU engineering as opposed to parallel CPU engineering is because the profiling tools available specifically for CUDA GPUs are actually kind of way better than what I've found I've had on the CPU side. Like there are a few different things that you can use to do profiling on the CPU, but I find that the GPU tools are just way nicer in a way, specifically the CUDA tools. Also, cache size is ridiculously small, like 4 megabytes. Yeah, that's true as well. You can also do a lot of tricks with shared memory and stuff like that to make the computation faster. So, all this kind of stuff. There's so many ways that you can optimize GPU code. It's just kind of ridiculous. And it's kind of like a fun puzzle. But also, if you're interested in making the world's fastest anything, like world's fastest fractal simulator, the world's fastest, N-body simulator, whatever you're working on, for the most part, the fastest code bases nowadays, the ones that work on supercomputers, the ones that people are super interested in for scientific computing, these methods, these simulations are all done on GPUs. They're all done on parallel systems. So not only parallel, but distributed parallel systems. So for example, here's a paper I just have sitting around. Okay, I just broke something. Oh, no, I didn't. It's fine. Let me go into the Ramboleos mode really quick. So here's a paper I just have lying around of a 2.477 petaflops on a gravitational tree code to simulate Milky Way galaxy with 18,600 GPUs, right? And so to do these large-scale, galaxy simulations, you kind of need a large parallel computing device that can do what you want it to do. So that's why I use GPUs instead of the CPU. But notably, I am actually using a code base called kernel abstractions, which basically means that whenever I write a GPU kernel, it can also be executed on the CPU in parallel as well. Hello together, nice discussion. Did also use some kind of mix of those. Did also use some mix of those resources, let's say combine the computing on CPU as well as GPU in parallel? Yeah. So this is actually another type of computation called heterogeneous computation. which will use more than just the GPU that's available. It'll use the GPU, it'll use the CPU, it'll use whatever compute resources are available. There are actually some operations that are way, way faster on a CPU than they'll ever be on a GPU. For example, parallel reduction, which is a summation, recursion, also known as tree traversal. Or grid or graph traversal. These are things that are like, way faster on a CPU than you'll get on a GPU. But then there are things that the GPU can do way better. Like, for example, if you're going to do a partial differential equation solver, or like you're doing anything with images, where you can split every pixel up into its own little element to work on. All this stuff is really good on the GPU. And so some people do heterogeneous computing. The big problem is when you're doing computation on both the CPU and GPU, you don't want to mix the computation. And the reason you don't want to mix it is because the transfer time of data from the GPU to the CPU through the PCIe slot on your motherboard or whatever is slow. Like, that is the slowest part of the computation. We're going to do some GPU benchmarks not benchmarks, I'm sorry, some GPU performance analysis in just a second, and you'll see that by far the longest amount of time spent in any computation is on the transfer time of data from the CPU to GPU, or vice versa, right? That's just going to take a super long amount of time. Are they just slow in APUs? Nice detail. Never thought about that, the amount of time. Yeah, so in general, when you're talking about GPU computing, the main thing you're trying to figure out how to solve is the amount of time it takes is the amount of time you're trying to limit the amount of communication time. Now, APUs, I know literally nothing about. In fact, I'm going to Google it so I don't give you the wrong thing. I know nothing about APUs. But anything that's connected through a PCIe slot is going to be basically the same thing. So actually, what I should know. People talk about APUs all the time, and I nod my head, asking like I know what it is. Wait, is it just an AMD accelerated processing unit? What is an APU versus a GPU? A stupid question. I'm so sorry. But what about the new platforms like Apple Silicon, which gets shared memory? So that's an interesting case where they actually, I think, can circumvent a lot of that transfer time. So again, if you do like a shared GPU CPU type of thing, that actually allows you to do heterogeneous computing a bit better. CPU integrated GPU. Oh, right. So that's what the APU is. Okay, right. This is stuff I don't know much about it because people in the HPC space have not evolved yet to use APUs, but probably in the near future we'll see it used a lot more. It shares the same memory, so communication between CPU and GPU is basically instant. Right. So that is also fair, like with the heterogeneous computing. Good. Okay. That's the other thing. I actually don't know much about this area because I just haven't touched it very much. All of like the V100 cards and stuff that I usually use for computation is just so heavily on the GPU side. But probably you'll start to see the APUs make more of a dent. My current understanding, and this is me not knowing anything about the topic, I literally just had to Google APU. But from what I've heard people talking about in the space, right now the throughput of APUs does not match the throughput of GPUs. Therefore, it's not used so much for like scientific computation. But I think for general desktop use, I think that is probably the future. APU is a term AMD started using, but it's become universal. Do you know if CUDA OpenCL performed vectorization on CPU code, or is it same as your regular compiler? Do I know if CUDA performed vectorization on CPU code? No, so you have to do the vectorization on the CPU code fundamentally differently than how you do the vectorization on GPU code. I can't talk about OpenCL too much. I've used it a few times. But specifically with CUDA, you're only really parallelizing stuff on the device, which is your GPU. So if you want to do parallelization on the CPU, you have to do other things like OpenMP or MPI or something like this to do the parallelization on the CPU. And that's why kernel abstractions is so nice. It gives you that parallelization on the CPU as well as the GPU with a single piece of code. It's quite nice. Thanks for your answer. Heterogeneous computing means that CPU and GPU share the same instruction set. Right. There's different definitions of how you define heterogeneous computing, but in general, that's true. I was just thinking, because when Linux drivers execute GLSL on the CPU, they try to auto-vectorize, and I was hoping CUDA OpenCL would do the same. I don't know much about that. Again, for graphics, Happy Little Rat is going to know way more for graphics computing than I know. I don't do shader stuff. I do more kernel stuff. in terms of like the shader logic for OpenGL and all of this, all I know is that it's kind of roughly similar to OpenCL, but I'm way more familiar with OpenCL. I tried to do like a foray into OpenGL before. I created like a very simple like scientific visualization library, but it didn't get very far. I got bogged down with like all the vertex shaders and all this kind of stuff. It was so far from the type of computation I was excited to do. It ended up really bogging down the stream at the time and a lot of other stuff. It's a really abstract way to say what it is, but yeah, it's basically HAL abstraction for running code between different types of hardware units. Wait, actually, now I don't know what you're talking about. Are you saying that, yeah, hardware abstraction layer? Right. So, actually, question to you then. What part of that was really abstract? Were you talking about like, so the problem is like in the scientific literature, at least the papers that I read, heterogeneous computing can mean a bunch of different things depending on who says it. But as far as the APU computing, the shared CPU GPU stuff, it's exciting to see where we go with that. It would be really nice if we could have a platform that just allows for us to do the CPU computation super quickly, like for example the summation really quickly, and then also do just transfer that data instantaneously to the GPU to do that computation separately. We're actually going to run into a problem later today, maybe even that we have to like do this weird parallelization scheme for summation that would be super easy to do if we were doing it on the CPU, but because it's on the GPU, it ends up being super complicated. Maybe the APU stuff, which would be quite nice. Maybe the APU stuff allows for us to basically like throw away GPU computing in a bin, like be like, oh, actually all of this all these tricks that you used to do in GPU computing to make it fast, you actually don't need anymore because you can just use the CPU variant for that or something like that. That'd be actually really cool. Although I do actually really like the parallel computing stuff. So in some sense, it makes me feel a bit sad that that's going away, but that's progress. You make progress that way. It has a way to discover resources and a way to use them, and it's implemented at hardware level, so it's OS whatever agnostic. Oh, right. OpenCL specifically, I think you're right. It's written that way. Yeah, I'm trying to remember. So OpenCL, I remember not liking it because all the kernels were read in as strings. Like I think the same is true for shaders and stuff. And there were just a lot of issues with it in terms of usability. But maybe, yeah, I think maybe you're right. Maybe it does have the vectorization available in the CPU as well. Again, I only really know CUDA. That's what I've used a lot. Heterogeneous computing, OpenCL is just an atrocity. Yeah, that's fair. So I think you're right. I think OpenCL does actually do heterogeneous computing, okay. But I think just syntactically, it's a bit hard to use, I think is the truth there. And I think OpenGL is much the same. Okay. So we've got all our visualizations kind of working now. What do I want to do next? I want to take a look at some of the profiling results and kind of mess around with them and see if we can figure out where we're going wrong. Because there's a lot of things that are quite slow with the code that we're currently doing. It's funny, I thought OpenCL would be better on Linux, but couldn't get it to work where CUDA worked fine. Yeah, so the truth is CUDA, unfortunately, is just way easier to work with than OpenCL. So, I mean, this is the other thing, right? So let's talk about NVIDIA. I mean, probably shouldn't, but NVIDIA, right? Look, I want to hate NVIDIA. Everyone hates NVIDIA because, like, the fact is they're kind of a scummy company. They do a bunch of stuff to keep themselves on top by pushing down their competitors. Their big competitor is of course AMD with their AMD GPUs. Now the problem with NVIDIA is that they actually produced a better piece of software for doing GPU computing than anyone else has produced, and that is CUDA, right? There's a reason that everyone uses NVIDIA GPUs for GPU computing, and that's because CUDA is just so much easier to use than OpenCL. So, if you're asking scientists, do you want to spend your whole day doing software engineering, or do you want to spend your whole day just, doing actual science? They're, of course, going to say actual science, and CUDA allows you to do more of that science than OpenCL does. Now, of course, you're still going to be, you're not going to be able to do that much. Like, you're still going to be, dealing with, heterogeneous stuff, or like dealing with parallel computing, figuring out how to use shared memory. There's still all this stuff that you're going to have to do. It's just easier to do with CUDA than it is with OpenCL. And there's a reason why in the compute space, everyone uses NVIDIA GPUs, and it's because the software is so good. And that's just what it is, Anyway, what do we have here? Vulkan basically exposes what hardware can do with compute and graphics in one package, but it's much lower level than CUDA, OpenCL, etc. Right. I thought about looking at Vulkan, but I just never did. And GLSL isn't really great for compute. I know that as well. Did you use already WSL2 to work with this CUDA libs? I don't know. What is WSL? Is that the Windows subsystem for Linux 2? I didn't know there was a 2 there. But if that's the Windows subsystem for Linux, the answer is no. I have I've never used Windows effectively. The last Windows version I actually used legitimately was Windows Millennium Edition. So the answer is no. Unfortunately. So there could be a whole bunch of library issues specifically with the Windows subsystem for Linux that I don't know about because I know nothing about it. So, sorry about that. AMD answer to CUDA is ROCm. Yeah, I've seen a lot about ROCm. So also with kernel abstractions, this can technically target ROCm code as well. They're still working on all the bugs for AMD. There's still a lot of issues with it, but in principle, it can also target AMD, and they're working towards that. And the reason they're working towards that is because there is a new cluster coming out that is exclusively AMD GPUs. It's quite interesting to see where that's going as well. Like honestly, I'm quite surprised to see AMD even having a showing in terms of like GPU performance and stuff like that nowadays. But yeah, I don't want to dwell on the Windows comment too much. It's just that, like, I don't know. I've been using Arch Linux since I was like 15, and that's just what I've been using. So it's been about half my life using Linux exclusively. So, but it's in use in current and upcoming supercomputers. So I'm pretty confident it'll get better. Yeah, that's exactly what I was thinking as well. We'll see how it goes. Unlike OpenCL, that's basically dead. Yeah, I mean, the thing is, OpenCL can target AMD GPUs as well. So I'm surprised that it didn't. Like, the thing about OpenCL is it can target GPUs, both AMD and NVIDIA GPUs. So I was super surprised it didn't take off. It was just because, the software was just so hard to use, NVIDIA outperforms to that extent. It's not NVIDIA. It's CUDA. That is so much better than OpenCL. It's so much easier to code in CUDA than it is OpenCL. That's why. It's not the GPU hardware. The hardware is kind of roughly equivalent, but CUDA itself is way, way better. Let's see. Windows is the professional OS that has pre-installed unremovable games. Wait, it has unremovable games? What do you mean unremovable games? Like you can't remove Minesweeper or something? Like, what does that mean? Anyway. I don't want to delve too much more into that. So what I want to do next is open up some profiling results. So I'm going to run nsite. This should do it. Report3.qdrep. This should be for, it's in the other directory. CD back into source. Let's see here. Now we're going to do this guy. This should be the 1,000 time step run, and I want to do the 1 time step run. So let's do report4.qdrep. Okay. So we ran our code for 1 time step, and I just kind of wanted to look at the results, see what we got here. Show an events viewer. We're going to do duration here. So we spend the most amount of time with CUDA mem copies H to device, which is actually, no, that's interesting. No, most of our time is actually spent in device to device. I don't know why we have device to device. This is something I have to figure out. I don't know where that's coming from. Anyway, we'll talk about the profiling results. This is kind of what I want to dive into. If you remove Minesweeper, Windows will not start anymore? No way. You guys have to be trolling me, right? Like, there's no way that's true. Not at that scale, because Minesweeper is not installed by default anymore. Oh, so like, what is installed by default? Okay, so to be fair, like Linux, it comes with apps that you can't install or you can't uninstall. Like, for example, if you try to uninstall systemctl, like, that's just not going to work. Your computer's not going to load because that's like the bootloader. Like, you uninstall grub, you're going to break something, You can uninstall your UI. If I open a terminal, I say sudo pacman-r, and then I do openbox. I can literally right now remove my GUI, right? I can do that. And in some sense, that is just like what you're saying. Like, it's an unremovable app. This is an app that I can't remove on my system. Otherwise, I break it. It's not exactly the same scale because, like, obviously I know how to fix that. But, you're just talking about PCI being slow and reducing transfers. Right. So this is exactly what the issue is. So I mentioned this not too long ago, how the longest part of any computation is usually the copies to the from the CPU to the GPU. So let me just take a look at this guy that we have here. and we're just going to kind of walk through it. How do I scroll appropriately? Okay, so we start out with this really big CUDA memcopy H2 device asynchronous. So what this is doing right here is it's the initialization of all of our particles. So we've initialized 1,000 particles, and they're n-dimensional. So it's a 3 or n by 1,000, right? And then we're transferring these over to the device. So this is the creation of a set of positions, accelerations, and velocities, and also a temporary acceleration set of values that we're writing to. So all said together, it's 4 times 1,000 times 4. So it is a lot of points. Ideally, we fix that. But this is going to take the longest amount of time. This is what I expected. What I didn't expect is this D to D. I don't know where this is going from, like where these are even coming from, if I'm honest. And it seems like, let me go ahead and do, this seems to be in the CUDA, this is in this call? How does that make sense? No, here it is, right here. CUDA D to D. That's what it is, right there. That must be this call here. There. Yeah, that's this call. So where's the other call? And then you see all this other nonsense over here. So if I zoom in over here, what are these guys? So this is CUDA memcopy H to device. This is going to be CUDA memory allocate, CUDA H to device again, and this is going to be CUDA memory allocate. That's all fair. But what is this guy? Where is this being allocated? CUDA memory allocate, and then where are we copying device to? Is this a broadcasting kernel? Let me think about it. I'm going to try running this again. I don't know how to do this, actually. It's not that you can't uninstall without breaking. It's that you literally don't have the permissions to do so, even if you're the admin user. Oh, that's interesting. I am kind of surprised by that, if I'm being honest. Okay, so then after that, we have the Verlet kernel, which is right over here. Actually, it should be way further down. Where is it? It should be... Where is it? One of these guys, I believe. So this guy, maybe? So that's the velocity kernel. This is the broadcast kernel. Broadcast kernel. Oh, that's when we set it all to 0. So then we have this guy, which is the Verlet kernel. Then we have the n-body kernel. Where's that guy? Should be just before the Verlet kernel. Is it that small? No way. Why is this so small? Relay kernel is here. That's that one. Let me zoom in a little bit. Where's the computation? Is it all over here? Maybe it's there. Maybe this is it. It's over here. That's where it is. So this is the, yeah, so that's this kernel over here. Oh crap, where'd you go? Oh crap, where is it? It's over here somewhere. I lost it. I'm really bad at scrolling through this. So it should be on this side, right about here. I need to find a better way to scroll in. There, move it over a little bit. And here it is right there. That's the kernel that we're looking at right there. So this is our one compute kernel. So we've got multiple compute kernels. Let's just take a look at the visualization here. So here's the visualization we're running. And what you can see here is that we have, by the way, I missed this a few minutes ago. Fusion Happy, thank you so much for following. We have all these particles. Let me go ahead and full screen it. And each of these particles is feeling the force from all the other particles, right? So we've got two steps here. One, we have, well, three steps technically. We have one step where we are looking at all the other particles and seeing what the force is applied on each individual particle, right? Then we have the other step, which is actually moving them forward with time using Verlet integration. So those are the two big steps. The final step is just resetting values to 0 for the next point. Let's see, what do we have here? Even if you are an admin user, yeah, the trusted installer user group is above all user accounts, even admins in Windows 10. That goes back to at least XP, I think. It just means admins aren't admins. Interesting. Previously, trusted installer wasn't any higher than normal admins, e.g. you could duplicate system 32 if you wanted in previous Windows versions. Now you can't. Yeah, so previous Windows versions meaning like Windows XP? I mean, I know in Windows XP you were able to, I think. I actually, again, I never used Windows XP. I only used Windows Millennium Edition. And then after that I think I had Windows 95. So I think I had Windows 95, Windows Millennium Edition, Windows Vista for a little bit, and I technically had Windows 7 installed on my computer, but I never actually touched it. So when I say Windows Vista for a little bit, I used it for a month. So like genuinely speaking, I know nothing about this. Like I'm blind when it comes to Windows problems. You know, I used to be like, I used to say when people talked about Windows on the stream, I used to be like, oh, I just like Linux better. But the truth is, I genuinely know nothing about Windows and find the entire ecosystem like incredibly confusing. And so because of that, I just don't use it, you know? Like Macs, at least I can reason my way about, but Windows is just so confusing to me. If I had only seen Windows Millennium Edition, I would also not touch any other Windows anymore. That's probably fair. But the truth is, like, you know, I've had to do like tech support for my mom's like Windows 8 device, and I've had to do it for Windows 10 as well. I've technically used them to help other people in using them, so it's not like I know nothing about them. It's just that like I don't know enough about them to form like an actual opinion. It's like, yeah, technically, if you want me to install Windows 10 on your machine, I can do that. If you want me to fix something on Windows, I can figure out how to fix it. I'm good enough at Googling. But if you want me to use it as a daily driver, then things get really complicated for me. I don't know how do you install things on Windows? You have to go online, you have to like figure out the right exe to download. It's just confusing. Like, how do you do, like, there's so many things that's just hard and just kind of confusing to do on Windows, and they're easy to do on Linux. Now, the other side of that coin is there's a bunch of things that are complicated to do on Linux that are really easy to do on Windows, right? And so, like, because I'm a terminal user, because I'm a heavy terminal user, I'm a, what are they called, power users or whatever, I like it. I like Linux. It's easy to use for me. But if you give me a like full GUI setup, I get super confused super quickly. 98, XP7 were also great versions. I don't know if I ever had 98. I think I just had 95. Maybe I had 98 at some point. But like we're talking about like when I was like 10, like really like younger than 10, probably like 7, like really young. I'm not someone that like knows anything about anything. Don't ask me questions here. I'm like completely lost. Okay. So what I'm trying to look at here, let's go ahead and look at the start time here. What we also see here is a whole bunch of, like, what's this guy? Where's this guy being called from? Okay, so remember, this is only for one time step. Okay, so here's what I'm going to do, guys. I'm actually going to take a quick 2-minute break right now, and then we're going to hop into the profiling results. I realize it might not be the most, you know, like the coolest content to see on stream, but I feel that, like, it's really, really good to go through and just, like, try to clean this up a bit as best we can. We're doing a lot of like weird things with the kernel that we're calling. And so finding any way to like make this faster, remove the amount of memory copies, all this kind of stuff would be ideal. You know, getting that runtime down as fast as possible would be quite nice. Especially because, you know, when we run this with a lot of particles, my GPU is struggling. And I want to be able to run with at least enough particles that my GPU doesn't struggle. So I'm going to be right back. I need to get a little bit more water, and then I'll be back in 2 minutes, and we're going to take a look at the profiling results and see what we can do about that. That might be what we're doing for the rest of the stream today. So if you're not super into the parallelization and the discussions about GPUs and stuff, feel free to come back tomorrow. We'll be doing more stuff then. But for the rest of today's stream, for the next 2 hours, it might be exclusively GPU stuff. So it might be just profiling results, figuring out how to fix the code so we don't have as many, you know, mem copies, all this kind of stuff. Again, I think it's quite cool. I think it's really fun. But I think, you know, obviously, you know, you're here for a 4D Galaxy simulation, and this is all part of the process. But it's not like the cool, sexy part of the process to some people. For me, I find it really cool, but not for everyone. And 3.11 was also cool back then, but everything in between is quite a catastrophe. I know nothing about 3.11, never used that. Okay, I'll be right back. Give me 2 minutes, and then we'll just spend the rest of the stream doing GPU stuff. Pretty excited for it. So see you guys in just a second. Okay, I'm back. Sorry about that. Good news is the apartment is now 18 Celsius after. So earlier today it was like 14, and it's gotten a little bit warmer after about 4 hours of the air conditioning or heater being on. What do we have here? Never seen anybody work with straight up CUDA. That's interesting. Same for me. Normally people just load up CUDA with TensorFlow or the like. Oh, that's probably true. I have roughly 10 questions new popping up in my head every passing second of stream. That's a lot of questions. If you have questions, please ask them. Like, genuinely speaking, I'm super happy. Like, if you guys just want to spend the next 2 hours just chatting about like parallelization, GPU computing, high performance computing, supercomputing, all this kind of stuff, just I'm happy to chat. Like, I mean, I wouldn't be here if I wasn't happy to chat, you know? So I'm not like giving you guys a stern lecture here. Obviously, don't ask questions if you don't have any. I'm not I'm not trying to draw information from you guys. I'm just saying that, like, genuinely speaking, I'm here to answer these questions. So if you have any, please feel free to ask. In terms of CUDA and TensorFlow and all this kind of stuff, I think you're generally right. I think most people don't work with straight up CUDA. I think most people probably have like an application that uses CUDA underneath. And that's just how it is. So when you're using GPU clusters and stuff, a lot of these clusters are built specifically for like machine learning nowadays. Like they're built for like these TensorFlow calculations and stuff like that. Ooh, I just screwed up. My keyboard's blinking. Let me fix something really quick. I think I have a slight video audio desync. I think I fixed that by doing this there, and that should do it. I don't know if that fixed anything actually. Okay. And then let me go back over here. So, let's see. I'm unable to rank the questions in order of what piques my curiosity the most. Well, just ask any of them then. Like, genuinely speaking, any question, I'm happy to answer. Okay. I'm going to go in here really quick. We do have the projection from 4D to 3D working okay. Let's go over here, Control D. Over here, we're going to CD into projects, Galilee. So I'm just going to have it kind of open in two different screens so we can flip between the code and the profiling results. Okay, over here, we're going to CD into projects. Oh, CD projects, Galilee. Okay, let's do clear here. And over here, we're going to clear here as well. And again, so let's go over here, clear, and over here, we're just going to clear it up. Control D, clear. Okay, the first thing I'm going to do is just take a look at the code, and I'm going to put it over here. So let's go to VI source, and then we're going to do, let's go into simulate.jl. It's going to be over here on the side. And I'm going to get some new profiling results for each step of the simulation instead of like the whole simulation together, because I'm going to try to pick apart what was going on with those profiling results. So to do this, we're going to go back a directory and we're going to run nsite-sys, and then we're going to do, nsys launch Julia --profile project. Ooh, I'm getting tired apparently. nsys launch, I misspelled launch. Try it again. Okay, so here's Julia. Let's go ahead and do using CUDA and Galilee, which is a code we're running. I'm actually just going to run one step, and then we're going to just go through each line in this run file and run each individual line is what we're going to do. And again, guys, if you have any questions, comments, concerns, anything like that, just please ask. I'm more than happy to talk about it. Output type, I believe? Output method equals none. Okay, so this should run with nothing. We're going to run with this. Should be fine. And we're only going to run one time step. Well, let's do 1,000 time steps. Why not? Is your interest more in physics or modeling or CSCI? What is CSCI? Computer science, but what's a CI? I mean, this is an interesting question. My interest is almost always in the computation, right? But like 4D galaxies, this is a really interesting n-body simulation that you can run that it's super simple, right? It's easy to parallelize, it's easy to mess around with. There's a lot of really unique things that you can do with it. And it's also useful for a lot of, things to do in like computer graphics and stuff like that. CompSci. Yeah, sure. CSCI. What does the CI stand for? Wait a minute. Anyway, so my general interest is in computer science, but also I'm kind of in the border with something that you would call computational science. This is just a bunch of people who focus on doing the computation that you need as quickly and efficiently as possible. In general, computational scientists are like, they're not real scientists. They're not real computer scientists. So you run into a situation where computational scientists are like they end up becoming research software engineers, which is just kind of a dead end job for a lot of people. So, it's really difficult to find like a professorial position doing computer science or computational science because it doesn't fit into computer science, but it also doesn't fit into the sciences because you spend all of your time doing software projects instead of all of your time writing papers. So anyway, there's a lot of little things here and there to kind of talk about here. But for the most part, I don't know. For the most part, I feel like the physics to me is interesting in that it provides a lot of interesting computational tools to look at. That's why the physics is interesting because of the fact that for physics simulations, like the reason I went into physics to begin with was because when you are a physics undergraduate, right, and you're learning physics for the first time, it doesn't make that much sense. Like we just had discussions yesterday about how the speed of light is the same, depending on what reference frame you're on at, right? Like no matter what reference frame you're on, the speed of light is the same. So no matter how fast you're running, the speed of light is always going to be the same speed, which is super interesting, right? And there's stuff like this that you have to grapple with. But the reason I was always interested in physics is because there's so many different simulation methods with physics. You've got Monte Carlo, which bleeds into the Metropolis algorithm, which we talked about earlier today. You've got n-body simulations with molecular dynamics. You've got DMRG for spin dynamics. You've got tensor network stuff. You've got machine learning and stuff can be used in science. You have everything. Everything can be used in physics. Every single simulation method that exists for computational purposes has a utility in physics. And it's super nice to see like a clear applied computational, a clear applied, thing for computer science, right? So that was why I was super interested in physics. Now, I didn't realize at the time that at the time I started my PhD, that my interest was so far on the computational side that I would start actually to loathe the physics the more I did it. But that said, I think that's an interesting thing to learn during your PhD. Like, what actually are you interested in? And I think a lot of people during the PhD, they take time and they just start digging their own grave. Like they're sitting there like, oh, I hate my research, I hate doing this. But the point of the PhD isn't like to hate the stuff you're doing. The point of the PhD is to use the research that you're doing as a seed and figure out where you or how you want to grow that tree. Like, the work I was doing was computational physics. And so I could grow either towards the computation or towards the physics. The PhD was growing towards the physics, and I realized that wasn't the direction I wanted to go in. So then I tried to take a postdoc that would allow me to do more computation. And so that's kind of what you do. You try to just figure out your place. I don't know. It's super long and rambly. I'm sorry. I don't know if that's helpful for anybody. Let's go study computational maths right now and consider data science. Yeah, data science is quite nice. Would have to guess there's money there. There's probably money in data science. I bet there's a lot of money in data science. Okay, here's what I'm going to do. I'm going to initialize a bunch of particles. So we're going to say p set. It doesn't matter the dimensionality here. So we're going to say p set is going to be equal to initialize, and it's going to be a coup array. Okay. I think I want to check this guy as well. I want to see how long the initialize takes. So we're going to do at CUDA, come on, dot at profile. There we go, of this guy. Do you see how long this takes? And we're just gonna, this should be report 5.qdrep, and we're gonna take like every step along the way. We're gonna see how long everything takes. And so then I have to create the second particle set, see how long that takes as well. I don't think it's going to take too long, but I'm really trying to figure out the device to device. So I think this actually is where the device to device happens. So I want to check that as well. So let's go ahead and run that and see what we can do. So we're going to do CUDA.appRofile. This must be the device to device. Must be. Particles of copy. One second. Copy of p set dot positions. Okay, that must be it. Copy of p set dot velocities. And then finally copy of pset dot accelerations. All right, perfect. Misspelled accelerations, but that should be fine. And then we want to do, I think we're going to call this pset2. Let's see, positions, velocities, accelerations. This should be fine. So I'll say pset2 is going to be equal to this guy. So we're in CUDA app profile here for report 5. And we're going to have to write this down somewhere. So let me go ahead and put over here. I'm just going to open up notes. And it's going to be 1 is going to be equal to initialize. Sorry, this is going to be 5 is initialize. Okay, so the next one, 6 is going to be a pset2 copy. Okay, 7 is going to be the creation of the next line, which is going to be temp accelerations. Oh, this broke. Pset not defined. Oh, how interesting. Interesting. Okay. Okay, well, let's go ahead and remove that file then. Remove, oh, it's report 2. Never mind. Report, one second. Remove report 2.qdrep. And let me define pset again. Here. CUArray. Okay, so now we're going to do CUDA app profile again. This is for pset 2. See if this one actually works. I'm an aerospace engineer turned data scientist, very new to this. Is that just a Zorg server without any DE, new to Linux as well? No, so this is actually OpenBox. If you're interested, let me go ahead and give you guys a link. Also, before I open this up, please consider wearing sunglasses. People get mad when they see my Discord, and I'm just letting you know, I'm using Light Theme. If you need sunglasses, put them on. 3, 2, 1, there you go. Okay. So in the off-topic channel, if you go to the pin messages, you'll see actually the OpenBox theme right here. So I'll go ahead and give this to you right now. Create invite, copy, paste. Here you go. But yeah, I quite like it. I really do. So now we're going to create a second pset. Pset 2 is going to be equal to, sure, that should work. So now we have pset 1, pset 2. Let's go ahead and create the temp accelerations, which should be this guy. I'm also going to create a report for that. So let's do CUDA.appProfile. I know this is really stupid what I'm doing, but just hear me out. I just want to know what each line is doing. And I'm really trying to figure out where the device to device is. And I'm pretty sure it's in this line here, but I'm double checking. So this allows me to check each one individually, which is quite nice. A few minutes ago, Vladimir, thank you so much for following. Really appreciate it. Yeah, but as far as Linux is concerned, honestly, I've been using this setup. Since I was, I don't know, like 15. Like generally, this is the first thing I created when I started my Linux journey, I guess you could say. So I need to go back up here and I need to change this so it is CUArray. There we go. Run that, get that report, and then we're going to do the next one. If you guys have questions about Linux or anything, feel free to ask. Like, I mean, you guys know that at this point, you guys should see. You can look at my screen, and you can immediately tell what kind of questions I can answer. Like, anything related to computation, this kind of stuff is probably fine. So we're going to do this guy, and let's go ahead and do temp accelerations. There we go. Okay, so we got the temp accelerations. Everything should be good to go. So now we just do a single iteration, and all we have to do is run this guy. Wait here, and I think we can just remove, wait 1 second, I'm doing a very bad job of this. So let's go ahead and do CUDA.appProfile, and let's go ahead and wait on this guy in here. Let me also write some stuff out. So this should be 1, 2, and 3. And this is going to be the creation of temp accelerations. And then 4 is going to be, what is 4 equal to? 4 is going to be our find accelerations. And then 5 should be relay. And 6 is going to be resetting to 0, just for completeness sake. 0. Okay, good. So we'll have that all written down just so I remember to look at it later. Let's go ahead and run this. This is just finding accelerate. Oh, it's going to break. It's going to break because we don't have a force lock. Oh, you're kidding me. Oh, that's okay. All right, this is me being dumb. Let me just wait for this to run, and we'll go from there. But yeah, in general, if you're here for the first time, you haven't been to my stream before, I gotta remove report 4. Yeah, let's go ahead and remove report 4. And let's remove this force law at the end here. It should just naturally run gravity. So if you're new to the stream, you haven't been here before, the point of this stream is just to do research in an open, engaging way. The hope is that, we as a community can just do really cool, boundary pushing stuff. It might not be like, super novel. It might not be like, shaking the foundations of reality type of things, but it's like, hey, this is cool. It's research. It's interesting. And I just want to show you guys that stuff, like show you guys that stuff as it's going along. That's kind of the point. I have a question. Why did that not work? Let me scroll up really quick. When we created the pset is equal to particles, did this run initialize? Oh, that ran because we ran Galilee.initialize. All right, that's fine. So we're going to run it one more time, but this time we're going to do Galilee.find accelerations. There we go. This should run. And then we're going to run the next step after that. But yeah, so we're trying to do, like, I basically started an open research company, and the point of this stream, the point of my YouTube channel, the point of everything is just to, you know, show research in a way that's open and engaging, and hopefully allow the community to come together and just like kind of chat and like talk about the research that we're doing, like do new stuff together. That's kind of the whole thing. If that sounds interesting to you, you know, obviously, please feel free to follow. I'm genuinely trying to make this work as a career for the next year. So I have about 12 months from now to make this happen. I'm going to be putting a bunch of, you know, new YouTube content out soon. I want every single video that I put out to be like fundamentally groundbreaking, like just be like, hey, this is something you haven't seen before. I guarantee it. Here's the new stuff that people have never done before, this type of thing, you know? And that's kind of what we're doing, just new stuff people haven't seen, and that's the goal. Only dot probably Verlet is what I want. I think it's just Verlet integrator. Yeah, Verlet. And then we want to do pset1, pset2, and dt. And dt here is just going to be like, like 0.1 or something. So pset, and then pset2, and then 0.1. And I think that's going to run. Yep, so this should be report 5, and then the last one should be report 6. And that's just going to be us testing this bit in here. Now, what I'm afraid of is that like this shouldn't be the case, but what I'm afraid of is that like the fact that we're kind of masking, like we're passing around function pointers and stuff might run into an issue. I don't understand how that would, but maybe that's causing some overhead that I'm not really paying attention to. There's just a lot of like kernel launching events that take time, and I just want to make sure that we're not, at this point, you know, we're so far from like kernel launching, like time management that I think is kind of fine. But I'm hoping to get to the point where like, you know, we actually care about like the time of a kernel launch, and this is something we have to optimize and stuff. Okay. So we should have our 5 reports, and we're going to take a look at each of them and figure out how that plays in with the big report that we saw before. Okay. So let's start with report 1. So we're going to do nsite sys, and let's do report 1.qdrep. This is going to be the creation of a bunch of particles. So let's go here, CUDA API, show an events viewer, and you see here, this is literally just the first line in the code. So this is this line in here. Let's just make this huge. This line here, initialize, particle number, dims, all this kind of stuff. So what this is doing is it's creating a set of positions, a set of accelerations, and a set of velocities, and it's copying that over to the GPU. And as you can see, it is literally just allocate, and that's it. Hardware to device, hardware to device, hardware to device. Good. That's what we expect. Okay, now report 2, open report. I need to go back to directory. Report 2.qdrep. This one is the second line here, where we're copying the positions, velocities, and accelerations to a new device. So what we should see here is a device-to-device asynchronous call. Let's take a look there. Show an events viewer. And so we should see, yep, 3, it should be 3 allocate, D to D async. So we have 3 copies from one device to another device. Good. That's what we want to see. File, let's do open, and we're going to do report 3. So this one is, what is this one? This is the definition of a temporary acceleration. This one should just be literally just, host to device. So far we've seen 4 copies from a host to device and 3 copies from a device to device. Perfect. We have a lot of memory allocates between that, so that's 6, 7 memory allocates, which is fine. And so this should be all the memory allocation. If we see any memory allocation from this point, we're screwing something up. Yes, that is true. We should see no memory allocation from this point forward. So let's do file, open, and we're going to do report 4.qdrep. Let's take a look here, show an events viewer, and we see QEvent create. That's something. But you do see the bulk of this computation is in the n-body interaction here, and we do not technically see a QEvent allocate, but we do see QEvent create. Let's go take a look at the durations here. The bulk of this is going to be in the context, and we do have a synchronize in the context, so that is why this is taking a while. So if we were to remove that synchronize, things could be quicker, but I don't think we can, otherwise we get different results. So good, we don't see any allocates here. Yeah, we do see this QLaunch host function here, which is taking 15 milliseconds. So this is what I was saying before. Every time you launch a kernel, there's that little bit of latency with a CUDA launch, which you do sometimes have to take into account. But this time, like we're talking about 15 microseconds versus 3.4 milliseconds. So we're literally talking about like 1%, like 0.1%. Oh no, like 2% is what it is. So 2% runtime. And as you ideally, you minimize the number of launches so we can find a way around that, but right now we're not at that stage. So file, open, good, we're good so far. Report 5, there we are. That's what I was looking for. CUDA memory allocate. Where is the CUDA memory allocate coming in for the Verlet integration? So what we can see here, which is super interesting, is that the GPU Verlet and calc velocity here, there is a memory allocate in the calculation of the velocity. That's where this is coming from. So that's why we're getting so many memory allocates, because we're also memory allocating every time we're calculating the velocity. So let me try running this one more time. And let me try running one more time with calc velocity equals false, because we don't need it for Verlet integration, which is why that's happening. There's probably a way around it. There has to be a way around it. There has to be a way around it. Yeah, okay, good. This is what I wanted to see. So we found the memory leak, as it were. So we found that. This also explains why Verlet integration took so long, which is good to see. But also, look how messy this is. Like, it's super messy, because we have all this, coup wait event, all this kind of stuff. Okay. File, open. The last one is just setting everything to 0. I really am not expecting too much here except for a single broadcasting operation, which is literally all it is. It's just CUDA synchronize broadcasting operation. That's it. Okay, perfect. You know that the CUDA synchronize is 22 microseconds, whereas the duration of the actual broadcast is 2.14 milliseconds. Again, we're really splitting hairs here with the milliseconds and microseconds and all that kind of stuff. I just wanted to say, good. So far, the memory allocate that we're looking for is in the Verlet integration. Easy to find. And this is why, doing these types of benchmarks or performance tools, performance analysis is actually quite useful. So if you guys noticed yesterday, or even earlier today, when I was running with a lot of particles, we ran into a situation where the memory of my GPU was just flooded, and we couldn't figure out where that was coming from. The answer is it's probably coming from this velocity calculation and or the generation of the temporary accelerations. The reason that happens is that Julia is not manually memory. It uses a garbage collector, right? And the garbage collector works perfectly well on a CPU, but unfortunately it doesn't work very well on the GPU. Even if you do manual calls to the garbage collector on the GPU, it still is not particularly fast. So what happens is every time you allocate something, right? So you'll allocate something, like let's say you have a loop through 1,000, and every one of those 1,000 iterations will allocate some data, right? Well, that data that's being allocated will not be removed before the next iteration hits up. And so what could happen, and what used to happen a lot with Julia GPU ecosystem, is that these kind of empty arrays would just start flooding your GPU until basically all your memory is used, right? And now the way it works is it will stop any execution for a while. It's just a pain. Garbage collection on the GPU should always be done manually, in my opinion, but that's just not how it's done here. So because of that, the garbage collector just kind of fills up with data, and that's an issue. So what we need to do is basically modify the velocity, the calculation of the velocity, so that it doesn't have that allocation in it, and we're going to do that right now. It should be pretty quick. Good. I'm happy to see that, actually. So what we learned there was actually a lot. What I learned, oh gosh, look at that. My GPU is just struggling, isn't it? Okay, what we learned there was that, sorry, give me a second. So what we learned there was a couple things. One, all of those allocations, the bulk of those allocations were coming in the initialization step, which is great. The other thing that we learned was that the velocity kernel, the kernel to calculate the velocity, actually does take too much time, and it actually allocates too much data. So that's what we're looking at. So they optimize really well, the kernel launches. I think so as well. Garbage collection on the GPU. Yeah, so it's not great. What does Monka S mean again? Sorry about that. I don't know if that's good or bad. Is it actually managing memory on the GPU from the GPU, or is it just from the CPU forgetting to free the GPU memory? I gotta be honest, I don't know how the garbage collector works on the GPU. I know it kind of works, but I don't know exactly how it is working. I'm not sure if it's like a separate kernel launch, to do the garbage collection or something like that. I really don't know. I think it's trying to like compile the GPU, the garbage collection ecosystem onto the GPU. So I think it is run from the GPU. It's a nervous, slightly scared face. Oh, I guess I can only see it in like certain Twitch browsers. I couldn't see it on my chat over there. Okay, so let's go ahead and mess with this then. Quit here. Okay, frog face with sweat rolling down the forehead. Oh, I see. Okay, Monka sweat is what it is. Good. So let's go VI. Is it only like better Twitch TV, BTTV, or whatever? I know that's a thing. I've never used BTTV. Also, I've got a question for you guys. How do you guys find new streamers on Twitch? Like, what do you guys do? Typically, I only watch streamers that have been recommended to me by other streamers or chat. So like, you know, I sometimes I'll browse on art or science and tech or something like that. But for the most part, I only watch people who like someone else has rated or something like that. And I'm curious to see what you guys do. Like, how do you find new people? Like, do you just like look at who's top on Twitch and just go through that? Or do you look at what Twitch recommends in like the sidebar? I don't know. I've actually been wondering this myself. I feel like the usability of Twitch is not particularly high. Like, you know, if I browse just chatting, I feel like, I don't know. I feel like I don't know even what to click on. And like half the stuff isn't even in English. So it's like quite difficult to find stuff. Like I can usually find stuff on like art or something, but I don't know. I was just wondering what you guys do. Okay. So let's go ahead and go into VI source, forces here. And let's see, where's this? So here it is, right here. The temp acceleration, repulsive gravity, where is it? It's down, where is it? End body for lay. Here it is. So in this guy, calc velocity, this is what it is. Perfect. We have a temp velocity. And let's see, how does this, so this is the problem right here, where this allocation of the temp velocity is the thing that's taking so much time. I clicked on science and tech and saw you were programming. Ah, cool. Okay, well, that's fair. I started watching back in Justin TV days, like Destiny and Soda Poppin'. Oh, I didn't realize they were that old. I didn't realize they were like constantly streaming since the Justin TV days. That's interesting. I was just wondering, like, so I guess Vladimir, like, what are you expecting to see on the science and tech category? I guess is my question. Like, do you expect to see like programming streams, for example, are probably going to be on software and game development, right? So nowadays, if you're looking for like heavy, you know, C++ content or whatever the you know, like language specific content you're looking for, you can probably find that in the software and game development category. So in science and tech, what exactly are you expecting? So I guess part of the reason I'm asking this is because I really do feel like the science and tech category on Twitch has a, like, I don't know how to put it, but it has a possibility. There is a potential that the science and tech category on Twitch becomes a haven for people doing research, right? So it could be you go here and you see people doing biology research or chemistry research or physics research or whatever kind of research. And I think that'd be super cool, going on Twitch and finding a bunch of people who are just like doing groundbreaking research. Again, maybe it's not like super groundbreaking, but something new, like open research. I think it'd be super cool. And I'd love to see that. And I just wonder, do you guys use tags, for example? Like, I find I use tags somewhat frequently. Like if I'm looking for Linux content, I'll use a tag for that. I don't know. I guess that's the other thing, right? Whatever piques my interest in whichever category I'm browsing, that's fair. High-level programming exposure is probably my interest. That's fair. I feel like there's so much potential. People doing chemistry, mixing things, or doing physical stuff, or geologists actually going around to rock formations. Right. And this is, I know I'm going to ramble about this. I'm sorry I'm rambling. Just deal with my rambles. Let me go to Twitch right now. Sure, I'll just go to my own stream. And go to following, let's go to categories, and let's go to science and tech, which is down here. Perfect. So if you go to the science and tech category right now, like, oh, this is probably fine, but it's not clearly, I guess it is in English, actually. I don't know if I know this. Oh, Deadmau5 5. Is this actually the guy? Like, isn't he like popular or something? I have no idea. But you've got Bird Box. This is quite useful. But like, you got things like Live Earthquake 24/7. It's like, well, okay, that's science and tech. Sure, I agree with that. But also, it's like, is it like actually what you're looking for when you go to content here? And then you got Portuguese, French. So like, really, top English streams. You've got this guy. I don't know who it is, but I know he's popular. And then you have for English streams, you have literally, I'm the next English stream. So if you're looking for an English stream in science and tech on Twitch, I'm number 2. Woo! Anyway, Deadmau 5. What is he known for? Isn't he music? I thought he left Twitch. He does touch design stuff, visual node based programming. I'm a huge Deadmau 5 fan. He's a DJ. DJ. How do you pronounce it? Is it Mouse? Is it Dead Mouse? Interesting. So should I raid him at the end of stream if he's still live in an hour and a half when we're done? Let me get some water. Maybe I should. Why is he on Science and Tech? Oh, you put an emote in there. Interesting. But yeah, why is he on Science and Tech instead of like another category, like just chatting or music, for example? Music would be great. Okay. So let's go ahead and see if we can figure this out. So right now, the calculate velocity kernel. Let's take a look there. Calc velocity here. Reason of position 1, position 2, velocity 1, velocity 2. And I think we can literally modify this so we don't use the temporary velocity at all. And this is just velocity 2 is going to be equal to velocity 1 of TID. And the velocity 1 is here because it's independent of the previous velocity. So we can just do this. And so we're reading in the two different positions. Position 1, position 2. We have the velocity 1. Should be fine. I think that's fine. So let's just go ahead and remove the definition of the temp velocity here. dd there. Go in here, remove the copy here. There we go. And this should be fine. So let's go ahead and try running that really quick. We're going to do another profile. Oh, actually, let's just run it really quick. Julia _ project. Okay. What do we have? I missed a lot of stuff. Electro DJ from Halifax, because he's a weeb. Probably to be edgy, because his music is electric. Oh, interesting. No shade though. It's good. That's fair. Maybe I missed this, but are you doing this for work or is it for your personal interest? Sometimes his streams are just analog signal processing. Interesting. Actually, that sounds quite cool. I'd love to do analog signal processing streams. Yeah, so I see Yogi. That's actually a good question. Let me run this really quick and I'm going to answer that. It's not long, but it's kind of, I need to word it in a way that doesn't make it sound like I'm a huge loser is what I need to do. So let's go ahead and do Galilee.run and let's just give it a go. Grid extents 2, sure, give it a go. And then we're going to profile that as well. But actually, like, I could rate him at the end of stream if he's still live in like an hour or so. He's an EDM producer, not DJ. So EDM is electric/digital music, I guess. I gotta be honest, I know nothing about music. Genuinely nothing about music. If you ask me anything about pop culture, I know nothing. I'm so bad with pop culture. Like, I don't even know Star Wars references. I'm really bad. Okay, so this runs, everything should be fine. Electric dance music. Oh, interesting. His label, Mousetrap, also signs a lot of smaller artists, which is cool. Oh, actually, yeah, that is quite cool. Ooh, my eyes are starting to bug out. There's a neat video showcasing his setup on Linus Tech Tips channel. Oh, okay, cool. Okay, so let me go over here, open up the, ooh, I missed it. I missed it again. Here, that's what I'm looking for. Perfect. I think the video and audio is in sync. Okay, right. Journal new page before. Okay, so what exactly is this? So you're on a Twitch channel called Leos Labs, right? Here's the thing. So I'm Dr. James Schloss. I finished my PhD at the Okinawa Institute of Science and Technology in December 2019. Since then, I actually spent a year working at MIT, working on the Klima project, which is a climate machine. And then since then, I actually took a break from doing, well, not really a break, but I stopped doing research in a sense in 2021. It wasn't because I didn't want to do research. I still love doing research. It was just that I found that the research I was doing at MIT was not, it didn't fit me very well. During the PhD, I was constantly struggling between physics and computation. We had that discussion earlier. And I found that really and truly, I was very burnt out of physics. I loved doing computation. I loved GPU engineering. I loved doing parallel processing. All this stuff was great. But the physics itself was very tough. It felt like, I almost felt like I was you know, you get kind of nauseous when you look at something. That's kind of what I felt like when I was doing physics, right? And so when I entered MIT, I was fully expecting, since I was working with the Julia Lab and I was working with Klima, I was fully expecting to transition more towards a computer science role. And in particular, I wanted to do a lot of computer science research in the area of computational science and work my way towards like graph methods and like computational, computational geometry and stuff like this, and maybe even computer graphics, that type of thing. But that just didn't happen. It ended up being that when I was working at Klima, the project was great. Like, genuinely speaking, if you want to work for it, please do. I was basically a research software engineer at the time. And I just didn't really like that role. I didn't like doing software development for a physics project. I wanted to do novel computer science research, right? And so what this is, Laos Labs, is an attempt to do the research I wanted to do. So for the next year, I saved up enough money that I'm actually just going to try my best to make Laos Labs be financially stable. It's an LLC in Alabama. I just started it up, and it is a purely open research company, right? So starting this week, I'm doing like daily live streams on Twitch. I technically have been doing live streams on Twitch for a long time, but like starting this week, I'm actually making sure it's every day, and I'm actually making sure it's like a relatively long, like 6-hour stream a day, just to put like at least 40 hours a week exclusively in streaming. And I'm really trying to make sure the research is open, engaging, interesting, and that people can ask questions about like how research is done. That's the point of the Laos Labs initiative. After a year, at the end of this year, we will have published a few papers. We will have tried to see if we can make the research engaging and open, whether this can work as a model or not. I will hopefully have applied to a couple grants and see if those have worked out or not. There's going to be a lot of things that will happen by this time next year. And if it's successful, we keep going. We keep pushing towards an open research lab. If it's unsuccessful, then that's okay. We take a step back. I apply for postdocs in academia, and I try it again when I'm a professor and I have full control of my lab. So that's the idea. That's the Laos Labs channel in a nutshell. That's what we're doing. If you like that, feel free to join. Thank you so much for the subscription. Really appreciate it. But of course, I'm not asking for subscriptions here. I mean, I kind of was saying yesterday that it'd be nice if I could, but like, look, I'm not asking for subscriptions. I can find the hardware I need to run these simulations on. I can figure out how to make it work. But ultimately, I'm really, really trying to make an open, engaging research lab that uses the community to just kind of do cool stuff together. That's the point. And so, yeah, I've been streaming for 4 hours and 30 minutes. I might be a bit tired. I might not have described that as well as I could, but that's the whole point. I just want to show that research is cool and that it's something that I wish more people would do, and that it's not this thing that only academics do. It's this thing that everyone can understand if they just take the time to like learn about it and try to figure it out. Anyway, that's where I'm at. I know it's kind of wishy-washy. It's not really like a perfect answer, but that's what I got. I'm tired, but research is cool. I'm tired right now because I've been streaming for 4.5 hours, and my stream stamina as of last week was like 30 minutes, and I would get super tired. Somehow, I genuinely have no idea how, but like I caught a second win this week, and now I'm able to do like 6-hour streams, and it's like fun. I really enjoy it. It's super enjoyable. Like, I can talk to people. We're having great conversations, but somehow, like the week before that, I literally would stream for 30 minutes, and I'd be like, oh, I'm so tired. I don't know what happened. You'd be surprised as much as I do if you tried to do research in a third world country. Right. That's totally fair. Are you sure using Alt-Tab to switch between apps? Does Alt-Shift-Tab not do the same, but backwards? Oh, I have no idea. I think it does. Alt-Shift-Tab. It's just Alt-Shift-Tab is like hard to press. So that's why I always do Alt-Tab instead. But you're right. You're right. Alt-Shift-Tab works. Thanks for that. As much as I am. Let's see. You'd be surprised as much as I am if you tried to do this in a third world country. Right. As much. Yeah. Right. Very cool that you are sharing the research here and make it transparent. Right. So for the record, the interesting thing here and the research that we're doing is not in the 4D galaxy. The 4D galaxy is kind of like a clicky thing. It's something that I think will do well on Twitch and YouTube and stuff like that. The interesting thing here is that I'm hoping that when we're doing the 4D galaxy, we actually run into certain problems that I know are going to be problems. Like the reason this paper is right here is because I'm actually taking this as a model for, like, it's from 2014. So there's better models now. But the reason this paper is right here is because it's an interesting thing. It's like, oh, okay, these guys did a super big simulation, but there's a lot of things that we can make better about it. And so we can improve their simulation by doing better clustering methods and stuff like this. And eventually it will hopefully build its way into like better like color quantization methods that can be used in computer graphics. And essentially it builds itself. Like it will all build on top of itself. And I'm really interested in like applying these clustering methods that you find in computer graphics to these n-body simulations and seeing where that goes. It might not lead into a paper here, but there definitely will be a paper at the end somewhere in between computer graphics and physics. And I'm really interested in where that is. Is the paper public? It's on the archive. So this one's public. I'll go ahead and give it to you. 24.77, this one. You might, I think you can just click the PDF button. No, you can't. But if you Google this, you'll find it on the archive. Let me go here. Sorry. Just go to, oh, hello. Stop it. Just go to Google Scholar. Gosh darn it, every time. Okay, go here. Go to Google Scholar. Come on. Okay, so if we go to Google Scholar and we look for this, it should be apparent on the archive. Here. So here's the PDF on the archive. I guess I can just give you a link to that PDF. Sure. Let me give you a link to the PDF directly. I don't know how to do that, but, screw it. How do I just look at the archive? I don't want to look at the, here it is. Let's grab this guy. There you go. Perfect. There you go. I'm so sorry, but it is an interesting paper. They do a simulation of 18 billion stars or something like that. And it talks about how like you have to do the dark matter halo. There's a whole bunch of other really cool things about it that I find super interesting. But we're very far from doing this right now. We're literally on like day 4. And like you just saw, we just did some very basic GPU analysis and saw that I'm so stupid. I like ended up like creating data when I didn't need to. So we've got another like hour and 30 minutes left in stream today until 8 o'clock p.m., which is when I'm going to stop streaming. My stream times are going to be from 2 o'clock p.m. to 8 o'clock p.m. Central European Standard Time. I think that's the time zone I'm on. So that's going to be my stream time. And yeah, let's just talk about what we're going to do next. So I'm going to do Control D here. I wrote down some notes and I just want to make sure we did all of those notes. So for kernel abstractions, we checked to see, yes, we have to do some kernel abstractions work next. Perfect. Okay. Let's do that then. Yeah, let's do that then. Okay. So I'm going to go ahead and commit what we have, git status dot. I'm going to put the Qt REP files in the git ignore. Let's do Qt RDP. Okay, git status dot. Sure, git add dot. Git status again. Perfect. Git commit. Commit. And we're going to do -m. Oh, come on, I can't type. I just can't type at all. Git commit -m. Okay, and we're going to do, we did GPU performances and we also did projections. So projection to 3D and performance fixes. Okay, there's still a lot of things about the code I don't like, but we'll fix those later. So git push, origin, development. Perfect. Okay, so let's talk about the next thing. In fact, let me run this one more time. Let me do a very quick at time here and just see what happens. So let's do Julia --project. And I'm going to do an at time of 4,000 particles, I think. Yes, that's what I want to do. So we're going to do using these guys, do a single time step, and then we're going to do a profile. And I think, based on what we just did, we should have cut the time for the GPU computation down. So it's now faster than the CPU computation, I think. So I'm going to go ahead and check that. So we're going to do Galilei.run. This is for 1,000 time steps. That's fine. And we're going to check it. In fact, let's just do it right now. Let's just do the CPU versus GPU and see what we get. So let this run, and then I'm just going to quit it. And then we're going to run with, I guess, 12 threads. Yeah, let's run with 12 threads. Yeah, okay, that's what we'll do. We'll run with 12 threads, and we'll check that versus the CPU or the GPU results. So Control D. Julia --project, and we'll do -T12. Okay, let's do using this guy, We're going to run some simple code, and then we're going to just do some quick tests between the CPU and GPU. I think without the allocations, our GPU code will be faster than the CPU code, but we're just going to double check. And then after that, we're going to talk about how to make the GPU code even faster. In particular, we're going to talk about parallel summation. And I think we're going to spend the next hour messing around with kernel abstractions just to see if parallel summation actually works or doesn't work. I don't know. This will help us learn what we actually have to do to make the code better, essentially. Okay. So let's go ahead and run the Galilei.run for 1,000 time steps. This will just do all the pre-compilation. We're also going to run it on the CPU as well, just to do the pre-compilation pipeline on the CPU. And then we're just going to do a few different at times for 1,000 time steps for the CPU and GPU for different numbers of particles. And we're going to see what happens. So I guess we'll do the CPU runs first, maybe. Oh, and note, we're not outputting anything to file. So this is specifically just a runtime. Okay, so let's run this with the CPU array as well. And then we should be good to go. All right, run that. And now we're just going to @time some stuff. So let's just do @time, and we're just going to go up in powers of 2. So take this last guy that we just ran, go here and @time. And we're going to start with, let's do 16. Well, let's do 128. Okay, so we're going to run that, see how long it takes. 0.22 seconds. Okay, 0.11 seconds. So let's do 256. Perfect. 0.14, 512. Okay, 3.44. Okay, 1024. Okay, this should take about 1 second. We're starting to chug a bit. So 2048. Okay. This should take 4 seconds, I believe, if it scales. Yeah, about that. And now this should take 4,196. Now, what is it? 4,096. Run this, and this should take 16 seconds, about. And then we're going to do the same on the GPU and see what the scaling is like. Also, we're going to see at what point my GPU starts to chug. So if this stream goes down, it's because my GPU is kind of struggling a bit. Also, I needed to do one last thing, which is htop. So let me run htop here. Let's run it again just to double check. So that took about 13 seconds. Like I said, it should have taken about 16 seconds. And you can see that we're using all the threads on our CPU, which is great. We're not using too much memory, which is fine. I don't think we'd expect to be using too much memory. So next what I want to do is run, I think I'm going to run NVTop. We're going to see if we can get that one to work. A lot of people really like NVTop, but I just don't. To me, NVIDIA SMI is just slightly better. Okay. My computer was chugging, just moving that window around. I have been thinking about switching to Wayland recently. I wanted to 10 years ago, but there was no OpenBox equivalent in Wayland. I know there's Sway, which is kind of the same thing, but maybe I should switch to Wayland because it probably doesn't chug as much, you know? Okay. So now we're going to do the same thing for the GPU. So we're going to start with 128 and go our way up. So 128, we're going to do CUDA.@time. And we're going to run with the cuArray. Yeah, so Wayland is another compositor for Linux. 0.4. Is it really that long? Interesting. It's another compositor for Linux. Like X, for example, the X server is what displays all my windows and stuff like that. So it's the fundamental underlying thing that all the windows are displayed on. So Wayland is another one of those things. But as you can imagine, if you completely update all of your graphics, it means that there are a bunch of functions, a bunch of pieces of software that don't work on Wayland. So you will usually use some extension layer like XWayland or something. So GNOME, for example, which is a very common front end, uses Wayland, I think, primarily nowadays, and I think also does KDE Plasma, but there hasn't been an OpenBox port. If there was an OpenBox port to Wayland, I would probably be using that. Anyway, so let's keep going up. So 128, we're going to do 256 here. Okay, that's twice as much time. We're going to do 512 here, which is going to be 1 second. So now let's do 1024. Ooh, this is actually taking some time, isn't it? Let's see, what do we want to do here? 1024 is 2 seconds. So let's do 2048. 2048 is going to be, look, it's going to be 10 seconds, I think, which isn't great. I mean, that says that the CPU version, oh, actually, that was quite quick. Let's do 4096. This might be actually better than I thought. Okay, let me also see if my GPU is chugging. Oh, it's chugging. It's chugging a bit. my FPS just dropped. It's now at 15 FPS. It's okay. It's fine. I'm just kind of watching. Okay, so that took 12 seconds. Okay, so what you're seeing here is that the CPU actually started way faster. So let's take a look at the CPU results first. Sorry, that's the archive link. I don't know how that appeared. So CPU results are going to be these guys up here. So all these CUDA at times here. And then the GPU results are down here. So what you saw is that the CPU was originally at 0.11 seconds, then 0.14, 0.34, and then slowly increased until you got to 4096, where it's 13 seconds, right? If you look at the GPU though, it immediately takes longer. The reason it's taking longer is because if you're copying data to the GPU, all of those CUDA memory copies, they just take a while. Like we just showed that in the profiling results. They take a while, right? But if you notice here, the difference between this 4.5 and this 8, it's actually not too bad. Again, the main thing here is that you're copying more data, right? So as you go further down, you see that here we're at 12 seconds, whereas up here, we're at 13 seconds, right? And so we're actually running into a situation where as you start scaling up and as you start using more and more particles, the GPU starts to win out. And this is the core reason why you use the GPU. This is kind of what I expected. I thought the GPU would kind of win out actually a bit earlier than that. Does it win out earlier? No, it doesn't win out until 4096 because this is 4 seconds, whereas 2048 here is also 4 seconds. So at 4096, about this scale, then the GPU wins out. So what we need to talk about is kind of other ways in which we can speed up the computation on the GPU, because right now it's not really worth using the GPU at this scale of computation. By the way, Anonymous123494, thank you so much for following, really appreciate it. Again, guys, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know, and I'll totally address it as soon as I see it in chat. But this is good. I just want to check the profiling results here. For some reason, I thought the results yesterday were better for the GPU. I'm going to have to take a look at the VOD again, but I really genuinely thought that the results yesterday were better. Let me try polling that commit. Yeah, let me try polling that commit, see if we get better results. Because that would be super surprising if after today, spending what, 4 hours on this, we actually got worse results at the end. Let's do Control D, get log, and let's see what we got here. So allowing more generic function interface, and then adding naive parallelism with kernel abstractions. This guy. So we're going to do get checkout. This guy. And let's take a look at that for the GPU. So we're here, let's do Julia -- project. Oh, I'm worried now. I'm super worried that we're actually like messing things up somehow. No, I don't see how. I don't see how this could possibly be faster unless the fact that we're sending function pointers back and forth led to. But we looked at the kernel launches. It wasn't like it was particularly long. Okay, let's just do using CUDA Galilee, and we're just going to run the cases for the CUDA app profile one more time and see how it goes. My GPU is going to probably chug a bit more. But we'll just see what happens. So we're going to do Galilee.run here, and let's just see what happens. Again, the reason I'm moving my mouse around screen is just to see how much it's chugging. I'm sorry. I could also just look at the FPS counter over there. Okay, so we got this going. Now let's do CUDA.app profile for, let's start with 128. I'm expecting this to be way longer, honestly. It should be like a second. Yeah, it should be way longer. Yeah, it has to be way longer. It is in fact way longer. The last one took 0.4 seconds. This one is 17 seconds. Let's try running this at, let's do 512. Interesting. I thought it was way better yesterday. Wait, how did that happen? Wait a minute, what? Let me try running at 128 again. 120 is 0.4 seconds. Okay, so now let's try going up the ladder. So 128, then we're going to do 256. 0.7 is actually kind of the same. 512. Okay, 1.4 seconds. 1024. Okay, I'm surprised it's so close. In fact, it looks like it might be faster. 2048. No way. How is this faster? Oh no. Am I 4 seconds? It is faster. After all that work, we're slower. No way. It's going to chug a bit. Actually, it's not even chugging that much. Not as much as last time. No way. 12.8 seconds. Okay, we're not faster, but we're not slower. 12.7 seconds. Literally 0.1 second different. Okay, so we did nothing. We literally did nothing. I think the... Fine, whatever. We're the same speed as before. 4 hours of work, and we have literally done nothing this stream. We are the same speed as we were when we started. We're getting the same results as we did when we started. Sure, we can now do 4D and project down to 3D, but like, really? Oh man, let me get some water. That's just disappointing. I was really expecting to be faster because we have less allocations. How are we not faster? We have less allocations. Yeah, we have less allocations. So if we have less allocations, we should be... This is kind of blowing my mind a bit. All right, let me get some water. Maybe we're just at the scale where the allocations don't matter that much. So here we have allocations of 12 megabytes, CPU allocations, and then 1.01K GPU allocations, 31.46 megabytes. Let's check down here. It is literally 125 megabytes. We're worth 4 times as much allocation time. 252.44K CPU allocations for 43 megabytes and 4.01K GPU allocations versus we're literally 1/4 in all of these metrics. 0.23% management time. Where's the garbage collection time? Oh, actually, maybe we don't have... Okay, 0.62% memory management time. 0.23. Okay, fine. Fine. That's the reason. The memory management time was only accounting to 0.4% of the runtime, which explains why we're like 0.4% faster. Okay, fine. We are technically faster by 0.4%. We spent 4 hours to get a 0.4% speed up. And yes, I'm pretty sure we're doing less allocations. That's what this is showing me. So with the at time, it shows us the allocations here. And so I was just double checking this allocation set versus this allocation set. And you can clearly see we're going from like 252.44K CPU allocations for 43 megabytes. And also 4.01K GPU allocations at 125 megabytes down here for the previous branch versus about the same CPU allocations, but way less megabytes. Actually, wait a minute. 1.01K GPU allocations at 31 megabytes versus 12.0 megabytes. Oh, yes. Okay, I see. It's 31 megabytes versus 125 megabytes and like 10 megabytes or whatever versus 43 megabytes. So we're about a quarter as many allocations. Yeah, about a quarter as many allocations on both the CPU and GPU. So technically we are doing less. Okay, well, that is simultaneously disappointing and disheartening. Anyway, let's keep going. Okay, so we're going to do Control D here. Let's do git checkout head, I believe. Sure. Okay, so we should be back git log with the latest changes. Adding naive parallelism with kernel. Git checkout master. Obviously the head, development. Obviously the head was at the head that we just detached, you know? Git log. Now we should be projection from 3D and performance fixes. Perfect. Okay. So let's go ahead and update on what we've done so far and where we need to go. So I'm going to just, I guess, put it here. Why not? Okay. So today, what have we done? We started with the ability to do an n-dimensional galaxy simulation. We spent a lot of time working on kernel abstractions. In particular, we allowed for different forces, so different force integrators, different forces, not force integrators. So this means that we could run with gravity, but we could also just read in our own force. So we could do a repulsive force. We could do a number of different things. So this allows for us to write extensible code by reading in a function pointer that allows for us to basically use a different like force argument. So for example, for 4-dimensional gravity, we might want to do a 1 over r cubed potential. In fact, we might just do that simulation now. Let's do that simulation now. Yeah, let's run with 4D gravity and see if that simulation changes things. Why not? So we did that. The other thing we did is we actually looked at kernel performance and we removed a lot of unnecessary allocations, allocations, which resulted in a 0.4% speed up, which is negligible. But hey, we did it. It's something that we need to look at a lot anyway, so we'll look at it later. Aeroduct, thank you so much for following. Really appreciate it. Okay, so stuff to do next is GPU optimizations. So we're going to talk about optimizations of kernel optimization, kernel optimizations. Now that I'm reasonably confident that at least the workflow makes sense, now I want to talk about like performance optimizations and stuff like that. So we looked at the performance, now we optimize on that performance. What do we have here? Are you sure you have less allocations? Sorry if it's obvious, but are you ping-ponging to CPU every step maybe? No, so we obviously have, we have to run the kernel launch from the CPU. Actually, yeah, let's do both those things before continuing. So one, let's go ahead and add in a 4-dimensional force. And two, let's show the profiling results one more time for a single time step after we did the reduction. So let's do that now, actually. So we're going to nsys launch Julia --project. Sure. Okay, now we're going to do using CUDA Galilee, and we're just going to do a super quick benchmark or performance test just to show that we're like the kernel launches are coming from the CPU, but we're definitely not copying data back and forth from the CPU and GPU. Yeah, that's definitely not happening. We actually double checked every single kernel before to ensure that we had the exact number of allocations that we expected. That is to say, 3 allocations at the start, where we create the position, velocity, and acceleration vector for each particle, essentially. Then we have another allocation, which is from device to device, where we create a second set that we need for Verlet integration. It's an unfortunate side effect of using Verlet integration for this. Then we created another allocation, which was for like a temporary vector to work with. And then that's it. Those are the only allocations we had. So with all those allocations in mind, we actually limited those, and we made sure that the data was always on the CPU. So we weren't ping-ponging back and forth with data back and forth from the CPU and GPU. There is a potential case where we do need to go back and forth from the CPU to GPU in the case that we're outputting data every time step, but we're not doing that in the profiling results. So that did not need to happen. But yeah, it's actually a very good question. Like whenever you're looking at GPU performance, I mean, I mentioned this a couple times, but whenever you're looking at GPU performance, the number one like way to make sure that you're actually doing a you're making performant code is to minimize the number of transfers between the CPU and GPU. So that's like the perfect question to ask. Okay, so let's go ahead and do Galilee.run. We're gonna run this really quick, and then we're just gonna app profile. Let's do it for 1,000 steps and then again for 1 step. Oh, that's a single array. Let's do a coup array. Okay, so the other thing we need to do, I'm just going to go ahead and write it down. So we're going to do profiling one more time, but we're also going to do 4D force. So let's go ahead and add that in. I think it's going to be like 1/6, like 1/6 r cubed or something like that is what we're looking for. But it doesn't matter. We'll just do, 1/6 r cubed is what we'll do. Sure. Okay. Sorry about that. We're going to let this run, and now let's run it one more time. This time we're going to do CUDA.appProfile. Where are we at? Profile. Sure. Okay, and then we're going to do it again for the single time step. And take a look at that. Because actually, you're right. After I fixed the performance stuff, I didn't actually look at the profiling results one more time. It's something I really should have done, but I didn't. So. Also, I have been streaming for 5 hours, so if I sound a little bit tired, that's why. Again, as much as I'm trying to like increase my stream stamina and do more and more streams and stuff like that, I'm still getting used to getting the hang of doing these longer streams. So forgive me if I'm a little bit like, if I'm not as engaging as I normally am. The next hour I might be a little bit quiet just because I'm getting a little bit tired and honestly a little bit hungry. But I'm going to do everything I can to keep streaming until 8 o'clock p.m. I'm not going to end early because I genuinely am trying to get this stream time from 2 to 8 to be my normal time. So that if anybody wants to find me, they can find me during my office hours here from 2 to 8 p.m. Tomorrow is Saturday. I will say that I might start a little bit later. I'm going to still try to do this stream, but I might start a little bit later because my wife is coming back from a conference and she might be coming in a little bit late, so I might need to pick her up or something. So with that said, that's the only reason why I might be missing it. So like if something like that happens, if there's like a real life event that comes up, feel free to hang out on Discord. I'll go ahead and give you guys a link here. Feel free to go to Discord where I'll let people know on the stream chat if something came up and I wasn't able to stream during this time. Okay, so we got the profiling results. Let's go here, Control D. Let's run nsight sys one more time on, it should be report, I think 7 and 8 is what I'm looking at, QDREP. So this should be the result with 1,000 time steps. It's going to look kind of ugly. Yeah, it looks really ugly, doesn't it? But let's go here to show an events viewer, duration here. And it should be, yeah, the end body takes the longest, calc velocity is the next. And then we have a lot of allocates here. Okay, you might be right here, actually. Let me check something. Why do we have so many? Okay, wait. I might have screwed up. I might have screwed up big time. Where are these guys coming from? Wait. Why do we have so many? CUDA launch. Oh, I see what's happening. Yeah. No, these are all fine. These are all memory allocates. Now, where is the memory allocate coming from? What is this memory allocate for? That's my question. Where are these memory allocates coming from? This should be start time. Let's take a look at start time. Nope. What? Where's the start time? Not name. I don't want to go by name. Let's go ahead and remove from event viewer. Show an events viewer. Ah, come on. Wait. Where is our... I'm going to have to do something dumb here. I actually don't know how to fix the UI. Let me fix this. This is actually quite cool. Okay, we might spend another hour on performance stuff. Give me a second. This is actually quite interesting. Show an events viewer. This is now time dependent. And what's bothering me about this is that we have the CUDA memory allocate, H to device. Then we have the device to device. That's fine. And then we have H to device again. That's all fine. This is all fine. CUDA create, stream wait. Then we have the end body simulation. We have CUDA record, QEvent query, wait, launch host function allocate. So what's this allocate for? Where is this allocation coming in? And then we do another D to D async. Where is that coming from? Is this the broadcasting event? No, it can't be. Create, record, wait, create, relay kernel. So this is between... Wait a minute, we're doing something funky here, and it's something we definitely need to check out. So the way this works, let me just go ahead and take a look at this visualization again. Okay, so what's happening here? At any given point in time, one of these particles, there's two things happening in the simulation. One, we have to find the acceleration that the particle is feeling. The way this is done is by looking at every other particle in the simulation, because we're doing a fully end-body simulation, and basically adding all of the forces together to find an acceleration at the end. That's taking the longest amount of time. The next part, which is also somewhat difficult, is moving the particles forward one time step. So those are the two things that are happening in this simulation. So what I'm doing is I'm taking a look at the profiler right here, and I'm just going through event after event, and I'm trying to figure out what's happening with time. So it starts up here where we allocate three values. These three values are the position, acceleration, and velocity vector of our particles, right? Then we create a second set, which is necessary for relay integration. Again, so this is a device-to-device memory transfer, because it's going to be the creation of an acceleration, velocity, and position vector from an already allocated GPU array to another allocated GPU array. We have one more host-to-device async copy, which is going to be the creation of a temporary working vector to go with. We have QEvent create, QEvent record, QEvent wait, QStream wait event, and then we have the end-body calculation. This is the finding of the accelerations, and as you can see, it's 2.1 milliseconds versus all these guys, which are in the nanoseconds or microseconds range. We have QEvent record, which is going to be, I think, a profiler overhead. QEvent query, again, I think profiler overhead. QStream wait event, and I think all this profiler. And then we get this Q memory allocate. And this is what I don't understand. Where is this memory allocate coming from? That is a super interesting question. I'm going to zoom in. Let's just try to figure it out. This is a mystery. All right, so let's go here, because this means that there is here's the end body calculation that we were talking about before. it's interesting that these are so short now. Yeah, why are these so short compared to the n-body calculation? Why is this so different than when I ran each step individually? Okay, so let's go here. So we have that guy. Perfect, that's fine. GPU n-body calculation, context 1, perfect. I think I want to go to the next one though. So here we have, this should also be an n-body calculation. Calc velocity, this is n-body. Broadcast kernel, this is n-body. No, cuEvent record. What's this one? N-body calculation 2, perfect. So between that second n-body calculation, there should be a memory allocate right there. Oh, hello. So let's figure that out. So here's that, the broadcast kernel, this is it, right there. Okay, let me zoom in and see if we can figure out what's going on here. So here's the n-body calculation. Let me move over a little bit. So this is actually quite cool. So good thing you told me to look at this again. I'm actually quite interested. So this goes here. Then we have cuEvent record, that's this one. cuEvent query. Wait event, that's the end of the kernel instructions wait event. Launch host function. Launch host function. This is going to launch. What is this launching? It's going to launch the next kernel. And in the next kernel, there is a memory allocate. What are we waiting on here? What's this epoll wait for? Yeah, what is all this? We're still waiting. We're in the microseconds regime. Oh my gosh, this is crazy. Am I dumb? Where's this guy? Yeah, it's that way. Thanks for giving me a little heads up. Okay, that's fine. Async here. So I'm looking for the memory allocate there. Let's take a look here. Let's move over a bit. Okay, so there's the memory allocate. There's a device-to-device asynchronous copy. Am I dumb? No. Am I dumb? I am dumb. It's not a question. I know I'm dumb. So the memory allocate here, and then we have a device-to-device asynchronous copy. Where is that being done? This must be, it's just before it's a device-to-device asynchronous copy. Where is that done? All right, let's take a look at the code. I'm clearly doing something stupid, which is great. VI source, and let's go into forces.jl. So we call the n-body calculation, and then after calling the n-body calculation, where is that? That's down here. We find the acceleration. So we call n-body, which is just going to be a kernel. Then after that's done, we shouldn't have to do anything. So we now go to VI source simulate. So we're at the end of finding the acceleration, then we're launching the integrator. The integrator is Verlet, so let's take a look there. So let's go into Verlet here. And so we have this guy. So this is going to be the launch for the Verlet function. And basically we have a copy. Why do we have a copy there? What's going on? Oh no. Oh, that's so stupid. I can't believe we had a copy there. Oh, jeez. Okay. How do we fix this? So do we need that in the Verlet kernel? The Verlet kernel has a temporary position. Do we need the temporary position, or can we get away without it? We could send it to shared memory. Or we could just read in a temporary. It's the ease optimization part. Here's what I'm going to do. I'm going to do the following. I'm going to modify this. So everywhere we see temp acceleration is going to be fine in this file. And this guy, we're going to directly read in to Verlet, pset1, pset2, but also a temp positions vector. There we go. And that way we don't need the copy anymore. Oh, I can't believe there was a copy there. That's insane. Try to remove all the sleep 10s also. I'm sorry. I don't know what's going on. I had to get back here onto my phone's hotspots because my PC can't connect to my home Wi-Fi. My word. So actually, I have the same problem here where my laptop will sometimes just like disconnect all the time from the internet. It's fine if it's like directly connected to the Ethernet, but the Wi-Fi just doesn't work sometimes, which is a huge pain. So let's go ahead and put the temp positions in here because I can't believe I did that. No way. That's insane. Let me just go down here. So we have the temp position here. Do we update it in the kernel? We say position 2 is equal to temp positions here. So where do we define temp positions? Temp position is being read in as a copy. Okay, so it's already being read in as a copy, which is fine. Okay, fine. We'll just do the broadcast. Yeah, okay, that's okay. But I could have just done the broadcast here, where we... I think my router is like 5 meters away. Yeah, I have the same problem though. My computer keeps like disconnecting. Back in the day, this was actually a software problem with the router. And by putting on new software in the router, it would actually solve the problem. What was the new software? It was, oh crap, what is it called? It's like an open source variant of router hardware or router software. Crap, what is it called? It's... Oh gosh, my mind is going blank. I can't remember, but there's like an open source router like software thing that you can flash onto it that helped me, at least when I was, running into that problem before. So like my mom had the same problem where like her Windows device, just anytime she would connect to the router, it would actually like kick everyone off the network. And it would also kick her off the network. It was like this weird panic situation. I don't know what was going on. And yeah, so that was fixed by switching to this open source thing. I really don't remember what it's called though right now. All of the devices in the house can connect and stay connected on this Wi-Fi. Right, so what I was saying is that like it could be an issue with like specifically if you're using like Linux or something, it could be a problem with that particular operating system connecting to that particular router, and sometimes updating the software will fix that. It's fixed it, at least in my case. Like I had the same problem where like Linux, my Arch Linux device just wouldn't, OpenWRT, yes, that's what it is, where Linux just wouldn't connect and it would keep disconnecting and all this kind of stuff, but everything else would work. And then switching to OpenWRT solved it. So I'm not saying you have to do that. I'm just saying that it could potentially be the issue. So I'm gonna say temp positions of TID is gonna be equal to position 1 of TID. Doing it in the kernel is probably faster than doing it as a separate broadcasting operation. And then we do this. We have the temp positions being read in. So this way it doesn't matter what they're set as before. I'm going to modify this to be temp vector. Okay. And then we're going to do find accelerations on temp vector. 1 second. And then here we're going to read the temp vector in as well. Okay, that should solve it. It's my ISP router, so I can't update it myself. Right, I have the same problem here, where I also can't update the router that we have. So as much as I want to flash OpenWRT on it to see if it solves my issue, I can't really do that. So I'm actually in the same boat as you are with my laptop, in that I kind of feel like I need to buy a new one, but I'm kind of holding out until the Framework laptop is available in Europe. Or maybe I would buy it and then like have it sent to my parents' address when I get there, for like, I don't know, when I visit next time or something. I haven't really decided, but I kind of really want that Framework laptop. It looks really, really cool, especially as someone who always fixes their own devices anyway. Okay, let's go here. Let's make sure there's no other copies, because apparently I'm just a copy man. Okay, let's go here. Are you back from the land of the rising sun? I am. I moved from Okinawa to Boston, and then from Boston to Alabama, then Alabama back up to Boston, then Boston back down to Alabama, then over to Okinawa again, and then finally I landed in Barcelona. So I'm in Barcelona. That's what happened. I ended up moving like literally over the past 2 years. I've moved like 7 times. It's been insane. I said this before, but like, part of the reason I haven't been streaming or like I haven't been making content is just my life was crazy. Like genuinely speaking, I was spending like 6 hours a day doing like visa paperwork to go back to Japan over like, so I could visit my wife. It was like all this kind of stuff. I was spending so much time just doing absolutely inane, just nonsense, just so I could like live normally. So between MIT and just normal life stuff, I didn't have time to do the online content until now, I'm definitely settled now, and I'm actually quite happy that I finally, I realized this just the other day. This is the first time in literally 2 years where I can look forward and like plan for more than a month ahead. And it's insane. It's absolutely insane. That this is the first time, but also like I'm happy that I can, work on Leo's Labs. I'm happy that we can make this happen. I'm happy that we're finally moving and making progress in this direction, Does the router update itself? Sometimes they have updates you have to install yourself from their website. Yeah, that's also true. I don't really know. You could always have a processing. You can always have Raspberry Pi as a cheap router and your ISP router in the bridges. That's fair. I'm settled now. What's with everyone moving to Spain? I'm here because my wife is here. That's just how it is. How did you find Japan? Like, how did I like Japan? I actually really liked Japan. I genuinely enjoyed it. So when I was there, I went to the Okinawa Institute of Science and Technology, which is an open, not open, it is an interdisciplinary institution. I really liked it, genuinely really liked it. And I would encourage anyone else to look there as well. Have you ever done any tutorial on parallel processing, not GPU based, in Julia? I've got some embarrassingly parallel loops that are akin to calculating moving mean or something similar on a 1D array, but everything I've tried hasn't given me the expected performance boosts. The only thing I've done is when I did some ray tracing back for the Julia computational computational thinking course. I did a little bit of parallelization on that just to show that you could do it, but I don't think I've done too much more. Basically, all the parallelization I've done in Julia has been GPU based. Are you doing it in Python? I mean, Spain has good food. I'll give you that. It's great for Europe, but it's not South America. I don't really know, if I'm honest, about any of this. The router updates itself, indeed. Julia Python's multiprocessing sucks because of GIL. What is GIL? Does Julia not have GIL? What is GIL? I should know, but I don't. I'm so sorry. Remove report 7 and report 8. And let's just run this again. So we're going to regenerate those two reports and look at them one more time. Global interpreter lock. Oh, okay, interesting. Are you saying you haven't tried Spanish food yet? I mean, like, I'm vegetarian, so I don't tend to be able to eat too much food. I mean, we've had empanadas. I make tacos every Tuesday, but this is not Spanish food. That's Mexican food, you know? So, all right, let's go here. Let's run it one more time. Nsys launch. Where are we? I think I can just go up. Nsys launch Julia double dash project using this guy and go from there. Taco Tuesday. No, I gotta be honest, Taco Tuesday. Like, my wife had never had a taco before I made one for her in Japan or in Okinawa. Oh, I think she might have, but she didn't really. Anyway, I make good tacos. Like, sure, they're vegetarian, but they're good tacos. It's one of those things we just make sure we meet for Taco Tuesdays, just because it's I don't know how to say that. It's just like one day a week where we meet, we make sure that we eat together and we enjoy each other's company. So, like, for streaming, my general time is from 2 to 8 every day, but I think on Tuesdays that will change. So it's not from 2 to 8, it's actually from like 12 to 6 or something. But that's going to be the only difference. I messed up. If I simulate source, simulate accelerations here, where did I screw up? Find accelerations, temp vector. What do I call it? Temp vector. Here, rank quit. All right, try it one more time. Nsys launch. Using this guy, it should build this time, and we should go from there. So to be fair, my cousins used to live in Spain. So they used to live in Sevilla. I did go here before I was vegetarian, and I had like obviously like tapas and stuff like that. Tapas. I actually don't know how to pronounce it. I missed some chat over here. Julia's Python, let's see, Gil. Isn't that more of a Python thing? Also, it's pronounced like Gil. I thought I did pronounce it like Gil, but maybe I said GIL. I'm sorry. Not sure, but from what I've read, Julia is more fundamentally designed for things like parallel for loops. In general, yes. It's meant for more of this type of thing, but that doesn't mean it's always going to be good. One day a week we sit on a table, not to hate each other. Well, no, like, for the record, after stream every day and stuff, we do actually, like, we'll have soup or something light or something. But Taco Tuesday is the day that we definitely have a meal for dinner. Because, I'm typically busy. She typically comes home late. Like, sometimes we'll have lunch together. Which is why I like starting at 2, because sometimes she'll come home for lunch and stuff like that. But it's just a time that we definitely have together. That's the point. And I think it's really important to do that kind of stuff. Let's do CUDA at profile for 1,000 time steps. Run this, take a look at the profiling results, see if it's any better, and then we're going to do the same for the other thing. This actually makes sense. So this makes sense why we're still allocating so much data. Okay, I get it now. Good. So we're going to do the same thing down here. And we're going to do here, maybe. Where is it? Oh, no, that didn't work. Let's just go here. And let's just run one. So we'll take a look at both of these. One here. Okay. A global interpreter lock is a mechanism used in computer language interpreters to synchronize the execution of threads so that only one native thread can execute at a time. Yeah, so I figured that as much. An interpreter that uses GIL always allows exactly one thread to execute at a time, even if run on multi-core processor. Some popular interpreters have GIL, are CPython and Ruby. Interesting, so Ruby too. I think Julia doesn't have anything like GIL. GIL's for interpreted languages. Yes, you can definitely do, you definitely don't need it for Julia. There's definitely ways to do concurrency and stuff in Julia particularly well. There was a workshop that was done at OIST by basically the creator of kernel abstractions that went through all of this. And there's actually a lot of like discussions and stuff to have about this that I just don't know because I basically only do GPU computation. And site. Let's take a look at this. I think this will hopefully be better. So this is 7. I still can't quite tell. Let's look at the CUDA API here. Show an events viewer. So it should be that we have no allocations anymore. Yeah, so if you look now, there is no allocation in the middle there. Perfect. There is no more allocation. Oh, thank you so much for the catch. I don't remember who it was that said it in chat, but thank you for telling me to do the profile one more time or like encouraging me to do the profile one more time. This is good. We got rid of one unnecessary allocation, which is great. Because otherwise, we still have the broadcast kernel and stuff like that, but this is fine. This is okay. In fact, what happens if I remove the broadcast kernel? Let me try removing the broadcast kernel as well and doing that in the kernel itself so we don't have a separate launch. So let's do... I want to do forces, I believe, here. So the temp acceleration is naturally set all to zeros, but let's just remove the broadcast kernel and put that in gravity in here. So we should have a temp acceleration. Here is going to be plus equal to that. So here's in the gravity kernel in there. So I believe... Okay, so I believe what we want to do is set the temp acceleration to 0 at this stage in here. Let me think. I need to think about this. You can do parallel in Python too, no problem, but if it's CPU intensive, then you're effed. Yeah, that's probably fair. Recently, there was news that they have CPython without GIL, and Guido said it was good enough. Oh, interesting. That's good to know as well. Let me get some more water. I was not expecting to spend this part of stream talking about GPU profiling. But anytime we get to talk about GPU profiling, I'm happy. So, you know, it's good. Okay, so where do I actually want to set the accelerations to 0? We have the relay function in here. We have the relay kernel, but probably we want in the accelerations, the find accelerations kernel, where we do n-body is probably where we want n-body. Here. So we have n-body here. We have at index global linear. Then we have the application of the force law. So we have TID and K is going to be plus equal to that. I think if I set the accelerations here to be 0, I think that'll work. So let's do temp accelerations of TID K equals 0. And this means we're initializing it to be 0 at this stage. And I think that's fine. No, we don't want it here. We would want it up here in this part of the kernel. So here's where we're setting the temp accelerations to 0. So for K is equal to 1 to size of positions of 2. And here, and then we're setting it to 0 here. So we're going to do temp accelerations of TID K is going to be equal to 0. What I'm doing here is I'm just avoiding a broadcasting operation. To be honest, I'm not entirely sure. So what this is doing is it's saving a kernel launch, which takes time. But is it actually useful? Not really. I think it's going to be the same exact speed with or without this. So, wait, MRI is different than what I thought it was. I only know that MRI is magnetic resonance imaging. So I think we can right quit here, and then we can go into the iSource simulate here, and we can remove this broadcast here, I think. And this allows for us to have our temp vector just be similar instead. which is quite nice actually. So we can just make this so it is equal to similar of p set.accelerations. And that saves a lot of time actually. So let's write that, and that should be what we need. Perfect. Okay, let's try running this. So we're gonna do, I guess we'll do the same. Let me think here. I'm gonna do remove report 7.qdrap, report 8.qdrap. We're gonna do it one more time. So we're gonna do whatever is this guy here, and let's just do it using CUDA Galilee. Let's run it. And then I think this will solve the problem. We won't have any allocations. We won't have the broadcasting kernel. Admittedly, I don't know. The broadcast might be useful. So here's the difference. With the broadcasting kernel, we can set all threads to set each individual element of the array to be 0. With the kernel that we currently wrote, because of the way we wrote it, we have a for loop in there, so each thread triples up on computation. There's like, I don't know if this is actually good or not. Oh no, screwed up big time. What'd I do? Julia, let's go over here and let's fix it. Julia -- project. And let's run it using CUDA Galilee. And let's run it again and see what we got. It looks like we probably don't have much time to do more than this. So probably after this is done, we can talk a bit longer and stuff, but it looks like once we get this performance done, it's going to be near the end of stream. We've got like maybe 30 minutes left. So we probably want to talk about where we need to go, all the interesting stuff to come up and stuff like that. So obviously stay tuned for the next 40 minutes or whatever. But you know, we don't have too much left to do here. I think this is a good place. Unsupported, undefined name, temp accelerations. All right, let's do simulate.jl, accelerations. Here we have accelerations, accelerations.dat. Okay, that should all be fine. So let's go into vi source and probably forces.jl, accelerations. And it says we don't like temp accelerations. Temp accelerations. There. Here is where it doesn't like it. Oh, you're kidding me. Yeah, it should be temp acceleration. Why did I change from temp accelerations plural to singular? Why would I have done that? Let me modify all the temp acceleration singular to be temp accelerations plural. So let's do S, and we're going to do temp acceleration to temp accelerations plural. Then we're going to do CG. That one is a no. This one is a no. That is a yes. 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 No. Yes. Yes. All right. Let's do it again. Right over here. Control C, D, Julia, using. Let's try it one more time. And hopefully this works out. Peter, 88 Tom, thank you so much for following. Really appreciate it. What is Matt's? So the Matt's Ruby interpreter is just, I guess, is a Ruby interpreter, right? That's fair. Okay, so let's run this one more time. Make sure it runs, and then we're going to do some profiling results. And I think we're good. I think that's a good place to kind of like, you know, obviously there's still much, you know, stuff to do, but that's a good place to kind of talk about where we need to go and like think about what the problems are. I wrote down a list of 3 things that I wanted to get done this stream. We got 2 of the 3 things done, which is still pretty good. I also want to do the tests again now that we're no longer allocating that positions term. Now that we're no longer allocating that, I want to basically run this whole thing one more time and look at the profiling results one more time, just time it and check it out and stuff like that. Because I suspect, I'm not entirely sure, but I suspect it might be a bit faster without that allocation, but we'll see. Using CUDA and Galilee. And let's just take a look at the profiling results and take a look at the timings and go from there. Okay, run this. And then I think we just app profile and go from there. I'm actually really excited with how far we have gotten today. I mean, look, it's slow progress, but it's progress. And the way I see it is any progress is good. You know, it's Friday, November 26th. By the way, everyone in the US, I hope you guys had a happy Thanksgiving yesterday. And I hope you're having a happy Good Friday or Black Friday today. I gotta be honest, I always confused Black Friday and Good Friday, and they're completely different. You know, like one of them is like when, you know, Jesus died, and that's Good Friday, but Black Friday is a sale day. And it's like, it's weird to me that Black Friday, which you think is going to be the day, like a grim day in Christian's history, is like, you know, I don't know. Like, it's just weird that they're named that way. You know, Good Friday is the day that Jesus died, so you'd think that would be Black Friday. And then you'd think that, you know, Black Friday is the day of sales, so you'd think that, I don't know, you know, dealing with like, I don't know, evil, I don't know, money, I don't know, you'd think it'd be Good Friday. I don't know. Just, I think the name should be switched, so I always get confused. I don't know why I mentioned that. I genuinely don't. I'm so sorry. By the way, Zero NE, thank you so much for following. Really appreciate it. I'm sorry. I don't know why I brought that up. I think it's the official implementation of the Ruby language, same as C Python, for Python. Oh, wait, really? I didn't know C Python was... I guess that makes sense. I'm so far out of the Python loop. I really don't know like what's going on there. Okay, so the next thing I'm going to do is Julia double-dash project. And let's just run CUDA at time on a couple kernels. So using this guy, and we're just going to run CUDA at time, starting with 128 and all the way up to 4096, and see what happens. The fact that we were allocating that positions array says to me that actually maybe my GPU won't chug anymore when I'm doing the computation, and we might be able to do more particles because we're not using that much memory. I think it was just allocating a bunch of just dummy vectors and stuff. So let's see what happens. I'm going to run it a few times and see what we can do. Cool. So we'll do an at time after this is done and see what we can do. Oh, man. Okay, so let's do the CUDA. Should be an at time in here somewhere. Yeah, there we are. 128. Good. This is the same thing we were running before. So that took 3 seconds, which is about the same as before, 256. All right. This takes 7.4, 5.12. I did 5.13, but fine. I guess it's fine. Let me run it with 5.12 instead. Powers of 2 are important sometimes. All right. So now we're going to do... now we're going to do 1024. And then we'll do 2048 and 4096. And I'm just checking the FPS on stream to see when I start to chug. Because I will start to chug at 2048, I'm pretty sure. All right, give it a go. I'm still at 30 FPS, so I think I'm fine. And now we're going to do it one more time with 4096. I'm fairly certain I'm going to start slowing down here. All right, what's my FPS? It's actually 29.6. 17. Okay, I'm dropping. Yeah, my FPS is dropping. Give me a second. It technically says I haven't dropped any frames, but I know I've dropped frames. Like... Okay, so let me take a look here. We have 11 megabytes for... Oh, no, that's nice. Look at that. 7 GPU allocations. Beautiful. That is the exact number of allocations you want. Because 7 is... we have a temporary vector. Then we have a position, acceleration, velocity. And then a second set of positions, accelerations, and velocities. Literally 7. That is the exact number that we needed. 7 allocations. Perfect. Control D. That was nice. That was super nice. I'm glad we did that. Okay, let's take a look at the profiling results as well, just to double check to see what we've got here. Timing-wise, this is the same as before. Actually, just a little bit faster, but not that much faster. So let's do nsite sys, and we're going to run report 7.qdrdp. QDREP, yep. Let's take a look at the CUDA API here, show an events viewer, and let's see here. So we have the allocates, the event create, record, again here. So what we're doing here is we're now no longer having a broadcasting kernel. And in fact, maybe that's what sped up the computation, the fact that we don't have the broadcasting kernel anymore. So things are just a little bit snappier because we're missing that CUDA launch. But ultimately, I don't think we're that much faster. Good. Let's take a look at report 8. Open report 8. Let's do the... Oh no. Show an events viewer. Look at this, buddy. Everything is in CUDA H2D. There's nothing. It's just everything is in that. And we only have this little bit of computation in there. Oh, well, that's what it is. Whenever I show people profiling results, I always kind of mention that's what we got here. Okay, let's go down a bit. Okay, this looks good to me. I'm happy to see that. Wonderful. Whoever told me to look at profiling results again, I'm happy you did. I actually, that was super nice to do that. So git status here, git add dot git commit -m for the profiling improvements. 7 allocations. That was beautiful. Okay, origin development. Okay, that was nice. That was super nice. I realized, look, maybe some people were lost there because I wasn't being very clear, but if you have any questions, comments, concerns, anything like that, feel free to let me know. So what we just did was we were just looking at the GPU performance of our code, checking to see like what was running, why it was running, and making sure that we had the appropriate number of allocations so we weren't using unnecessary data. What you saw was actually quite nice in kind of an external sense. So every time I was running that code before, my stream would drop down to 6 FPS or something like that. Now it dropped down to 16 FPS. So I have literally like 2 to 3 times as many frames as I did before. So, you know, in some sense, that's a win. I'm happy with that. Okay, let's go over here. Where am I? There, that's what I want. Okay. So the other thing I want to do is add in the 4D force. Let's just go ahead and do that now while we're thinking about it. So let's go into vi source forces.jl and let's just do it because at this stage, I think we're good to go. So I'm going to add in gravity 4D and we should be able to run with a 4-dimensional gravity thing. So let's go here, paste that there, and I'm just going to do it. So gravity 4D here, this is going to be R3 instead of R2. This is going to be R3. It should only happen with 4D potential, so that should be fine. And what do we need to do? So we have U here, which will still work. The only thing we need to do is change R3. I think that's it. I think we just have to change it to R3. I think actually, what we had before is fine. I think it was already running with the gravity 4D. Yeah, it was already running with the gravity 4D because, wait. It's going to be x squared plus y squared plus z squared. So it should be x cubed plus y cubed plus z cubed. No. I was wrong. So it's x cubed plus y cubed plus z cubed. And then we want to do it's going to be cubed root. Can we do the cubed root? Is that something you can do in Julia? What is CBRT? Does that exist? Of 8? Okay. CBRT here. And then we just change this to r cubed plus 1. And in principle, this will run. So we have r cubed. Yeah, let's see what happens. Okay, so we're going to run another 4D result, 4D simulation, and see what it looks like. It's probably going to look the same as the other one. I'm just warning you, it's going to look the same, but we're going to run it anyway. So Julia, double dash project. Actually, I need to do one more thing. Let me go ahead and make it so this is 1/6 as well. The reason I want it 1/6 is because I know we're gonna have a 6 I know we're gonna have a 6 there. So let's just do 1/6 times. I guess I'm gonna have to do it this way. 6 times this guy and another parentheses there. I screwed up. There's gonna be a name error. Did I mess up? Wait, what name error would there be? Let's go here to 6 times this guy and another parentheses there. All right, quit. So let's run Julia double dash project. Okay, and let's run it one more time. So I probably screwed up. I mean, Amaris is probably right. I screwed something up, but that's okay. We'll figure it out. Again, if you guys are liking this content, please just feel free to let me know. I mean, obviously, like, you know, I hate to be that guy that like begs for follows and stuff like that, but like honestly, it does mean a lot to me. I'm trying to make the research that we're doing here like engaging and interesting to people, and sometimes it's hard to do. Like we're talking about like GPU engineering, we're talking about like you know 4 dimensions and stuff like this. It's hard. Sometimes it's very hard. So if you're interested, if you like this stuff, just let me know. Did you cube root R2 instead of R? Did I? Let me check. VI source and then forces. CBRT. You're totally right. Oh, no, you're right. This is CB, and this should be changed to R3. Okay, there we go. I understand now. Control D, Julia, try one more time, and now we'll try the Gravity 4D and see how that goes. Sebastian1733, thank you so much for following. Really appreciate it. But But yeah, like in general, like I said before, you know, we're trying to start an open research company, make the research open, engaging, interesting for as many people as possible. And, you know, part of that is here on Twitch, you know, starting it and getting as many people as possible to be engaged with the research so we can, you know, show people that it's cool, it's fun, it's enjoyable, it's something that, you know, I don't know. I really don't know what else to say here, but I do want to say I really appreciate you guys being here. It means a lot to me. Okay, so let's go ahead and run Galilee.run. We're going to run it in 4 dimensions with 256 particles, 4 dimensions, and then we're going to run Gravity 4D. And then output method is going to be just default output method. And over here, what we're going to do is Control D, remove accelerations, and what else am I removing here? It's accelerations and one other thing. Oh, Hip, how are you, man? It's been a while. I hope you're doing okay. Accelerations and positions. No, check, because I'm bad at naming. Okay, so we run this. It should be fine. It is not fine. What did I do? It's 4D. Okay, now it's fine. We got it. Okay, so we're going to let this run. We'll take a look at the visualization. It's going to look the same. Like, I need to set L equals 2. I forgot to set L equals 2. I'll do this one more time. I need to set L equals 2 or something, or whatever we set it to last time, so we get similar results. And then we'll take a look at the visualization, and then we'll talk about what we need to do from there. My favorite part was the bit about good and Black Friday. I'm sorry. Let's do this again. Let me run L equals 2. Over here, we're going to remove that. Run it one more time. This should be way faster this time, I think, because we don't have the pre-compilation. And then we're just going to plot it. Control D, CD into, what am I doing? CD into aux, I believe. Now let's run GNU plot. Plotting 1D. I don't want to plot 1D. Oh, geez. That's not going to work. Plot 3D, man. It's okay. We'll let it run, and then we'll plot. I can probably cancel. I screwed up. So just plot.gp should do. Okay, give it a second, and then we should have a 4D plot to look at. Wow, amazing. It's going to look the same. It's literally going to look the same as every other plot that we've had. You're not going to be able to tell the difference. I'm so sorry. I don't mean to break it to you. I hate to break it to you, but like, this particular visualization is not going to look cool yet. It's going to take some time. Mirage here. Okay, so here's the initial bits, and wow, amazing. Actually, it does kind of look different, doesn't it? Whoa, actually, what's going on? Holy crap, what is going on? That's way different than I thought it was going to be. Oh no! Here I am thinking that's going to be the exact same, but I just realized it's a 1 over r cubed force law, which means as the particles go further away, they're not going to feel each other. So what's happening is these guys zoom out, and then they just get stuck. They get stuck. They don't come together. Oh no! Oh geez, that ruins everything. Oh geez. Okay, well, okay, that is, do I have to run on different time scales? Because they will come together eventually. Okay, well, that's super disappointing. Let's go ahead and run Mogrify, and let's recreate that visual that we have in the upper corner, because frankly, that is way different than I thought it would be. Oh no. Oh, the whole 4D galaxy simulation is just, it might not be a good idea after all. Who would have guessed that removing yourself from physics is a bad idea. Okay, let's go ahead and run /create video. Yes. Oh, I can't believe that happened. Okay, let's go ahead and move test.mp4 into 4D. That MP4. Okay, and now what we want to do is set it all. So let's do history, grep. Let's do, what am I looking for? Concat here, and now we're going to run 633. Sure, that should do it. All right, this should recreate the all video that we have in the upper corner. 1 second. Where is this? Is it here? Yeah, there it is. 1 second. Wait, what? How's that still running? Control C. Let's run all, and let's just move forward to the 4D simulation. Yep, that's what I thought was going to happen. Yep, perfect. Okay, wonderful. Let's move this in the upper corner, and let's go here. And yeah, let's just go. Okay. Let's see. Don't panic. Favorite part was the bit about Black Friday. Does the 4D sim have a specific goal or purpose, or are we experimenting for fun? There's, okay, look, the overall goal here is, how do I put this? The 4D-ness is not particularly interesting for my own research purposes. I'm mostly interested in accelerating the N-body simulator to make it so basically accelerating the N-body simulator so that we can do like larger scale dynamics and stuff like that. In particular, what I'm interested in is like adaptive mesh refinement and stuff like this of octrees, or maybe different clustering methods that you could do to speed up the computation and stuff like this. So the 3D results are actually more inherently interesting for me. But the 4D results I was hoping would be interesting for other reasons. So what I'm going to do is I'm going to run the same simulation we just ran, but with a larger time step to see if the results are different. So we're going to cd back a directory, run Julia -- project. Here, we're going to remove the output file here, and then we're going to do include, using, and then we're going to try it one more time and see what happens. I'm going to increase the time step, and my feeling is with an increased time step, we'll see the particles come out, but they'll come back together. It's just the time will take, it will take longer to get what we want, but I think we can still get what we want. So let me increase the time step by a factor of 10 and see what we get. You can use 1 over r squared also for the 4D, something like, right, yeah, so we can do 1 over r squared. Oh, you're doing plus w squared. X squared plus y squared plus z squared. Oh. Yes. Yes, that's what I was doing before. That's literally what I was doing before. And the reason I thought it had to be 1 over r squared, yeah, so if I do that, it works. Like we get the visualization that we saw before. Oh, I should save that visual. Yeah, okay, I'm sorry. Let me save that visual because I actually don't have it anymore. So let's do the gravity sim. So this is that visual that you're looking at right now. I'll show you that visual. Oh, shoot. Shoot. Okay, let me generate 2 more things before the end of stream. So one is the visual that you're looking for, Tesla. Julia -- project, remove this guy. And then we're going to run at a different time step. Here. And that should be fine. I think I'm going to have to do using, and then once it's built. So making the particle system more efficient so that we can calculate more particles on the same GPU resource. Something like that. It's not only calculating more particles, but it's also making the simulation faster. The reason this is interesting is actually for a couple of reasons. The first reason is that I'm actually really interested in some other stuff. Like for example, I actually want to make ASCII art. Now that doesn't sound like something that has anything to do with 4D galaxies, but the space partitioning of a galaxy simulation, an N-body simulation, is identical to the space partitioning that you use in color quantization. And color quantization is something that I want to use as the foundation of creating photomosaics, which is the heart of ASCII art, so it kind of builds itself that way. Then once we have that done, we have the tools to actually go back to the gravity simulation that we're working on here. And what I want to do is I want to use the tools that I was applying here to make a better fractal generator is what I'm looking for. If I generate a better fractal generator, then I can do a better fractal compression method that should, in principle, also work for physical results. So essentially what I'm doing here is I'm ultimately trying to increase the speed of fractal compression, which is only marginally related through a bunch of steps to this simulation here. But once I do the simulation and I learn how to make it more efficient here, then I can learn how to make other things more efficient. And eventually that bleeds itself into fractal compression, which I then want to use as like a general purpose N-body physics solver again. So essentially we start here, then we go through a bunch of computer graphic stuff, and then we come back, and I want to do physics on a fractally compressed grid. That's the ultimate goal. That's where I want to go. But right now, 4D Galaxy Simulation is a start, kind of getting our feet wet, getting started with all the tools that we need, and eventually we work our way there. So that's where we're at. Let me do, actually cd aux in here, and let me just do the last GNU plot here, and then plot 2D, are you kidding me? There. So we'll generate the plots over here, we'll take a look at that visual, which will be the visual that Teslost said. Just everything is r squared. So anyway, the point is, the 4D-ness is not particularly interesting to me. It is it's just part of the overall process, right? And also, I figure a 4D galaxy simulation is one of those things that like it catches people, you know? Okay, so here's that simulation. So you see that they all come together and they do this thing. So this is the simulation that Tesla said. They all do exactly what you might expect. Let me also create that visual. I had it before, but I accidentally just deleted it. So Mogrify here, turn that into a video, and then we're going to do, copy that over to 4D R2 is what we're going to try. Oh, I knew this was going to happen as well. Okay, so while that's working, I'm going to run this with the 4D potential at a much larger time step. Sorry, I've got the hiccups here. Okay, so we've got that. Let's do create video, and then we'll take a look at this video as well. And I'll show it to you guys, and then we can go from there. So let's do mpv test.mp4, full screen that guy. So this is it if we use r squared instead of r cubed. This is the visualization we had before. It kind of makes sense. We talked about it before with the fact that we're doing the, like everything's coming in towards the center. Like it's kind of the same thing that you'd expect in 3D, except in 4D. And the visual that we're doing here is projecting from 4D down to 3D using a type of stereographic projection, which is kind of like a shadow type of thing. So that's why as you go further out, the particles move faster because of just the way that we're doing the projection here. So that's what we see there. Let me go ahead and move test.mp4 into 4D R2.mp4. Sure, that'll do. Now let me run it with a slightly longer time step and see what we got. Man, that's super, it's frustrating to some extent, but also like it should be expected. Maybe we need to run with an adaptive time step such that like, did that run? Let's go ahead and remove, let's remove accelerations and then also the check.mp dat file. Let's try running it again. And then we're going to regenerate the GNU plot script and see what we got. This is pretty dope. Building up from fractal compression, building up to fractal compression from other related projects. The only thing I know about fractals is that they occur in broccoli. Oh, that's probably fair. Eat your vegetables, and they may be related to chirality. To be fair, it's a different type of fractal than the type that people are typically used to. So let's run GNU plot. And that we don't care so much about the self-similarity. We care more about the ability to generate shapes via iterated function systems. So fractal compression doesn't care about self-similarity. It's a common misconception about how it works. It cares more about like Barnsley-Fern type of generation and stuff. Let's take a look at Mirage here. Okay, so here we have the particles. They should zoom out. It's not interesting. They just crystallize. Which is expected. You need some other force to bring them all in. And I suspect with more particles, maybe it gets more interesting because if you have more particles and there are more particles that are closer by, that would force people in. Anyway, the 4D simulations are a bit of a dud, but that's okay. And now my Wi-Fi works again. Wonderful. Okay, so I think now is a good time to wrap up what we've got. Git status dot, let me go ahead and add that. Git add source forces.jl git commit -m, and we're going to do adding r cubed force law. There we go. Git push origin development. Okay, so now's a good time to wrap up. And let's talk about what we're going to do from now. So at this point in time, we have the n-body simulation kind of working. It's parallel. We did a lot of performance tests. It looks pretty nice. It's getting there, you know? So the next step would be to make the simulation way faster, which is where I'm actually kind of interested. I'm super interested to see how it goes from here. So for example, with the n-body simulation that we're doing right now, every single particle looks at all other particles and kind of sums all the forces together. Even without changing the way in which the particles look at each other, there's still some optimizations we can do there. Like, for example, we can make it so, like, we do a parallel summation over all the particles or something like that. So that's something I want to look into tomorrow, specifically like how kernel abstractions implements the parallel summation. We might also look into histogramming again, which is a necessary method for visualization of a huge number of particles. But also, I'm kind of interested to see... Yeah, so the big problem here is that my GPU memory is fundamentally limited, and I can only do so many particles. And so if we could find some way to better cluster the particles so we limit memory, like if we use a different integrator like RK, Runge-Kutta instead of Relay, so we don't need to keep track of as many time points. I don't know, there's stuff like this that we need to consider. But overall today, we actually did a lot. We allowed our system to have different force laws. We basically made it so the performance is a little bit faster. And we made it so we have the minimum number of allocations on the GPU, which I'm incredibly excited for, actually. Like, I think it's really cool. I think this is probably a good place to go ahead and wrap up for the day. I've been streaming for about 5 hours and 51 minutes, 52 minutes. If there's somebody that you want to raid at the end of the stream, let's see who's live. Here, we have Kip Boga, we've got Gamozo, we've got Lana Lux, Oh Bother is live. Maybe we do Oh Bother. It's been a long time since we rated Oh Bother. That sounds good. Let's go ahead and do that. Let's bother him. Anyway, guys, thank you so much for coming in. I'm going to go ahead and start that raid. Just before finishing, though, if you have, if you like this kind of content, I'll be live again tomorrow, hopefully from 2 to 8 p.m. again. Might be a little bit late because my wife is coming back from a trip, and I might have to, kind of go shopping or something like that when she gets in. But I'll let you guys know on Discord if that happens. Let's go here to Discord. I think that's actually it. So we made a lot of progress today. Thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I'll see you guys around next time for the next episode of Leos Labs, which will be tomorrow when we do a whole bunch of cool stuff, hopefully related to N-body simulations. But if I'm honest, maybe will be something else entirely, depending on whether I think there's any hope in the 4D simulations or not. I do want to go back to fractal compression, which means we do have to do histograms again. Maybe we do that a bit. I don't know. Lots of little things. Thanks again, guys, and I'll go ahead and start that raid on. Oh Bother. And yeah, I'll see you next time. Thanks again. Bye, guys.